Okay, good morning, everyone. I am quite excited to guide you through this crash course, the FRM Part 1 crash course, which is designed specifically for your upcoming exam. Now, this course is kind of set up as a quick, intense revision for those who have already covered the material at least once. Okay, so I'll add this point. Now, this is the plan that we'll actually focus on the core topics. We'll try to concentrate on the most important topics and the key concepts, and we might skip over some less critical subtopics so that we can optimize our study time since it's a crash course. We also won't be able to go into detailed derivations like we do in the class and our self-paced course, and we'll focus instead on a higher level kind of review of the material. So the goal is to refresh your memory and help you to strengthen your understanding of the essential topics without getting bogged too much down into complexity. Also, to make the class more efficient, we'll have the class as a more kind of one-way kind of a topic than usual, because normally I like to engage a lot with all of my students, asking for your thoughts and having discussions. This time, however, we need to keep those interactions to a minimum to cover everything quickly. Also, I would like to request all of you to keep your videos turned off during the class, because it might interfere not only with the bandwidth, but with the PPT as well. The interface should not get disturbed at all. And the good news is that you don't need to take any notes. So don't worry about writing anything down during the sessions, because all these slides will be available as PDF format in the same learning management system in which you have enrolled, which will be complete with all the text and all the annotations that are required. Also, since we have to cover all the 4 modules over the next few weeks, say 4 weeks only, so each class, it might be 4 to 5 classes in total. So each class will last between 5 to 7 hours on an average. Okay. So I can understand that it's like a marathon, but as far as the exam is concerned, it's actually a great practice, because exam you all are aware of, it's a 4 hour long exam. So this class will actually help you to, you can say, build exam temperament. You will get used to sitting and focusing for extended periods, right? Just before the exam. So yes, these long sessions will be very challenging, and you might be tempted to leave early, of course. But staying for the full session, I think, is very, very important, because see, for the exam, finally, patience, resilience, endurance, all these things are the key aspects. And being present throughout will actually help you, become confident that you are fully prepared, and you are confident you are able to reinforce your learning properly. Also, one thing that I've taken care of, given the recent trend of increased theoretical questions, because if you see, starting from, in fact, this trend started from 2018 only, even before the syllabus was changed in 2020, that the number of theoretical questions actually increased over the last few years. And this has actually been even more enforced and more emphasized after 2020, after the change in the curriculum, even for conceptual topics. Say, let's say there's a topic in regression diagnostics with respect to the white test for heteroscedasticity. Now, instead of performing the full calculations in the exam, they probably will ask you the steps of the white test. I mean, if you see, there are questions not only in the gap sample paper questions, but also based on the feedback that we have got from our candidates, that steps of those tests were asked rather than the complete calculation. So we'll actually adjust our focus accordingly. Okay. And this shift, as I mentioned, it has been evident in past exams also, apart from the GARP sample paper question, where a lot of theoretical understanding has been prioritized to some extent. Then, of course, we'll not be able to tackle numericals with long, detailed calculations due to time constraints. But again, as I said, there is a good news that the PDFs will be available. So if you are unclear about any solution, even though we'll not discuss detailed numericals, we'll discuss short numericals. Even then, if you are unclear about any solution, you can always revisit the recording of our session, and you can also refer to the detailed PDF slides. So recording will also be available of the class, and detailed PDF slides will also be available. Also note that this is not a doubt solving session. Okay, this is not a doubt solving session, because for doubt solving sessions for the candidates who are enrolled with MidhaFin. We have a separate session. In fact, before the exam, we have multiple sessions dedicated to doubt solving, apart from the general doubt solving that we do throughout the year. So we encourage you to save your doubts for those specialized sessions. This is especially to the MidhaFin candidates. And let's start the course. I think it's a good opportunity for you to just solidify your knowledge and try to head into the exam with a lot of confidence. It is also possible that sometimes I might not be able to look at all the chats immediately, but I'll definitely have a look at it later on whenever I get time, and I'll answer to all your queries later on. Okay. So let's start. I look forward to try and help you all to review and prepare efficiently. Let's start with the first topic today. We'll try and cover 4 weeks. In fact, we have divided the course based on our study plan into 4 blocks. Out of those 4 blocks, we are going to cover, you can say, close to 0.7, 0.8 blocks today. We are actually covering the first 12 topics of quantitative analysis, QTA, today, starting from fundamentals of probability up to the time series chapters, okay, and volatility chapters. Okay, so let me just have a quick look at all the chats till now. So yes, yes. Okay, Britman is asking, can you increase the volume? Is the volume not audible properly? Because this is the maximum volume that we can have right now. Is the volume okay for everyone? Okay, fine. So let's start with fundamentals of probability, some basic definitions. So random experiment is an experiment whose result is unknown. Just give me 1 minute. Just take this back here. So it is an experiment whose result is unknown. Then variable is a variable whose value is unknown. Then outcome is the observed value for random variable. Sample space is the set of all possible outcomes. Event is the subset of the sample space. So that is one or several outcomes out of the sample space. That is an event. Now, what is the sample space? Let's just explore a little bit. It is a set containing all possible outcomes of an experiment. It is denoted as either ohm, capital ohm, or capital sigma, sometimes people call it, or capital S. And of course, the set of outcomes will depend on the problem being studied. So let's take some examples. So if we are studying the problem of returns on S&P 500, okay, so we all know that the returns theoretically cannot be less than negative 100%. So if you lose all your money, then the return is negative 100%. It cannot be less than that. And there is no theoretical positive bound to the returns. Again, I'm saying theoretical. So the sample space is all real numbers in this range, negative 100% to infinity. Now, if we are interested in the direction of returns instead of the actual returns, so direction of returns, either it can be positive or it can be negative or maybe no movement at all. So these are the 3 possible outcomes. Then if you are studying bond defaults, so either the bond will default or the bond will not default. So these are some examples. Now, events are subsets of sample space, and any event is denoted by omega or capital E. So for example, if you are rolling a 6-sided die, this is your sample space, 1, 2, 3, 4, 5, 6. And if you want to find out what are the outcomes or what is the event of getting an even number. So if, let's say, we denote E as the event of getting an even number, then E contains these 3 elements, 2, 4, and 6. And as I mentioned, that events are subsets of sample space, right? So mathematically, we'll write it like this. E is a subset of S. It means all elements 2, 4, 6 are already present inside the bigger set S. Now, an event with a single outcome is known as an elementary event. So for example, if suppose you have an outcome in this experiment only, if I say that what is the event of getting a number less than 2, so obviously only one outcome will be there, 1. So this is an elementary event. Then any event with no outcome is known as a null event. It is denoted by phi or this null set, the empty set. Okay. So this is an example. G is equal to this empty set. And of course, for null sets, the probability will be equal to 0. So for null events, a definite probability of 0 can be assigned. Now let's move to another concept, event space. Now this is a concept which I have seen that it is not very well understood by many candidates, so they tend to skip it. So obviously we'll not be able to go into details as we have done in the class, but I'll try my best to explain it quickly. So event space is denoted by this symbol F, consists of all combinations of outcomes to which probabilities can be assigned. So for example, if suppose this is the sample space, the experiment is rolling of a coin. So two outcomes are possible, heads and tails. So when I say event space, so event space is basically combinations of outcomes to which probabilities can be assigned. So in simple terms, you can say that it is the set containing all possible subsets actually. So if you see how many subsets of this set are possible, actually four. So these are the four subsets. One is H, one is T, one is H comma T, and one is phi. Now it is interesting to note that this phi is a subset of every single set. Remember that. So phi or the null set is a subset of every single set. Now when you combine all these four subsets into a single set, you actually get an event space. So that is the meaning of event space. It is the set of all subsets. Okay. Now, one thing also you can just note over here that in the event space, even impossible events or null events are also considered. Now, for example, when you throw a coin, it is not possible to get both heads and tails at the same time. So the probability of this event is actually zero, right? Even the probability of phi is zero. So event space, there is no bound that only positive probability events have to be there. No. Zero probability subsets, the events which are having zero probability will also be there in the event space. That is one of the features of event space. Now let us go to general probability algebra and Venn diagrams. So what is a complement? Complement is also known as not. Okay, so this is the symbol for complement, and sometimes it is also written as a complement like this. Okay, so based on the Venn diagram, it is quite clear that anything which is not in A or outside of A, which is in the shaded region, which is in the sample space but not in A, it is nothing but the A complement. So what is the algebra over here? Probability of A complement is equal to 1 minus probability of A. So for example, if probability of passing the FRM exam is 85% or 0.85, then probability of not passing the FRM exam is 1 minus 0.85, which is 15% or 0.15. Now let's come to intersection. So what is intersection? Intersection is basically that event A intersection B which contains both A and B. So A and B both are there. Okay. So let's take an example. If suppose A is this set 7, half, 2, 81, and 46. And we have B as 8, 4, 1 by 2, again half, 74, and 7. So if you want to find out A and B or A intersection B, then you simply have to check which elements are common to both A as well as B. So which two elements are common? One is half, the other one is 7 because it is present in both the sets. So this will be my A intersection B. Now let's come to union. So union, A union B, and which is sometimes referred to as A or B. Okay. Now, even though we mention it as A or B, but it actually implies A or B or both. Okay, because uh, although this or both is not required to write explicitly, but it is implied that even we are talking about the middle region. We are not talking about A exclusively, right? So that is why even if I say A or B, it is actually sufficient to explain that the middle region is also being included. But just to make it more clear, it is imperative, it is actually better to write A or both. Now, in general, the probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. This is our first algebraic equation of prime importance in probability, which has been tested many times in the exam. So again, the logic behind this equation should be quite clear, because if there are two sets, A and B, and if you're adding them, you can clearly see that the middle region, which is common to both A and B, is actually being counted twice. Okay. So to give a proper adjustment, you have to subtract it once. So then you will get the full A union B. Okay. Now, what are mutually exclusive events? Mutually exclusive events are events which cannot happen together. So for mutually exclusive events, the probability of A intersection B is equal to 0. So this is how we can denote mutually exclusive events using the Venn diagram format. So A and B, nothing is common between them. That is why A intersection B is the null set. And so probability of A intersection B is 0. See, I have not written A probability of A intersection B is equal to 5. No. Make a very clear distinction between sets and probability. So when we are talking about sets, A intersection B, unless and until I have not written probability, okay, we are talking about events. So this is a null event. Nothing is common. But when I say what is the probability of this null event, obviously it is equal to 0. So when you apply this PA intersection B to the general probability algebra over here, so this term becomes 0. Okay. I hope my laser pointer is visible to everyone. The laser pointer is visible to everyone, right? I'm highlighting A intersection B. It is visible, correct? Okay. So if this term becomes 0, what will happen? What will happen? The probability of A union B in this particular case will become PA plus PB. And in our self-paced course, in our main videos, we have actually done a very beautiful derivation of this using some very practical examples. Okay. So that these things are actually matching with our initial ideas. But anyways, as I said, this is a crash course. So detailed derivations can't be there, but at least for basic understanding purpose, I think this is sufficient. Now, we all know that one of the mathematical definition of probability of an event to occur can be PE is equal to NE over NS. So NE is the number of favorable outcomes for event E, and NS is basically the number of outcomes in the sample space or total number of possible outcomes. That's it. Now, mathematically, this assigns a number between 0 and 1 to each event E. And it is very important to note that this probability that we are talking about is actually the unconditional probability. So over here, till now, we are referring to unconditional probability. Remember that. Now let's come to three fundamental principles according to the GARP curriculum. Although this is something in which different authors have different viewpoints and different literature has listed these principles in a different manner. But based on the GARP curriculum, you have this fundamental principle: the probability of any event cannot be negative, of course. It has to be greater than or equal to 0. And we have all seen in the previous case that it has to be less than 1 also. And the probability of sample space is equal to 1. Also, for any number of n mutually exclusive events, probability of A1 union A2 union up to AN is equal to PA1 plus PA2 plus up to PAN. Okay. So we saw this for two events. Over here, for two events, we have already seen this. PA union B is equal to PA plus B. So the third principle states that you can extend this idea to n number of mutually exclusive events so that you are getting PA1 union A2 union AN up to PA1 plus PA2 plus up to PA. Now, what are exhaustive events? When two or more events form the sample space, they are known as exhaustive events. So the word itself, exhaust, is actually quite clear to explain what are exhaustive events. So exhaustive events, basically they exhaust the sample space altogether. So let's take an example. So if suppose this is the data set for 6 sets over here, 6 or 7 sets, A, B, C, D, E, F, and G. Now, if I have to check which of these are exhaustive events, so one thing I'll also do, apart from the exhaustive check, I also perform a mutually exclusive check. I'll tell you why. Because there is a special class of events which we discuss in probability, mutually exclusive and exhaustive events. Those are very important events. So if these are the given events, let's combine randomly some events. Say we combine A, D, E, and G. So if you combine A, D, E, and G, they are exhaustive. Why? Because you can see if you combine, 6 is there, okay, 3 is there, okay, 1 is there, 2 is there, 4 is there, 5 is. So 1, 2, 3, 4, 5, 6 is there. All the and the experiment being considered is actually the role of a single six-sided die. So all the possible outcomes are included if you consider A, D, E, and G together. But they are not mutually exclusive. But they are not mutually exclusive. Why? Because 6 is common in A and D. Although mutually exclusive events make sense for two events only, we take them in pairs. But just to make things simple, I'm just assuming that even if one of the pairs is having a common event, we'll assume that we'll say that, okay, these are not mutually exclusive events. Then let's consider only A and E. A and E. So A and E, they are not exhaustive, but they are mutually exclusive. Because if you combine A and E, do you get the entire sample space? No. You do not get many numbers. You only get 1, 2, and 6. But they are mutually exclusive because there's nothing common between them. Now let's consider a very special case of events, which is BC. These are exhaustive as well as mutually exclusive, and together we call them as mutually exclusive and exhaustive events, MEE events. Okay. Now let's consider BF. BF is also MEE, exhaustive as well as mutually exclusive, because there's nothing common between the sets in B and F. Okay. Because see, you might say that C and F are same sets. Yes, in terms of the outcomes, they are definitely the same sets, but maybe we have defined them in a way that coincidentally the outcomes are the same. So maybe C, we have defined it directly as the event of getting an even number, and F we define as, say, the event of getting a number more than 1 but less than 3 and greater than 3 but less than 4, something like that. Okay, so we can definitely have our literal definitions, but finally the sets are identical. So B, C, B, and F, they are exhaustive as well as mutually exclusive. E, A, and G, they are not exhaustive, but they are mutually exclusive. Okay, so this MEE, this class of events are very, very important in probability theory. Okay, so we'll discuss why later on. Now, what are independent events? Two events are independent if the probability of occurrence of A does not affect the probability of occurrence of B. Okay, so PA intersection B is equal to PA times PB. This is the algebra for independent events. If the two events are independent, then the probability of their intersection is simply the multiplication of the two individual unconditional probabilities. Now I'll just pause over here. Okay, and although I mentioned that we'll not be able to have a discussion kind of class, a lot of discussions will not be there, but some minor discussions we can have, some small discussions, because this doubt is asked many times. Are you all clear with the idea of the difference between mutually exclusive and independent events? I mean, have you ever thought that what can be the relationship between the mutually exclusive and independent events? Anyone? Mutually exclusive and independent events, are they same, or is there any relationship between them? Anyone who would like to answer?
They're not the same.
They are not the same. So any relationship between them? Not a direct relationship, but any implied relationship, can you say, between independent events and mutually exclusive? Can I say that mutually exclusive events, listen to my statement very carefully, mutually exclusive events can never be independent. if I say this is the implied relationship, if the events are mutually exclusive, then they can never be independent. Is this correct? Yes, absolutely correct. Because see, mutually exclusive events means what? That if one is occurring, the other cannot happen. That is mutually exclusive. Nothing is common between them. So either of them can happen. Either it will rain today or it will not rain today. Either a candidate will pass the exam or the candidate will not pass the exam. Okay. So mutually exclusive events, if you see by definition, there is an element of dependency between them. They are actually dependent on each other. So this is the implied relationship that mutually exclusive events, they can never be independent of each other. They are always dependent on each other, because if one happens, the other cannot happen. Okay. So this is an indirect observation, indirect interpretation regarding the relationship between independent and mutually exclusive events. Now, if suppose you apply this to the general probability algebra, then your general probability algebra becomes PA union B is equal to PA plus PB minus PA times PB. Okay. Now, how to try and visualize independent events? So let's say we have this Venn diagram over here, and the probabilities are demarcated based on region. So what I mean to say is, if you want to calculate the total probability of A, this 24% is exclusively for this region. Remember that. Okay. So this is how the other Venn diagrams will also be done when we'll try to visualize conditional probability. So if suppose you have 24% over here, 16% over here. So this is 0.4, 24 plus 16, 40% is PA. PB is how much? PB is also 40%. So can you just say, by looking at this Venn diagram, let's say nothing else is given to you in the exam, only this is given to you in the exam. Can you say that these events are independent or not? Anyone? Are these events independent? What do you think?
Yep.
Yes, they are, because PA intersection B is actually 16%. So PA intersection B is 0.16. It is clearly given, which is same as PA times PB also, because PA is 0.4, PB is 0.4. So PA times PB is 0.16, which is same as PA intersection B. So if this kind of a Venn diagram is given in the exam, you can just calculate and multiply the individual probabilities and check if the intersection is common. Now let's come to conditional probability. Conditional probability is the probability of any event given that another event has occurred. So this is how it is denoted. PA given B. So this sign, this bar over here is actually given. Okay, this is how it is stated. And this is the general algebra for conditional probability. Again, we cannot derive this today in the crash course. PA given B is equal to PA intersection B divided by PB. So if two events are independent, then PA given B is equal to P. Again, all these statements we have actually derived in the class. So, but from the exam point of view, it is important to remember that if two events are independent, then their conditional probability and unconditional probability are same. So conditional probability makes sense for dependent events only. This is a very, very important point. Conditional probability, it makes sense for dependent events only. Okay, this is where I have seen a lot of people making mistakes. Even some experts make mistakes, when they try to identify two events and they say that, okay, this is the dependent event, this is the independent event. No, whenever PA given B is written, it means both of them are dependent on each other unless and until this equation is holding true. Okay. Also tell me, if A and B are mutually exclusive events, what do you think the conditional probability will be? PA given B, according to you. If suppose A and B are mutually exclusive events, then very good. PA given B will be how much? It will be equal to 0. This is also something which we have derived, but you can understand it logically. Let's forget the mathematical definition right now. Mathematical definition is also quite easy. In fact, you just substitute P A intersection B as 0 in the numerator, you'll get 0, because for mutually exclusive events, the numerator itself is 0. But logically, also it's quite clear, right? If they are mutually exclusive events, then if B has already occurred, then it is guaranteed that A will not occur. So obviously, P A given B has to be equal to 0. If B has occurred, A can never occur. Okay. Now comes the important part, as I told you, visualization of conditional probability. Visualization is very, very important. It makes you understand how conditional probability actually should be interpreted. So let's say this is an example which I have taken. Now, just quickly pitch in fast. What is PA over here? I told you probabilities are demarcated region-wise.
16.
16%. Very good. What is PB?
60.
60%. Very good. 48 plus 12, 60. 4 plus 12, 16. So PA is this much, PB is this much. Okay. And PA intersection B is obviously 0.12 or 12%. Now, if you do the mathematical calculation, you can get it quite easily. You can get PA intersect A given B is equal to PA intersection B by PB, which is nothing but 20%. Now, how to visualize it? This is how we visualize it actually. So I'll explain. See, there are two universes over here. One is my original universe. So this sigma, ohm, or S, whatever you may call it, this entire sample space is my old universe. So initially, all possible outcomes of an experiment are considered. So this is your full sample space. Okay. Now what you have done, you have built a new universe. You let go of the rectangle. In fact, in this diagram, you ignore the rectangle. And that's why I have not written any sigma in this diagram. So this does not exist. Okay. Now your new universe is actually B. So everything is happening inside B. Because B is something which has already happened. B has already occurred. So this is your new universe. So when you condition on an event B, you actually restrict this universe to only those outcomes where this B has occurred. Okay. So this subset now of your original universe, because in the original universe, B is nothing but a subset of the original universe. So this subset of your original universe now becomes your new universe, and it becomes your new sample space. Okay. Is it clear? This B has now become your new sample space. So B is not just any subset. It is now the effective universe in which all the further probabilities based on the condition that this is your new universe or B has already occurred, all the future probabilities will now be updated and calculated. And finally, you are seeing that if I want to find out conditional probability, there is a dependence on intersection now. So now, since everything outside of B is ignored, so it means this red region is now gone. So this portion of A will not be considered. Only the portion of A which was common to B or inside B now will be considered. So the probability of observing A given B is dependent on A intersection B now. Okay, and now you can see that since your new universe, instead of this 100%, the new universe has become 60%. Okay, so if 60% is now your new universe, so that is why 12% has been scaled up to 20%. Because if 60%, this entire 48 plus 12, which is 60%, is now your 100%, this total is how much now? 80 plus 20. This now becomes your 100%. So out of this 100%, what is the space taken by the common region of A and B? 20%. So this is your conditional probability. Is the interpretation, visual interpretation, clear to everyone? That how in conditional probability your universe changes first. The new universe becomes this set B, right? And then based on this new set, the new universe, you actually find out what proportion of A is inside this new universe. So 20% of A is inside your new universe. Okay. Leaving everything outside of B. So this part of A is not considered now. This part is gone. Only the part which is inside B, how much percentage of that occupies B? That is your conditional probability. And it means that B has already occurred. B is your new universe. Okay. And again, these things we have done in great detail in the class. So this was the best possible way in which it could have been explained in a short way. Now, like probability, independence can be redefined to hold conditional on another event. So this is the algebra for conditionally independent events. So P A intersection B given C is equal to P A given C times P B given C. So this is quite similar. In fact, quite similar. I'll say identical almost. In fact, to this, this was the independence condition, normal independence condition. Okay. And this is the conditional independence condition. Okay, so this is the difference again. We have discussed an example in the live class and the self-paced course, but that is very, very detailed. The visualization has been discussed of conditional independence also, but I think from the exam point of view, this is sufficient for you because probably it might not be asked, the visualization part. If conditional probability visualization is clear, then you'll be able to visualize this also. Now let's come to joint probability. Joint probability for two events is the probability that both will occur together. This is the formula for joint probability PA intersection B or PAB is equal to PA given B times PB. PA given B times PB. And of course, if they were independent events, then this would be replaced by PA in that case, if they were independent events. If they are not independent events, then this is the general algebra for joint probability. Okay. Next. So let's discuss an example. The probability that the economy will undergo slowdown is 0.5, and the probability that the Fed will increase the interest rates is 0.6. The probability that the economy will undergo slowdown, given that the Fed will increase the interest rates, is 0.7. These probabilities you have to find out. First one, slowdown will happen and interest rates will be increased. So the first job always, when you see the question in the exam, should be to translate the literal language into mathematical notations. That's your half the battle is won there only. That is what I say to my candidates. If you are able to just transform them into the probability notations and in terms of probability, then your job becomes quite easy. So this part over here, if you see this part, economy will undergo slowdown is 0.5. This is nothing but PS. If we assume this is event S, slowdown is event S, so PS is given as 0.5. Let's assume that increase in interest rates, the event is I. So PI is given as 0.6. Okay. Now also one of the conditional probabilities is given. Can you tell me what is given? Is it PS given I or is it PI given S? What is given? What is provided in the question? PS given I or I given S? Quickly.
S given I.
Perfect. So it's provided that PS given I is 0.7. This is what is this information is provided to you. So first thing that you have to calculate is S intersection I. You can see that and is there. Slowdown will happen and interest rate will be increased. So we'll just use the joint probability algebra. PS intersection I is equal to PS given I times PI, which is 0.42. Next, you have to calculate I given S. So again, we'll simply use the conditional probability algebra. Pi given S is nothing but Pi intersection S divided by PS. And of course, it is quite clear that I intersection S and S intersection I, they are the same events, right? There's no difference. Whichever you write first, it doesn't make any difference. So the probability of I intersection S is also same as 0.42. Okay, so this becomes 0.84. Then you have to find out at least one of them will happen. At least one of them. Now, in the exam, they might not be very direct. find the probability of A union B. They might not ask like that, or find the probability of A or B. So it will be very obvious to you. In the exam, they might frame the question like this: at least one of the two events will happen. So try and understand what is the meaning of at least, either A or B or both. Either only A or only B or both. Okay, so at least one is nothing but they are actually talking about union over here. So this question has been framed to make you understand a lot of things that they can ask you in the exam in different terms also. Okay, and how they can extend the idea of conditional probability to include intersection events. Okay, you just have to calculate intersection. Then you have to calculate the opposite, and you may also have to calculate union part, which they'll frame in a different language. So at least one of them is also nothing but union. So this is quite simple now. It becomes 0.68. So see why we are skipping a very doing these things very quickly. These slides normally we take some time because you will have the PDF right to revise. So we will just do these things very quickly. And I said in the beginning only that I'm assuming that you have completed the course at least once. Now I said that MEE events, these are very special class of events. Any unconditional probability can be calculated from conditional probability if the events which have already occurred, they are mutually exclusive and exhaustive events. So this is the theorem of total probability. Again, a very beautiful visualization we have done for the theorem of total probability. But from the exam point of view, the special case is more important actually. Because you know that two events B and B bar, they will always be mutually exclusive and exhaustive events for sure. Guaranteed. B and B bar. You draw the diagram over here. Suppose you have B over here and B bar is outside of B. So this is your B bar. So can I say that B and B bar or B and B complement, they are mutually exclusive also and exhaustive also? Do you agree or not? A very important and subtle observation, but very important, as I said, from the point of view of the exam, because there is nothing common between them. B bar is outside of B. So they are mutually exclusive. They are exhaustive also, because when you combine them, when you combine the circle and the outside part, what do you get? Do you get the entire sample space? Yes. So B and B bar will always be mutually exclusive and exhaustive events. So this will be the algebra for mutually exclusive and exhaustive events. Now, this is one way to remember the theorem of total probability. Either you use the formula, okay, or you use the tree diagram, which is way too simple. And that is what we have recommended in the class also, although we have solved the question using both the methods. Today also we'll do that. We'll take an example and we'll solve them using both tree diagram as well as this formula. Okay. But I think it's important that you understand the formulas. Definitely in the exam, use the tree diagram without any doubt, but understand the logic behind the formulas. So this is an example. Out of a group of 1,000 patients being treated for chronic back pain trouble, 30% are chosen at random to receive a new experimental treatment as opposed to the more usual muscle relaxant based therapy, which the remaining patients receive. Preliminary studies suggest that the probability of a cure with the standard treatment is 20%. So 30% are receiving new treatment. And the probability of cure with the standard treatment is 0.2, 20%. But for the new treatment, the probability is 60%. So how many patients out of 100 patients selected at random would be cured? So the first thing I'll do for you, I'll just define the events in terms of alphabets, right? So let's assume that the event of getting new treatment is capital N. The event of getting the usual treatment is capital U. Do you agree that N and U are mutually exclusive as well as exhaustive? Yes or no? Because N is nothing but U bar. Those who receive the standard treatment, they don't receive the new treatment. Those who don't receive the new treatment, they receive the standard treatment. So at least either they will receive the new or the standard. So they are actually combining the sample space. So all the patients are included. 1,000 patients are included, either new or standard. So they are definitely exhausted. They are mutually exclusive also, because one patient cannot get both at the same time. Either the patient, he or she will get new, or he or she will get standard. Okay. Or usual. Standard, I mean usual treatment. Okay. So what is Pn? Tell me. Pn. If I only have to find out Pn, what is Pn from the question? Quickly. What is Pn from the question? Very good. 30%, in fact, it is given, so you can say that simply 0.3, right? 30% at random. Okay. What is Pu? What is Pu? Correct. 1 minus 30% or 1 minus 0.3, 100% minus 30%, whatever you want to call it, 70% or 0.7. Okay. Now tell me one thing. This statement over here, cure with the standard treatment. What kind of probability is this? Conditional or unconditional? Quickly. According to you, is this conditional or is it unconditional probability? Cure. Very good. It is conditional probability. So as I said, if you are able to transform this statement into a mathematical notation, the job becomes quite easy. So can I say that this statement implies PC give, and I have tried to color code it as much as possible. I mean, sometimes it might not be there, but mostly you'll find that if suppose this is a purple line, then the equation will also be in purple in most of the cases. So cure with the standard treatment is 0.2. So it means that given that the patient received the usual treatment, the patient got cured, the probability is 0.2. So do you agree that 0.2 is nothing but PC given you? Is this part clear to everyone? Okay. And just one quick note I want to give you. Again, everyone has a different way of understanding and perceiving things and remembering things, and they have their own tips and tricks, okay, for the exam. So for me, I always used to write conditional probability when I was preparing, and when I saw conditional probability for the first time in class 11, uh, then can you just mute your microphone, please, if you're not speaking? Thank you. So when I used to write conditional probability, I had this tendency, okay, I don't know whether it works for you or not, that I will write P and I will write the given event first. So I will write this first and then I'll write this. So this is my way of making things easier for myself. Again, if it works for you, then it's good. Otherwise, you can use your own way, right? Because it makes it yeah, okay, Dinesh, yeah. So actually, it makes my job easier. That's what I feel. So given, if it is given that the standard treatment is there, so I write P given, U is given, then after that the patient has been cured. So 0.2. Okay, now can you tell me from this line, cure from the new treatment, what can I write similarly? Cure from the new treatment is 0.6. Can I write this? PC given N is 0.6. Agreed? Okay, fine. Great. So then now it becomes quite easy. You have PC is equal to PC given you. Use the conditional probability formula and you'll get this as, in fact, you'll get this as 0.32. There's a typo over here. This will be 0.32. Okay. 320 is basically calculated after this number is multiplied with 1000 because there are 1000 patients. So to find out the number, you'll have 320 patients because the probability you will get as 0.32. So obviously, the total number of patients will be 32% of 1000. Okay. Now the same question, as I said, we'll solve using tree diagram only. No, actually, again, there's a typo. Sorry, Divesh, there's a typo. Actually, this you can see, this is 1000, right? Over here. And by mistake, instead of 100, 1000, they have by mistake, it's a typo. It's a little bit 1000, okay? This is a typo. Got it? So 1000 patients are being treated and the final answer has to also be calculated for 1000. Okay, this is a typo. So is the formula application clear? How to transform the statements into notations? Is this clear? Okay. And then the formula application. Fine. And when we solve this using the tree diagram, I think almost all of you will agree that tree diagram is simpler. But as I say, you should always try and understand the application of the formula first and then go for the tree diagram. So first we'll see what is Bayes' theorem and then we'll come back to that same question later on. So this is what Bayes' theorem is. And again, the derivation we have done in the video, it is quite simple, but over here we'll just focus on the statement of the Bayes' theorem. For two random variables, PA given B is equal to PB given A multiplied by PA divided by PB. So over here, the conditional probability you have to calculate conditioned on B. And the input that you use is the conditional probability conditioned on A. So you reverse this, okay, and then you multiply it with PA and divide it with PB. Again, this is the formula which many of you might remember using different tricks. Either you can remember it by multiplying PB to the left-hand side and by seeing that both of them are finally same, PA intersection B. That is what the derivation we have done in our video. Or else you can remember it in a very a different manner. You can see that B is given over here. So just remember in your mind that since B is given over here, so let's place B in the denominator on the right hand side. And this will be reversed. Okay, PB given A will be reversed. And then it will be multiplied with P. But of course, if you remember the visual derivation and the proper derivation, then even this will not be required. Okay, this trick will not be required. Again, your choice completely. So what is Bayes' theorem? Bayes' theorem is a plan to change our beliefs in the face of new evidence. So till now, whatever evidence you had, you calculated some probabilities. Now, based on new evidence, you are updating your probabilities, and that is what Bayes' theorem does for you. And it is, although a very, very simple formula, but it is used heavily in the fields of finance and risk management. One thing which you need to note is that this denominator has to be calculated using the theorem of total probability. That is where total probability comes into picture in Bayes' theorem. This denominator, remember, it has to be calculated using the theorem of total probability, PB. Whether you use the formula or the tree diagram is your choice, but it has to be the theorem of total probability only. Okay. So let's go for the same example. Let's go for the same example. So the complete statements, all of them are same, but there is some new evidence. This last line presents the new evidence. Sometime later, one of the patients returns to thank the staff for her complete recovery. This is your new evidence, and now you have to find out, based on this new evidence, that what is the probability that she was given the new treatment. Now, PC has already been calculated in the previous exam. PC, the probability of being cured, has already been calculated. This is the unconditional probability based on both the treatments. Okay. It was 32%. The probability of being cured is 32%, already calculated. Can you tell me what you have to calculate in this case? Which conditional probability you have to calculate? What is given to you now? Tell me. What is given to you? This last line will tell you what is given to you.
No treatment.
Yes, the patient has already been cured. Very good. Very good. The patient has already been cured. Okay. So given that the patient has been cured, what is the probability that the patient was given the new treatment? So do you have to calculate this now? Pn given C, yes or no? Okay, great. C given N was, no, Pooja, C given N we don't have to calculate. Okay, Pooja, we have to calculate N given C because C is given. See, sometime later, one of the patients returns to thank the staff for her complete recovery, Pooja. Okay. So the patient, she goes and she thanks the staff for her complete recovery. It means the patient has been cured. Agreed, Pooja? Okay. So given that she has been cured, what is the probability that she was given the new treatment? Pn given C. And that is why I say once you are able to formulate the notations, once you are able to understand clearly what you have to calculate, then your job is more than 50% done. Then you just have to apply the formula or use the concept or the diagram. Finished. So PC given N, it was already provided in the question. What is the information with respect to PC given in the question? I'll not go back to the previous slide. I want you guys again to look at the example and tell me what is PC given N. What is PC given N?
0.6.
0.6. Very good. This is exactly what we did earlier also. PC given n is 0.6 from n. Cure from the new treatment is 0.6. Okay. And we know that Pn was 0.3. That is also given. 30% were chosen at random. Okay. So this is how we calculate. So given that the patient was cured, the probability that she was given the new treatment is 56.25%. Now let us solve the same question using tree diagram. So how to start? See, although tree diagram seems quite simple and most of you are already comfortable with tree diagram, but still, how do you start with the branch of the tree, the first branch of the tree? Do you start with cure or not cure, or do you start with new treatment and usual treatment? Tell me, because there are two options. Either you can start with cure, not cure. Those can be your first, two segments of the tree, the first branch. Or you can start with new treatment, usual treatment. So in that case, how do you decide? Because see, when you solve these questions, it becomes quite obvious to you. You don't think about these things in detail. What if I had done the opposite? What would have happened? You would never have been able to solve the question if the start was wrong. So in the beginning, you always start with the information that is provided in the first place. So chronological order, what is happening? See, first the patients are being given. Cure is what? Cure is an outcome. Do you agree or not? Cure is an outcome of the treatments. Yes or no? So first you will plot the outcomes in the tree, or first you will plot the correct sequence. First you will plot what is happening. Okay, what kind of treatment is being given? So treatment first or outcome first? Tell me. Treatment first or outcome first in the tree? Very good. Treatment first. Okay. So new treatment, usual treatment. Okay. Again, there is a typo. There is a small typo. What was the probability of new treatment? 0.3, correct? So 0.3, 0.7. Now, under the new treatment also, what was the probability of getting cured given the patient was having new treatment? Tell me. Let's go back. If the patient is having new treatment, what was the probability of getting cured? Perfect, 60%. So let's go to the tree now. This is under n. We will have now two more branches. Cure or not cure? 60% probability of being cured, 40% probability of being not cured. Similarly, can you tell me under usual, we'll have again cure and not cure. What was the probability of cure under usual? What was the probability of cure under usual? Perfect, 20%. So if 20% is the probability of getting cured, it means 80% is the probability of not getting cured in usual. Is the tree clear? Is the tree clear to everyone? Is there any doubt? You can ask immediately, because this is the critical part, I believe. Okay, fine. So now there are two options. See, what is the event now which has happened? Finally, yes, Rohit, I'm repeating. So I said that you start with the treatment first. You don't start with the outcome. So there are two possible treatments. There are two possible treatments. New treatment or usual treatment. 30%, 70%. Clear? First part is clear, Rohit? Then under new treatment, there are two possibilities. If you get the new treatment, either the patient can be cured with a 60% probability, or the patient will not be cured with a 40% probability. Similarly, for usual treatment, the patient will be cured with a 20% probability, the patient will not be cured with a 80% probability. That is the tree. Is the tree clear? Rohit, now? Okay, great. Now it is given that the patient comes and thanks for her recovery. So it means that the patient has been cured. So we have to reach cured now. We have to reach C. Starting from the top, we have to reach C. How many routes are there? How many possible pathways you can see from top if you have to reach C? There are two C's. So there are two paths, right? One is this path. Do you agree? This is one path to reach cure. Agreed or not? Okay. So you simply multiply the probabilities, 0.7 times 0.2. So the probability of reaching cure through this path is 0.14, 14%. There's another path, right? This is the other path. Okay? The probability of reaching cure through this path is 18%. Okay? So what is the total probability of being cured? Simply 18 plus 14, which is 32%. And that is how you visualize this formula. So the first part was actually the reaching cure from one of the paths, reaching cure from the other path. This is actually the formula also. The formula and the tree, they are conveying the same thing in slightly different ways. That's it. Okay, so is it clear? How do you calculate the probability of a cure through tree diagram? So which one will you use in the exam, tree or formula? What will be formula? That's great. Okay, very good. Okay, so do whatever you want. Okay, Rohit, fine. Rohit has drawn a very nice tree. So yeah, okay, great. So then the next part is the same. Then you just apply the Bayes theorem formula and you get 56.25. Okay, fine. So that is it for the first chapter. Let's go to the second chapter and we'll just take a 5-minute break over here. Only for 5 minutes. Okay. So we'll have 4 breaks in total today. There will be short breaks between chapters, 5 minutes, and then there will be 15-minute break after we complete every 3 chapters. After every 3 chapters, there will be 15 minutes. So right now we'll just take a 5-minute break. So please be back in 5 minutes. We'll start at 12:16 p.m. IST. Thank you. 12 chapters puja will be covered today. Okay. Please be back in 5 minutes. And those who will be watching the recordings of this video, they can just fast forward it. You can skip the next 5 minutes, the break part. They can check when the audio resumes. Because I'll not pause the recording. I don't want to miss resuming the recording or any problem I don't want to have. So I'll not pause the recording. Please be back by 12:16 p.m. IST. Thank you. Okay, let's resume. Yes, Satish is asking, can we get access? Yes, definitely. As I mentioned, that recordings will be made available to all of you. In the LMS only, it will be there, and probably if required, we can also put it on YouTube. We'll see about that, and you'll get access to recordings definitely. Okay, and most probably this will be put on YouTube as well. Okay, let's continue with random variables. Now, random variables are random phenomena that can be described using numeric values. So examples, of course, we can have a return on a portfolio of stocks, let's say, or default on a corporate bond. Now, the set of values that a random variable may take is called a support of the function. Yes, Munmun, as I mentioned at the beginning only, that the PDF or version of all these slides that we are giving you right now, the PDF version of these slides will be shared by the LMS directly. Okay. And if the video is put up on YouTube, then probably we might also have a link so that you can download it directly from the website as well. Okay, fine. So what are the types? There are univariate random variables. You can have bivariate random variables. Okay, and you can have multivariate random variables. We'll discuss about these in detail. Then univariate, they are of two types. We can have discrete and we can have continuous random variables. Remember that the key properties of discrete and continuous random variables are identical. And again, I'm repeating, see, these things when we discuss in the videos, we discuss in great detail, discrete, continuous, the introduction part also. Countably, infinitely many, what is the distinction between discrete and continuous? Discrete does not mean that only finite number of outcomes will be there. It can be countably infinitely many also. All these things are there. But because of lack of time, it is just not possible to discuss everything in the crash course. But the good news, again, as I said, that since you'll get the PDFs and the recordings, the good news is that the structure that has been prepared, when you go through the PDFs, the details that we have omitted, you know, you can be almost 90% sure that they are not going to be asked in the exam. Okay, those are for detailed explanations for understanding purpose. So that is why we have omitted those stuff. So there's no need to worry that you are going to miss something which is very, very important. Now, PMF, probability mass function. Yes, Linio is mentioned that please slow down a little bit. I think you are going too fast. See, I totally get your point, Linio, that I'm going too fast. And see, the problem is that we have to cover 15 chapters are there in quants. Out of that, we have to cover 12. Now, we have covered one till now. Okay, we started at 11 and it's been 12:19. So you can understand if we try to cover the chapters even more slowly, then it will take, say, 10 to 12 hours of a session. So are you ready to sit with me for 12 hours? If yes, then probably I'll think about slowing down a little bit. Are you ready? Tell me. I'm completely okay. Say, because if you're not, say, I'm giving you one more thing. If suppose there are a few points which you are not able to understand, let's say, when I'm going quickly, then you always have the PDF and the lecture notes for revision. Got it? So go through that part. So I'll see all of the other candidates, they are mentioning speed is fine and everyone is mentioning because it's a crash course, right? Crash course means speed has to be there. So go through the recordings and the PDFs quickly. Fine. And apologies for any inconvenience caused. So, but this is what we are trying our best. And if there's any problem, just let us know later after the class. Maybe we can have some extra doubt solving session also, which we'll have for our candidates. If possible, we'll see if we can include you in that also. So two functions are used to describe the properties of discrete random variables distribution. They are PMF, which is denoted by small fx, and CDF, which is denoted by capital Fx. Now, PMF is the probability that a random variable takes a certain value. There are two properties of PMF, just like probability. Fx is greater than 0. The only difference is that now you are talking about functions, probability functions, instead of core probabilities. So everything will be in functional notations. Fx is greater than 0 and summation Fx equal to 1. This is just like the property of probability where the probability of all outcomes has to be equal to 1, right? What is CDF? CDF is the sum of the PMF for all values in the support that are less than or equal to x. Less than or equal to x. Okay. So starting from the minimum point up to that particular point, if you want to find out the probability, that is the CDF. So this is how CDF is calculated. Summation fxi, where xi is less than or equal to x. Again, notations are not very important from the point of view of the exam. Concepts are important. So remember this point. You sum all the probabilities less than or equal to a particular point. Conversely, you can also calculate PMF. Now, this is a very important point, and this is quite analogous to the concept of, you can say, summation and differentials. Okay. No, CDF is not the sample space. No. CDF is not the sample space. CDF is the probability. And in fact, when we'll see examples later on, it will be quite clear to you. This is just the definition. CDF is the probability that the probability of observing a value x which is less than or equal to a particular value. That's it. So for example, let's say in this classroom, there are say 50 students right now. Okay. And I take a surprise test and you get some random marks out of 100. And if I ask that, what is the probability of getting, taking randomly selecting a student who has got marks less than or equal to 70? Understood? So less than or equal to a particular value starting from the minimum, if you want to find out the probability, that is given by the cumulative distribution function CDF. Now, conversely, PMF is the difference of the CDFs for consecutive values in the support of x. Remember that. So if you actually do capital Fxi minus capital Fxi minus 1 consecutive values, if you subtract the CDF values for consecutive values of x in the support of x, of course, you get the PMF for that. A very, very important point. Okay, this is, as I was saying, this is analogous to something that differentiation is the inverse of integration and inverse is the integration is the inverse of differentiation, something like that. But of course, it is not in the course. So we'll not discuss in detail, but this part, the conceptual understanding is important. Okay. So when you sum all the PMFs, you get CDF. When you take a difference of the CDFs, you get PMF. Obviously, this is the inverse of the above statement. Okay. Now, what is the expected value? Expected value of any random variable is equal to summation of pi xi, which is p1 x1 plus p2 x2 plus up to pn xi. Now, expectation function of any random variable is similarly, see, either you can find out the expected value of x or you can find out the expected value of a function of x. Logic is same. Over there, you do summation pi xi. Over here, you'll do summation pi f of xi. So if suppose you have this example, suppose fx is equal to x square, then to find out the expected value of x square or fx, which is x square, you will simply do pi xi square. That's it, nothing else. Okay, so pi xi square will be your expected value of fx. Now, these are the properties of expectation. It's a linear operator. So expected value of any constant is the constant itself. Expected value of expected value is the expected value. An expected value of a random variable is always a constant. So expected value always gives you a constant, whether it is of a constant or a variable. So inside the expectations operator, you might have a constant or a variable, but on the right-hand side, you will always have a constant. And these things, they are testing a lot, in the past few years. Lot theoretical concept, theoretical ideas. They're testing a lot in the exam. Now, for nonlinear function, e of gx is not equal to g of ex. So, for example, expected value of 1 over x is not the same as 1 over expected value of x, because 1 over x is not a linear function. If you draw the graph of 1 over x, you can clearly check that in the first quadrant, you get something like this, and over here, you get something like this. So this is not a linear graph, right? So if the graph is not linear, then this property will not hold. Expected value of gx, like 1 over x, is not equal to 1 over expected value of ex. Okay. Now, in the video, in the live classes, we had a lot of examples, numerical examples also, a few examples to cover these things. But properties are important, so we'll just discuss the properties in the crash course. expected value of Cx is equal to C times expected value of X. So C comes out, okay? Expected value of X plus Y is equal to expected value of X plus expected value of Y. Expected value of Cx plus A, again, C comes out of the bracket and we know that expected value of A is nothing but A. Expected value of xy, if x and y are independent random variables, it is equal to ex times ey. This is just like probability for independent events. Probability, the joint probability was nothing but PA times PV, right? So expectations operator also behaves something like that. And of course, if the events are not independent and the random variables x and y are not independent, over there we were talking about events, over here we are talking about random variables. So if they are not independent, then of course this equation will not be true. So it will not be equal to ex times ey. Also remember that if you want to find out expected value of x square, you do not just square the expected value of x. This will not work out. You actually have to do this. You have to do summation of pi xi square. This is how you find out expected value of x square. Okay, you just don't square this because this is different. This is summation pi xi. If you square this, you'll get a different number. This will give you a different number. Okay, so they are not the same. Expected value of x square is not equal to expected value x whole square. Now, what is a moment? Moment is the expected value of a function of a random variable. So there are four common moments. We have mean, variance, skewness, and kurtosis. Mean is the first moment and is denoted as mu is equal to ex. It is also the average value and it is also referred to as the location of the distribution. Then you have variance. Variance is the second moment. It is denoted by sigma square. Now this is the formula. This is the formula of variance. So variance is measuring the dispersion around ex. That is why you can see. And again, the difference between central and non-central moment, we are not going to discuss in the crash course. That is not very important, okay, from the exam perspective. So we are talking about central moments right now. So you see over here, there are two formulas actually. This is the first version of the formula. So actually you take all the x's, you subtract the mean, okay, and you take the square and you find out the expected value of that. And in some cases, you simply sum those xi minus ex values, whole square values, because the probabilities for all the outcomes are same. Now, one mistake which the candidates do in the exam all the time, many a times in fact, is that whenever these kind of questions are given, they forget to pay attention to individual probabilities. Remember that. That is why I have not just divided it by n. You will divide it by n only when the probabilities are same. They are equally weighted. Something like that is given or no information is given. If probabilities are given explicitly, then you have to take a probability weighted average to find out the expected value. Then there is another version of the formula. This version. Sigma square is equal to ex square minus ex whole square, in fact. Okay, so this is actually ex whole square. This is a better way to write. From the exam point of view, let's say 3 or 4 data points are given to you. You should prefer this formula. This will be easier for calculation. And I hope everyone knows how to calculate these values using the BA2 plus calculator, because once you use the BA2 plus calculator, all these values become quite easy. So I'll just give you a quick heads up. There are two buttons in your BA2 plus calculator. One is data and one is stat. One is above, I think 7, the other is above 8 if I'm not wrong, correct? So if you have not learned the use of these buttons, do it today itself, because these buttons will help you calculate everything, right from mean, variance, standard deviation, sample standard deviation, population standard deviation, to even correlation, R square, and everything. Okay, so learn data and stat button today itself. That is very important from the exam point of view. Then square root of variance is denoted by sigma. It is known as the standard deviation. It is the measure of volatility of a random variable. So sigma square, the variance, is the measure of dispersion, how much spread the random variable is about its mean. Now, one point which I want to highlight over here is this. Because there is a mistake. Again, many books, third-party books, or even not FRM related only, FRM related, non-FRM related books, they tend to make this mistake that when they give the value for variance, they give the value for variance in percentage. That is wrong. Because if you are having expressing sigma in percentage, see, percentage is not a unit, I say. Okay, for convenience, you can call it as a unit, just for convenience, for understanding purpose. But it is not a unit, it's a way of expressing. You can either express in decimals or percentage. But you have to be very careful that standard deviation is in the same units as the original data. So if suppose you're talking about returns and returns are given in percentage, then standard deviation will also be represented in percentage. But can variance also be represented in percentage for that data? If I am already saying that variance is the square of standard deviation, should I also express variance in percentage? What do you think? Is it correct? No. So variance should always be expressed in percentage square. Okay, so this is one mistake which you should not make. And the square root of percentage square is percentage. So everything becomes consistent. Okay, if you are able to follow these conventions properly. Now let's talk about skewness. Skewness is the standardized third central moment. Now, when we say standardized, you might have noticed one thing over here. See, when I calculated variance, did I divide by sigma square or any measure, any squared of something? No. I did not divide it by ex square or mu square or any square, right? It is simply the spread about the mean. That's it. But skewness, when I define, skewness is actually not the third central moment. It is the standardized third central moment. Here also I have seen some candidates making this mistake. They'll say, okay, first moment is mean, second central moment is variance, third central moment is skewness, fourth central moment is kurtosis. No, you are right up to point 2. You are right up to variance, but you are wrong after skewness. Once you start with skewness, you are standardizing it by dividing it by sigma q. Okay, so it is the standardized third central moment. Okay, but if you are asked, what is the third central moment? So third central moment is simply this. That's it. Got it? This is your third central moment. Once you divide it by sigma cube, you get the skewness. Okay, because it is easy to deal with in terms of calculation. And there are some other reasons also, some statistical properties also, which we'll not discuss. So you can see that you can have positive skewness, you can have symmetrical no skew, or you can have negative skew. Over here in the second diagram, they are overlapped over each other. And the first one, it shows a longer right tail. So if the distribution is positively skewed, you will have a longer right tail. If the distribution is negatively skewed, you will have a longer left tail. Okay. Next, let's come to kurtosis, whatever you want to call it. So kurtosis is the standardized fourth moment. Again, it will be central, the standardized fourth central moment. Because why I'm saying central? Because we are subtracting ex all the time. So it is about the center. If suppose I take directly ex to the power 4, it is non-central moment. When you are subtracting ex all the time, you are taking central moments. Okay. Then you divide it by sigma to the power 4, you get standardized fourth moment, standardized fourth central moment. This is kurtosis. Now remember, and of course, distributions part we'll deal with later on. Okay, what is a normal distribution and all. Remember that kurtosis for a normal distribution, there is something called as a normal distribution, which is a very important distribution, is equal to 3. Similarly, for skewness also, for a normal distribution, there is no skewness. It is not skewed. Skewness is 0. So for a normal distribution, the kurtosis is 3. And excess kurtosis, we define it like this, k minus 3. So it means for a normal distribution, there is no excess kurtosis. We standardize it, actually we standardize it by subtracting it with 3. Okay. Financial return distributions are usually heavy-tailed. So they have a lot of kurtosis. So kurtosis is basically just like skewness was a measure of the degree of asymmetry, how much asymmetric your distribution is. Kurtosis is a measure of how much thick the tails of your distribution are, how many large deviations you have from the mean. That is how kurtosis, actually that is how kurtosis should be interpreted. Got it? Okay, now this diagram, which again you will see a lot of mistakes in almost, I'll say more than 80% of the figures that you will find everywhere, FRM or non-FRM related book. First, we'll discuss the theory part. So for there are three kinds of distributions. There are leptokurtic distributions. For them, k is greater than 3 and excess kurtosis is greater than 0. This is more peaked than the normal distribution and it is heavier tailed. So leptokurtic distributions, they are more peaked and heavier tailed. Platykurtic distributions, they are having k less than 3, so ek will be less than 0. So they are less peaked and lighter tailed. Mesokurtic distributions, they are exactly having the kurtosis of 3 and excess kurtosis of 0. Now the diagram which I'm talking about, which you'll find there is a lot of mistakes, this is the correct version of the diagram. See, it is very, very important to point out that in this diagram, in the central region and tails, in the central region, so this central region and the tail region, can you tell me which distribution is having the highest probability density? Quickly. Very good, lepto. And which is having the minimum? Minimum. Platy, correct. See, platy is minimum over here also. Platy is minimum over here also. So in the tails, you can see these two paths. See the tails. This is the lowest, correct? And this is platy. That is why I say, see, this concept will only be clear if you look at the correct diagram. And most of the diagrams, the tail part, they completely ignore. That which one is lowest and which one is highest. You can search on the internet also. You'll see, you'll get a lot of wrong diagrams. Platykurtic is lower both in the tails as well as center. So in the center as well as tails, lepto is greater than meso is greater than platy in terms of probability density function values. Got it? Is the diagram clear? To everyone, because this is heavily tested in the exam. When they talk about kurtosis, this is one of their favorite questions. Okay, so central and tail, both the regions, lepto greater than meso, greater than platy. But what about intermediate region? What about the intermediate region? Which one is highest? This is the intermediate region. So in fact, I should do one thing. I should do proper color coding. Central and tails we have given in purple. Na? So let me just use purple for central and tail. Okay, and let me use another color for intermediate. Platy, very good. So in intermediate region, red one. So this is red, intermediate. Okay, but maroon, not red, maroon region. Okay. Platy is greater than, meso is greater than lepto. This distinction should be very, very clear. Okay, so is it clear to everyone? Any doubt? Okay, great. Let's move forward. Now, what will happen if you change the moments? So let's start with the first one. What will happen if you change the mean only? If you change the mean, it means that you are just changing the location of the distribution. So this is the original distribution. Change the mean from 5 to 6. Nothing changes. No shape of the distribution changes. The shape is completely conserved. The distribution just shifts right by 1 unit to have a new mean of 6. That is the location shift when you change the mean. What will happen if you change the standard deviation only? So in this case, the mean is same. You can see that mu is equal to 5 in the old distribution also, mu is equal to 5 in the new distribution also. This is the old distribution, but you have actually increased the standard deviation. So what will happen? The distribution will become more dispersed about its mean. It will become more spread out. You can see green one is more spread out, light green one, right? As compared to the brown one. Okay. Then if you change the skewness from 0 to negative, sorry, there's a typo. Negative. So if you change the skewness from 0 to negative, what will happen? The tail will get pulled to the left side. This tail, left tail will get pulled to the left. It will have a more elongated tail. Okay, more outliers on the left hand side. Got it? And if you change the kurtosis, let's say the original kurtosis was 3. If you increase the kurtosis, then it will become heavier in the center as well as in the tails. And it will become lighter in the intermediate region. Now, this actually gives us a very interesting interpretation of kurtosis. So let's go back to this diagram again. Okay, I'm just removing all the annotations once again. So let's just go into this diagram. Now just look at the mesocortic distribution. Remember, mesocortic distribution is like the normal distribution. Normal distribution is the mesocortic distribution, okay? So let's look at the mesocortic distribution, this one. So if suppose I have the mesocortic distribution, can I say that to construct leptocortic from mesocortic, I can in fact show in this diagram also, and then I go back to that diagram because platy is also there, so you might get confused. Over here, we have only two lepto and meso. So to construct lepto from meso, can I say that I squeezed something from the intermediate region? I deleted this. I squeezed it. I took some portions out and I filled that portion in the center region and in the tail region. Do you agree? Can this be a valid visual interpretation of leptocortic construction from mesocortic? Everyone should be active. As many responses as possible. Okay. Similarly, can I say that for platy, I'm doing the opposite? For platy, actually, I'm doing the opposite. I'm taking out portions from the center and from the tail. So the tails are thinner, center is shorter, and I'm squeezing those portions in the intermediate region for platy. So that platy becomes thicker in the intermediate region and loses some weight in the tail and in the center. Do you agree? For platy? Okay. So this is how you can interpret it visually, right? Okay, now how to standardize random variables? Now standardizing random variables, what you can do, you subtract the mean from the value. If x has mean mu and variance of sigma square, you can construct a standardized version by subtracting the mean and dividing it by the standardized version. Now this variable has a mean of 0. This variable has a mean of 0 and unit variance. And we have derived this in the video. Not using the normal distribution. We have not, remember, although this is something which is very close to what we are going to study in the standard normal distribution, but till now we have not introduced it. Okay, till now we have just introduced it for the purpose of lepto and kurtosis and skewness. That's it. The mathematical part we have not discussed. So if you remember, this is also something called as the Z value, which we'll discuss later, right? But right now, we are just discussing if you have to standardize a random variable, subtract the mean, divided by sigma, and it is guaranteed that this standardized variable has a mean of 0 and a variance of 1. This is something which we have derived mathematically in the class. Okay, now what about transformations? This question was also asked not only in November 2023, but also in May 2000. Last year, 2 times I have heard feedbacks from our candidates that transformations were asked in the exam. So if suppose x is a random variable with mean of mu and variance of sigma square, Then you transform this. This y is equal to a plus bx is a linear transformation of x. So what will happen to the moments if you transform the variable? Will the moments also be transformed in the same way? Let's see. So this is x and this is y. For x, we know the parameters. I'm repeating again. For x, we know the parameters, mu and sigma square. For y, we don't know the moment parameters. We are about to find out. Let us see what will happen. The first moment will be transformed exactly in the same way. A plus bx is the transformation of y. So mu will also become a plus b mu. And everything can be derived. You just apply ey. I'm just doing the first one for your convenience, and the remaining, since we have derived in the videos, I'm not going to do it. And it's not important also from the point of view. So basically, we are just doing this. Ey is equal to e of a plus bx. Okay. Is equal to ea, which is a, plus b is, if you remember, it was a constant, it will come out. So it becomes b mu. B mu y, because ex is mu. Okay. So this, if we do for everyone, all the moments. So just a quick recollect. Can you tell me what will be the second moment? What will be the second moment of y? Let's say I'm talking about variance. What will be the variance of y? Tell me. Those who remember. Yes, yes. How to pronounce it? Is
B
J silent in your
square
name?
sigma x square.
Yes, very good, very good. B square sigma square. Don't say x square. B square sigma square. Okay. And the standard deviation is square root of b square sigma square, which is mod b times sigma. So a is gone. So it means that there was no relevance of the location shift. There was no relevance of the location shift when we are talking about variance. Again, the properties of variance are being used. Everything can be derived. Just a quick recap. Why I added a mod in front of b when I took square root of b square? I should have simply written b, right? Why mod b? Why mod b? Why mod b? Anyone would like to answer? Yes, Chitana, you are right. That is why Platykurtik was having the highest intermediate region. Correct. In the last case. So why mod b? Why not simply b? Exactly. See, the problem is that square root of b square. Let's say if b is, say, negative 3. Okay. And if I do negative 3 square root. Okay. If I write it, I mean, of course, it will be a square root of 9, which will be 3. But many of you might say, why not minus 3? Because it was minus 3 square. Why not minus 3? Because standard deviation cannot be negative. That is the problem. So even if the transformation, the initial transformation contains b as a negative number, remember, standard deviation cannot be negative. Absolutely. So we have to write mod b. And if you remember functions property from class 11, actually even in functions, square root of x square is actually mod x only. That is a different story altogether. We'll not discuss that because the negative part is ignored. Otherwise, it will not be a function. There was a problem with one too many and one too many. So one too many problem will happen. It will not be a function. Anyways, that is not a part of the course. So we just have mod b sigma. What about third moment? Anyone who can recall? What about third moment? So for third moment, skewness of y will be equal to skewness of x if b is positive. So there is again no effect on of a. A only had an effect on the first moment. There was no effect on the second and third moment. Okay. If b is greater than 0, then there is no difference in the skewness. Skewness is same. If b is less than 0, the skewness becomes opposite. Magnitude is same in both cases. So only the sign changes. So you can see that the effect of the parameters a and b are actually decreasing once you go towards the second moment, then the third moment, then the fourth. In fact, in the fourth moment, it will be completely unaffected. So this slide is very important from the exam point of view. Very conceptual slide. Okay, what happens to the first moment? First moment gets completely transformed in the same fashion. Second moment, only the scale parameter is important. Only D is important. Remember, A is known as the location parameter, B is known as the scale parameter. So for second moment, only scale parameter is important. For third moment, only sign of the scale parameter is important, positive or negative. For fourth moment, nothing is important. So linear transformation does not affect kurtosis. Okay. Now let us come to continuous random variable. Continuous random variable is a random variable which is having a continuous support. So for example, if suppose I say all like the example of S&P 500 returns we discussed, negative 100% to infinity, continuous. Let's say all real numbers between 1 and 9, continuous. Okay. Now probability of any single value for a continuous random variable is always 0. Can anyone tell me why? This is also extremely, extremely important. And this will be one of the hallmarks of a continuous random variable over which we will try to differentiate between PMF and PDF. Can you tell me why? Very good. So can you just send this message to everyone, Sushant? No, don't say X is very small. So those who have attended our classes, they are answering correctly. Yes, very good. Because the denominator is infinite. See, what did I say? The support is continuous, right, over here. So if I say all the numbers between 1 and 9, can you tell me how many numbers are there between 1 and 9? How many real numbers are there between 1 and 9? How do you calculate probability? This was the formula, right, of calculating probability. Probability of any event is equal to NE over NS. How many numbers are there between 1 and 9? Real numbers, not integers, real numbers. For a continuous support, infinite real numbers, because there are infinite real numbers between any two real numbers. Is it clear to everyone that there are infinite real numbers? Okay. So if there are infinite real numbers, and if I ask you what is the probability of say 2.5, so 2.5 is only one outcome. So any will be one, denominator will be infinity. So it will always be the case of finite over infinite. So if the denominator is infinity, this will tend to how much? If you divide anything by infinity, what do you get? Theoretically, tends to 0. So is it clear why probability of any single outcome, any single value in case of a continuous random variable is always 0? Is it clear to everyone? Is it clear to everyone? Great. Okay, fine. So the CDF is again similarly defined like this. And the interpretation of the PDF is something like this. Suppose this is the PDF curve. Now, if you want to find out the area under the curve, this from x1 to x2, this will give you the probability that x1 is between, sorry, x is between x1 to x2. And how do you find out the area? You perform integration, which is not a part of the course. So you don't need to worry about this part. You just need to understand what this part is conveying. It is conveying that the probability of observing a value x between x1 and x2 is equal to this area under the PDF curve between x1 and x2. Is the interpretation clear? Formula is not important. Is the interpretation clear? How will you calculate probability? To everyone? Okay, those who are sending direct messages, please, it is better if you send it to everyone. It will be better. Is the interpretation clear to everyone? Okay, great. Okay, Pooja, I'll explain again. See, if suppose this is the PDF curve, okay, and PDF curve is a continuous curve. It is a continuous random variable. PDF curve is a continuous curve. If I want to find out the probability, Pooja, that x lies between x1 and x2. So what is the probability that x lies between x1 and x2? It is given by this area under the PDF function between x1 and x2. That is what I'm trying to say. Okay, so under the PDF, you find out this area between x1 and x2. This will give you the probability that x is between x1 and x2. Got it? This area. That is how I'm saying it. And this is the method to calculate it, which is not in the course. Now, Divesh is saying that we don't have integration, gives me nightmares, which I used to have during my 12th standard. Fine. So definitely it's good news, but I'll say that, you try and revisit those concepts. It might be possible that, I mean, this is for everyone, not only for Divesh. It might be possible that things might, which were seeming difficult that time, with proper guidance, with proper practice, you might be able to, because see, I say this all the time to many of my candidates that right now, the stage at which you are in your career, it's not only about your professional life, right? It's about your personal life also. I mean, many of you are freshers, but most of you are working professionals, if I'm not wrong, most of you. And you have a family, you'll be having kids, you have to teach them math, right? So I think it's always better. I mean, take some time out, try to revisit those concepts. What is the harm? If you're not able to understand, still it's okay. But there's no harm. If you're able to recall some things, it is definitely a good thing for teaching your kids. Because a good mathematical background, the kind of evolution that we are seeing right now in the job market, no. We will not have integration. 100% sure. In the exam, we will not have integration. Okay, so I was saying the kind of changes that we are seeing with the advent of AI, and we are hearing a lot of discussions, right? There have been a lot of debates on both sides. What will happen to jobs and all those things? But anyways, that is a different debate. But in any case, I think in today's world, developing a mathematical perspective to everything as much as possible is very, very important. You should definitely try and excel in other things as well. And I'm not saying it's the only thing. People might be very good in finance, not very good in math. Even that is okay. But I think you should still take a chance, because if you, let's say, want to learn data science, many of you who are from commerce backgrounds, arts background, say even engineering backgrounds, but did not study engineering properly, did not prepare for JE properly, switched to commerce background again. There are many of you who actually started with science, but then they left and they pursued a career in finance. Or it is also possible that you are very good with science, you're very good with math, but because of lack of practice, it's been so much time that you are completely out of touch and things seem out of way. But you will definitely admit that if you have tried your hands learning, say, Python, say, machine learning, or other tools of data science, RStudio, mathematical tools are very important. Agreed or not? In the beginning, probabilistic and mathematical tools are always taught, correct? So it is always a good idea to try and revisit those concepts. You can always take the class 11, 12, grade 11, 12 books. You can try and have a revisit of those concepts. It will definitely help you. Okay. But the good news, as I said, from the exam point of view, none of these integration concepts are going to be directly tested. Only the visual interpretation is important. Now, as I said, that this part is extremely important, and this is how I'm going to base the difference. This is something which is heavily overlooked, I'll say. Heavily overlooked in the FRM curriculum as well as some other literature also. But I think differentiating between PMF and PDF is something which we should do at all levels, wherever possible. So PMF is only applicable, probability mass function, for discrete random variables. PDF is applicable for continuous random variables. For PMF, the probabilities are grouped into point masses. So for particular values, the probabilities are calculated and grouped. And the probability for PDF is spread over an area. The third point, I believe, is the most important point which you should understand. And this is where even FRM, CFA past candidates having a lot of experience in the industry, 90% of the candidates will give an incorrect answer. PDF does not give you probability, whereas PMF gives you probability. It means that the value of the PMF at any particular point X gives the probability that X takes that particular value. Whereas PDF for any particular value has no meaning. Now you will counter question me over here that right now I said that probability of any single value is equal to 0. Yes, absolutely I said that. But if you see over here, this is the PDF curve, right? So this fx, these are PDF values, agreed or not? These are PDF values. Okay. So PDF values are having some non-zero values. So these values, this point, let's say this is the point, say at random, I'm saying say 8. So f of 8 is having some positive value, correct? Let's say it is 0.14, for example, I'm saying. You know what? This has no meaning whatsoever. This has no meaning whatsoever. Because this 0.14 is not giving you the actual probability that x will be equal to 8. Because we know that from the properties of continuous random variable, probability that x will be equal to 8 is always 0. It's a single value. So probability of x taking a single value is always 0. So what is this 0.414 then conveying at 8? Nothing. It conveys no information. That is the most interesting part. The information is conveyed if you find out a range over here. Let's say if I want to find out that x lies between 6 and 8. If I want to find out the probability that x lies between 6 and 8, I will have to find out this area. This area gives me the probability that x lies between 6 and 8. But f8, f6, whatever values they take, they convey no meaning. Okay, at this level, at your level. Again, I'm repeating. Okay, so this might sound a bit confusing. That's why I'm repeating. I mentioned that probability of obtaining a 6 or a 8 is how much? Is how much?
0.
0. Correct. But f6, sorry, f6 or f8 might have some positive values which have no meaning. So the values of the PDF do not convey you anything. It only becomes meaningful when you integrate a PDF over a given set of real numbers. Okay. When you integrate, then it becomes meaningful. So PDF, when integrated over a set of any real numbers, it gives the probability that x lies between, say, any particular two numbers or in a particular range. Now, the last difference, that sum of the PDF equals CDF and integration of PDF, sum of PMF equals CDF. So summation of PMF equals CDF and integration of PDF equals CDF in this case for continuous. Because summation in case of discrete is analogous to integration in case of continuous and vice versa. Similarly, differentiation in case of continuous is analogous to differencing, subtracting in case of discrete. And that is why, if you remember, I mentioned that to calculate PMF, you take a difference of continuous values. So over here, if you differentiate CDF, you will get PDF. If you difference CDF, you get PMF. Okay. So these are conceptual points. This will not be tested. Again, anything related to integration, differentiation, if these words I'm mentioning, they will not be asked in the exam. So don't worry if you don't get it. Okay. So are the differences clear between PMF and PDF? Are the differences clear? So if yes, tell me. Yes or no? PMF gives the probability at any point. Yes or no? PMF gives the probability at any point. Yes or no? Okay, very good. Yes, correct. Next question. PDF gives the probability at any point. Yes or no? Value of PDF gives the no. Very good. So that is the distinction. Remember this. Okay. Fine. So quantiles, let's discuss. Again, we are not discussing the quantile function in detail. So it's the inverse of the CDF. We are just discussing the mean quantiles. So Median is defined as the 50% quantile because half of the probability is below the median and half is above it. Okay. Median is the, again, I'm mentioning we are not discussing the definition of quantiles and quantiles in details. We are just quickly recapping the main quantiles. Median is the middle value for a sorted discrete data. So we have discussed some examples where if you have discrete data, for odd numbers, you will have one middle number. And if you have even numbers, you will take the average of the two middle numbers. And of course, for continuous data, it will be the central point, where 50% of the distribution is to the left-hand side, 50% of the distribution in terms of area is to the right-hand side. Interquartile range. The difference between the 75% quantile and 25% quantile is a very, very important parameter. Okay, and it is actually a very good indicator, just like median. We'll discuss, in fact, there are some problems with mean. To overcome those problems, we use median because median is more robust to outliers. Similarly, IQR is also quite robust to outliers, and it is quite a good representation of your average data set. And mode measures the location of the most frequently observed value. So you can have unimodal data where you only have one mode. So mode means basically in a continuous distribution, you're looking at the highest point. So which value of X contains the highest value of the PDF, that is for continuous, and for discrete, you will measure which is having the highest frequency. So most frequently observed value. This is bimodal, two modes. This is trimodal, three modes. Okay. Now in distributions, this is the relationship for symmetrical data. Mean will be equal to median will be equal to mode. If the data is skewed, now this is where it becomes interesting. You see which one is pulled the most. See, over here, everything is at the center in case of symmetrical data. Which of the three parameters, mean, median, or mode, is being pulled the most? Tell me, both on the left-hand side and on the right-hand side.
Mean.
Exactly. You can see mean is being pulled the most. Mean is being pulled the most towards the left, right? On the right-hand side also, mean is being pulled towards the right-hand side the most. So mean is more susceptible to outliers, whereas median is more robust to outliers. Okay, so remember this. Fine. Okay, so we'll just take a 5-minute break. Please be back by 1:13 p.m. Thank you. I'll not pause the recording. Okay, please be back. Okay, let's resume. We'll start with common univariate random variables. This can be covered quicker than the previous chapters. So we'll start with Bernoulli distributions. So Bernoulli distribution is a discrete distribution for random variables that produce one of these two values, 0 or 1. It depends on a single parameter, which we call as probability of success, or P. And this is how we represent Bernoulli. X is Bernoulli distributed with a parameter of P. Okay. Now this is the PMF, an example of the PMF of a Bernoulli random variable. So there are two possibilities, 0 or 1. You can call say 1 as success or 0 as failure, but the choice is yours. Remember that. If there is no restriction whatsoever, but the convention is to call 1 as success and 0 as failure. Okay, and by success, it does not always mean that it should be a good event. It means that if you're modeling defaults, then default will be your success. Okay, so don't worry about these things at all when you're modeling this mathematically. You can choose anything based on your convenience. So this is an example of a PMF where you can see that if the probability of failure is 0.4, obviously the probability of success will be 0.6 over here. Okay. So what are the parameters of Bernoulli? The mean is P. Variance is P times 1 minus P. Again, these questions can be asked directly in the exam. PMF is P if x equal to 1. It is quite clear over here. PMF is P if x is equal to 1, and it is equal to 1 minus P if x equal to 0. And this is the CDF. Okay. So CDF will be something like a step function for a Bernoulli. Okay, step function. So like this. So it will be like this, step function. Okay. So this is clear, right? Bernoulli is quite simple. 1 minus P is the probability of failure and P is the probability of success. So over here we have taken an example for 0.6. Then binomial. Binomial has two parameters. You have N, which is the number of independent Bernoulli experiments, and again P, the probability of success. So you can say that binomial is nothing but a collection of N Bernoullis. So this is how you can see the binomial has been mapped over here. Remember, it's a discrete distribution. So this curve has just been highlighted, okay, over this discrete distribution to convey a message. The message is that when you are increasing the value of N, so earlier N was 4. So you have these 4 values of the PMF, okay? And now you have increased the value of N to 25. So as you increase the value of N, any distribution for that matter, whether it is binomial or not, any distribution, in fact, most of the distributions, I'll not say any, most of the distributions which are relevant to the FRM curriculum, they actually converge to the normal distribution and they tend to strike resemblance with the normal distribution. Okay, so what are the parameters of binomial? Mean is NP, variance will be over here, you have, this is missing, this will be NP times 1 minus P. Okay, and generally what we do is we also call sometimes 1 minus P as Q. So sometimes you can call it as NQ also, completely your choice. Okay. So over here also you can write it as NPQ. That is what we have told our candidates. You can remember it like this because then it is easy to remember the PDF like this because it is NCX P to the power X Q to the power N minus X. That is how you can remember. Or directly 1 minus P. So completely your choice, not a problem. Okay, so based on the PMF of binomial distribution, many questions have been asked in the past. So let's take one of the examples. The probability that each stock will go up, this is during an expansion, is 0.8. Just to make it clear, most of the examples that we have clear, most of them, not all of them, some of them are for car books also. Most of the examples that we've given in this slide, and this is a part of the slides that we have in our class PPTs also, some of them. So most of the examples are constructed in-house only. So they are new examples. Many of you might not have encountered these examples and they're not a part of GAR sample papers also. So this is also a chance for you to look into some fresh questions. So this is the probability that each stock will go up during an expansion, that is 0.8. An investor has 9 such stocks and the event of going up for any particular stock is independent of the other stocks going up. If X denotes the number of stocks that go up, what is the mean, variance, and standard deviation of X? And what is the probability that 0, 5, 7, or all stocks will go up. So let's just solve it quickly. So can you tell me what is the value of n over here? Quickly, what is n? Everyone? Correct, correct, correct. More answers, please. Please be involved. Yes, 9. Okay, what is P, probability of success? If we term success as the event that the stock will go up, that is my success, let's say. Very good, 0.8. Okay, so what will be Q, the probability of failure? 20%, 0.2. Okay, what will be the mean? Mean will be NP, we discussed it, 7.2. And variance will be NPQ 1.44. Now, standard deviation will be square root of 1.44, which is 1.2. So the calculations are quite straightforward, right? Calculations are quite straightforward. Now, before I proceed, I want to ask you guys, how do you interpret the mean? 7.2. What is the interpretation of this? Because 7.2 is not an integer. 7.2 stocks cannot go up. Do you agree or not? Do you agree or not that 7.2 stocks cannot go up? Okay. Right. So how do you interpret it? You can try and relate it to, say, some simple examples. So very good. You can even say in the long-term average value. So long average value of what? In the long-term average value of what? Yes, absolutely correct. So that is a good way to interpret it, and that is how probability should be interpreted. Because if I say that there is a 40% chance that it will rain today, I have calculated, 40% probability. Is it guaranteed? I mean, is it guaranteed that out of 100 days, 40 days it will rain? There is a guarantee. Or let's say if we take a simple dice, six-sided dice, there are six outcomes: 1, 2, 3, 4, 5, and 6. And the probability of each outcome is 1 over 6, 1 over 6, 1 over 6. Is it guaranteed that every 6 times we will have each outcome once? Is it guaranteed? No. Then how do you interpret probability? You actually interpret probability like this, that if you carry out the experiment a large number of times, theoretically it should be infinite number of times, theoretically. But if you carry out the experiment large number of times, then your actual probabilities, the practical probabilities, the calculated probabilities will converge to your theoretical probabilities. That is how it should be interpreted. So if you say roll the dice only 10 times, then if you calculate the number of outcomes that you got, say number of times you got 1, 2, they will be very different from the theoretical probabilities of 1 over 6, 1 over 6. If you roll the dice 100 times, they will become better to, they'll become a little bit closer to 1 over 6. If you roll the dice 10,000 times, million times, billion times, if you roll the die billion times, you will automatically find that the probabilities of all the outcomes, they match and they are very, very close to 1 over 6. So this is how it should be interpreted. Similarly, expected value. If you find out the expected value of, say, any random variable, say again in a throw of a die, you'll actually find that for a throw of a die, the expected value is 3.5. But 3.5 can never occur on a dice. Because if you multiply, say, 1 by 6 times 1 plus 1 by 6 times 2 plus dot 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 up to 1 by 6 times 6, you will actually get 3.5. You can check that. Can you get 3.5 in a roll of a die? No. So what is the interpretation? That if you roll the die enough number of times, many number of times, say infinite number of times, then the average of all those values will be equal to 3. Similarly over here, okay, in the long run, the average value will be 7, okay, of the number of stocks going up. There can be another interpretation also. I'll tell you when I calculate it. So tell me one thing. You can have 0 stocks going up, 1 stock going up, 2 stocks going up, 3 stocks going up, 4, 5, 6, 7, 8, 9. Okay. So there can be 10 possible outcomes. Agreed? Okay. So tell me one thing. What do you think if I find out all these individual probabilities? How do you form a distribution? You find out all these probabilities and then you map them. Okay, where the y-axis is the value of the probability and the x-axis is the value of the variable. So then you get a distribution just like this. So there are 25 different probability values over here. Okay, 25 different probability values over here, and these have been mapped. So this is how your distribution is obtained. So that's the difference between distribution and a single probability. So my question is, if you find out this entire distribution, all the possible values, okay, so let's find out. So we have to find out 0, 5, 7, and 9. What do you think, whose probability should be highest? Just by looking at this information, can you tell me? See, these are subtle clues, small clues to find out whether you have calculated your answer correct or not. Very good. Again, instead of direct message, please send it to everyone. Very good. 7. 7. Okay, so this is another interpretation. So even though 7.2 stocks cannot be there, but at least there is a number which is close to 7.2. Closest is 7. So you'll have the maximum probability for 7. Okay, and the second highest maybe for 8. Let's calculate. Let's do it for the first one. 9C0 times 0.8 to the power 0. So this is a very, very low probability, but not 0. Similarly, for 5 stocks, 7 stocks, and 9 stocks, we have calculated. And you can clearly see that for 7 stocks, we have a very, I'll not say very, very high, but a very high as compared to others. The highest probability, 30.2%. So is the idea clear? Is the idea clear? Okay. Now we have the Poisson distribution. It measures the counts of events over fixed time spans. So for example, number of calls in a call center like that per minute, something like that. So number of accidents in a road or number of defaults in a month like that. The random variables are always non-negative and integer valued, and it has a single parameter called the hazard rate. It is the average number of events per interval. Okay, this is the PMF. Again, you're seeing, I told you, no matter whichever distribution you take, the more number of the parameter values you increase, it tends to get closer and closer to the normal distribution. In this case, the parameter is lambda. So the mean of the Poisson is lambda, the variance is also lambda, PMF is this, and CDF of a Poisson distribution is this. Okay, in the class live video and self-paced video also, we have done some examples based on Poisson distribution also to make the idea more clear. Okay. Now, any value, let's come to a continuous distribution. Let's start with uniform distribution. So for a uniform distribution, any value within the range is likely to occur. And this is the mean, a plus b by 2. This is the variance. This is the PMF, and this is the CDF. Now you can remember everything. See, mean and variance you have to remember. PMF and CDF you don't need to remember. Conceptually, you can understand it quite easily. How? When I say uniform, it means any value is equally likely to occur. It means all of them have same probability. Correct? So let's say you are having the support is between A and B. And any value is equally likely to occur. It means the PDF will be, and in fact, there is a mistake over here. It will not be PMF, it will be PDF. Why PDF? It's a typo. Why PDF? Why not PMF?
It is continuous.
Continuous, exactly. So these mistakes have to be, in fact, I will expect that you guys, there will be, if there are any typos, I mean, we had before also there was some typo. You spot it quickly and tell me, okay? Because that will help you to make your understanding even stronger. So this is PDF. So since all of the values are equally likely, yes, variance is also, there's a typo. Very good. It should be B minus A whole square. Correct? That was the variance. So there are some typos. Wherever you find a typo, please let me know. Is it correct now? B minus A whole square? Yes. Okay. So this is the PDF. Now tell me one thing. If I want to just reduce this, why it should be 1 by B minus A? The idea is very simple. Is this a rectangle? Is this a rectangle? Okay. What is the length of this rectangle? What is the length of this rectangle? Correct. B minus A, right? And we know that the sum of all probabilities has to be 1, right? So the total area should be how much? So area of rectangle should be how much? 1. So if you know the height, you can calculate the area. But if you don't know the height and you know the area, can you calculate the height? Can I say that B minus A length times height of this rectangle, or breadth, if you want to call it, you can call it breadth. Height would be better because we are talking about the PDF values over here vertically. So can I say that this should be equal to 1? Yes or no? Do you agree? The area of the rectangle is always equal to 1. So what is H? What is H? 1 over B minus A. So this value is nothing but 1 over B minus A. So between A and B, that is what is written over here. So between A and B, the PDF is 1 over B minus A. Before A, it is 0. After B also it is 0. So is it clear how to derive it? How to, in fact, the derivation also will not be difficult in the exam. Detailed derivations we are not doing, but these are obvious things, right? These things we can quite easily interpret in the exam rather than remembering the stuff, right? So if you have a uniform distribution, let's say numbers are given to you, then it will become even easier. You just remember that the total area should be equal to 1. And these are figures for which area can be easily calculated. Okay. Similarly over here, x minus a by b minus a. This also can be quite easily interpreted and derived quite easily. So if x is any value over here, okay, between a and b, and CDF means what? CDF means from the minimum value up to x. So what is the minimum value over here? What is the minimum value over here? A, correct. So up to x, it means you have to calculate this area, agreed or not, for CDF. For a particular value of x, you have to calculate the green area, agreed or not. What is the length of this rectangle? X minus a. You've already calculated the height of this rectangle. Correct? So if you multiply length by height, will you get this? Yes or no? Is the CDF clear? To everyone, everyone should answer this. If there's any doubt, please ask. Okay, so this is how you have to interpret these things quite simply in the exams. Okay. Now, if A is 0 and B is 1, then it is known as the standard uniform distribution. And as I said, this will be A, which has a mean and variance of half and 1 over 12. So obviously, if A is 0 and B is 1, then 0 plus 1 by 2 half. Variance will be 1 over 12. Now let us come to one of the most important distributions that we have to do, normal distribution. So it is completely described by its mean, mu, and variance sigma square. This is how we write it. Expected value is mu, variance is sigma square. What is the skewness of this distribution? What is the skewness of this distribution?
0.
Very good, 0. So can I say that mean equal to median equal to mode? Okay, and what will be the kurtosis of this distribution? What is the kurtosis? Very good, 3. Excess kurtosis was 0, correct? Now, one point which is very important from the point of view of the exam, which again is overlooked over here sometimes, because this part though everyone knows. But what about if there are two normally distributed variables, x1 and x2? Both are having different means and different variances. If these normally distributed variables, if they are independent of each other, this question was directly asked in the exam, directly. if they are independent of each other and you construct a third variable, y, which is the sum of these two normally distributed variables, then you can easily prove that this new variable y will also be normally distributed with a mean of mu1 plus mu2 and variance of sigma 1 square plus sigma 2 square. Very important point, okay, for the exam perspective. Is it clear? Is the last point clear? Not the derivation. Will you be able to remember this? If there are two independent normally distributed random variables, then the sum of those variables is also normally distributed with a mean of mu1 plus mu2 and variance of sigma 1 square plus sigma 2 square. Okay. And this is how a normal distribution looks like for different values of mu and sigma. Okay. And how will the CDF look like? CDF will always be a non-decreasing function like this. Okay, now let's come to confidence intervals. We have 4 confidence intervals which are very important. We have 68% confidence interval, mu minus sigma to mu plus sigma. We have 90% confidence interval, mu minus 1.645 sigma to mu plus 1.645 sigma. We have 95% confidence interval, mu minus 1.96 sigma to mu plus 1.96 sigma, and we have 99% confidence interval. So the meaning basically of these confidence interval, layman interpretation, again I'm saying, not the theoretical correct interpretation, because the theoretical correct interpretation is quite detailed. Okay, the layman interpretation is that if suppose you are talking about say 90% confidence interval, it means that you can be reasonably confident that 90% of your observations are between these two values, mu minus 1.645 sigma and mu plus 1.645 sigma. So this area contains 90% of your observations. Similarly for the other confidence intervals. That was the interpretation, layman interpretation, not the correct interpretation. Again, I am repeating. So let's solve an example. The return on a stock is 12% per annum, and the standard deviation of annual return is 15%. Assume that the returns follow a normal distribution. Find the 90% confidence interval. So 90% is from mu minus 1.645 sigma to mu plus 1.645 sigma, which is 12% minus this times this. So you get straightforward answers. So you can be 90% confident that your returns under these conditions, your annual returns, will be between negative 12.675 to positive 36.675%. Now let us come to standard normal. So standard normal distribution is stated like this. It has a mean of 0 and variance of 1. And this is the Z value which we'll actually map for the standard normal distribution. Now, I told you, remember earlier, that this is also the standardized version of any random variable. And this has a mean of 0 and variance of 1. Standard deviation also of 1. So the same thing follows here. This can easily be proved that it has a mean of 0 and variance of 1. So remember, this is the Z value. This is the standard normal distribution. See, in the class, we have, in fact, for only multivariate random variables for probability, we have 3.5 hours, 4 hours of video for one chapter. So we are trying to cover these things in 30 minutes to 1 hour. So that is why we are actually rushing. But again, I'm repeating, I'm assuming for those who have joined late, I'm assuming that you are already through with the course at least once, and this is just a revision session for you. Now, this last part, phi negative z is equal to 1 minus phi z. This is a property which uses the symmetricity of the normal distribution, the symmetrical properties of the normal distribution. And can you tell me where this is utilized heavily, this property? When this will be helpful for you in the exam? When will this be helpful for you in the exam? When you will be given a Z table, let's say you're given a Z table, which does not contain any negative values. And you have to find out the phi values corresponding to the lower tail, correct, Sushant? So this property you'll use. See, if you directly have a Z table where you can find out the phi value directly, okay, then there is no problem. But what if you don't have it? So then you use the positive values only and you apply the symmetric properties of the normal distribution. Okay. So consider our last example where the annual return on a stock is normally distributed with a mean of 12% per annum, standard deviation 15. Same examples. What will be the Z value corresponding to -3 and 19.5%? So first case, I said X is -3. Z value will be -1. So what does it mean? It means that, listen to this very carefully, the interpretation. It means that -3% is one standard deviation away from the mean, which is 12% on the left hand side, because it is having a negative sign. Okay, so this -3, when you compare it in terms of distance, okay, this is 12%. I'm not writing percent over here. So in terms of distance, if you compare, this distance is one standard deviation. So this is basically the meaning of Z value. It tells you how many standard deviations away an observation is away from the mean and on which side. Okay, that is the interpretation of Z value. How many standard deviations away? Similarly, for 19.5, can anyone tell me how many standard deviations away you are getting? You solve this quickly, because it's very simple. What is the Z value corresponding to 19.5? Very good, 0.5. So 19.5 is 0.5 standard deviations away from the mean of 12% on the right hand side. Okay, that is the interpretation. Now, if suppose you want to approximate discrete random variables to normal distribution, so there are some conditions. One is for binomial, the other one is for Poisson. So for a binomial random variable, if both these conditions are satisfied, NP is greater than or equal to 10. NPQ, you should write NP. Yeah. If NP is greater than or equal to 10, in fact, there was a condition for NPQ also. There is a condition for NPQ also. NPQ should be also greater than or equal to 10 actually. Then it makes a better distribution. Okay. Now, the PMF is nearly symmetric and well approximated by this in that case. It means you will get a normal distribution with a mean of NP and variance of NPQ. Okay, but these two conditions are more important. NP is greater than or equal to 10 and NQ is also greater than or equal to 10. Okay, and in some literature, as I said, you'll find some conditions with respect to NPQ also. In fact, NPQ is greater than or equal to 5 is also acceptable sometimes. Okay, so if these conditions are satisfied, a binomial distribution can be approximated to a normal distribution. Also, a Poisson distribution can be approximated by a normal random variable when lambda is greater than or equal to 1000. In that case, you will get a normal distribution with a mean of lambda and variance of lambda. Now, log normal distribution. If suppose y is equal to ln x, then x is log normally distributed if y is normally distributed. So if suppose y is defined as natural log of x, and if y is normally distributed, then we'll say that x is log normally distributed. There is another way to define it. Alternatively, a log normal distribution can be defined like this. X is equal to e raised to the power y, where y is normally distributed with a mean of mu and variance of sigma square. And in that case, we say that log of x is normally distributed with a mean of mu and variance of sigma square. So this is how it can be denoted. X is log normally distributed. It means log of x is normally distributed. So again, I'm repeating. Remember this. X is log normally distributed means log of x is normally distributed. X is log normally distributed means log of x is normally distributed. And over here by log, I mean natural log. Now, log normal distribution, you all know that it is only defined for x greater than 0. So it does not take negative values. It is not defined for negative values of x. This is because logarithm of a negative number is not defined in the real number system. Can you tell me a good part about this property, a practical application of this property? Which instruments, which financial instruments
Prices can be
Yes, please.
log normal in
Your voice is not very clear.
or
So
price.
prices, perfect. So yeah, Divesh has mentioned, Divesh, not stock returns, stock prices, because returns can be negative also, right? Got it? But prices cannot be negative, correct? Again, this is also a question, a very easy question, which has been asked not recently, but in 2015-16, this question was asked 2-3 times continuously, because the GARP has this tendency of, earlier in fact they had this heavy tendency of repeating questions, at least 8 or 10. In fact, I'll also give some good news over here with respect to sample papers. If you have gotten access to the 2024 sample papers in your GARP dashboard, in your portal, then there is a good chance that at least 8 questions will be almost similar to what are given in the sample paper questions, almost or even identical. When I say almost, they might just change the numbers a little bit, tweak it a little bit, but more or less you'll find that 8 questions will almost match. So practice the sample papers, yes, including both marks, yes, including both, at least I'm saying, at least. So if this batch is lucky, then maybe 10, 12, 15, who knows, but practice them properly. Okay, because they are a very good reflection of what is going to be not exactly tested, but how GARP is changing the pattern towards more theoretical questions or conceptual questions, what they intend to ask this year. Okay, so practice the sample paper questions without fail. So the application of this property is that it is very useful to model stock prices. Yes, Rohit. See, actually, we give our candidates the past sample paper questions of the last 15 years. And we don't just give them as PDFs. No, we have actually taken a lot of time and we have filtered those questions module wise, and we have omitted the questions which are not relevant from the current syllabus point of view. Module wise, we have filtered so that you can get everything in one place. Okay, and mapping according to the learning objectives also has been done. And if there are some mistakes also in the solutions, yes. So instead of last 5 years, Rohit, don't uh, solve this PDF separately. Use our the main MidhaFin PDFs for the past sample paper questions. That's what I'll say. And of course, there might be a little bit some, or maybe once in say 100 pages or once in 50 pages, there might be some typos. Notify us, but use them only, the PDFs which we have provided. Okay, but for current year papers 2024, that you can use it from the GARP dashboard. So that would be advisable. Okay, so the distribution is positively skewed. So log normal distribution is actually positively skewed. It has a long right tail. So there are outliers on the right hand side. Then chi-square distribution, they are defined, again, the details of these distributions were there earlier prior to the 2020 curriculum. Since 2020, the details have been omitted. In fact, in hypothesis testing, even the chi-square test, F test were discussed extensively, which has been omitted now from the syllabus. Now a very basic intro has been given. Chi-square is defined as the sum of squares of new independent standard normal random variables. So sum of squares, remember, how is chi-square defined? Sum of square of normal variables. Okay, it has new degrees of freedom. This is how it looks like, and this is this is how it looks like. That's it. That is what you have to cover in chi-square, nothing more than. Then t distribution is closely related to the normal distribution, but it has heavier tails. Okay, now one thing which I think is not very clear in the GARP curriculum, and they have asked questions also, and it might be incorrect, but that is what you have to choose in the exam. Let's say they give you the choice for a leptokurtic distribution, and you find that T distribution is the only option which has heavier tails. So you'll have to choose the T distribution, right? So T distribution is leptokurtic. But there is still a debate with respect to T distribution, although it has heavier tails, but what about the central region? Okay, but mostly T distribution is also having a higher central region. So you can safely say in the exam, even if it's not 100% correct, but for most of the cases, T distribution is a leptokurtic distribution. That is what you have to assume for the exam point of view. So it has one parameter again, and it is a distribution of y is equal to z divided by square root of w by nu, where z is it a standard normal W is chi-square random variable, Z and W are independent. Generally, I have not seen questions based on T distribution, chi-square distribution, and this is how it looks like, okay? And F distribution in the past few years, okay? Generally, in the last 2-3 years, I have not seen questions, and even the candidates have not given any feedback that these kind of questions were asked in the exam. So this part, you can just go through the PDF that we'll provide you, okay? So, okay, so that's it for the first 3 chapters. Let's take a break right now, and we can resume in 20 minutes. Is that okay? At 2:10. As I said, we'll take 4 long breaks and some short breaks, 5 minutes each. Okay. So 20 minutes break, have your lunch, be back by 2:10 p.m. Okay. Now this time, what I'll do, with respect to recording, okay, if we are having 20 minutes. Okay, so I'll resume the recording later on. Fine. No problem. So we'll start QTA 4 now. Now, multivariate random variables, they are vectors of random. So basically, they are extending the concept of a single random variable so that measures of dependence can be included between 2 or more random variables. Okay. Example is bivariate random variable. Now, each component of a multivariate random variable is a univariate random variable. They can be discrete or continuous, just like univariate variables. For discrete, we remember we had PMF. For continuous, we had PDF, and CDF was common to both. Okay. Now, as I said, they are vectors of random variables. So, for example, if you consider a bivariate random variable, so X will be a vector, okay, with 2 components, X1 and X2. Okay. And its realization, now there is something called as the vector, and of course its value. Generally, we denote the vector as X or the function as capital letters. If you remember earlier also, we used the capital letters X, capital X for the random variable, and the realization of the random variable was denoted as small x. So this is the random variable, the 2 components of that, and the realizations and the 2 components of that. So X1 is a realization from capital X1, small x2 is a realization from capital X2. Okay, so this is the PMF of a discrete random variable bivariate. So basically, this is how we denote it, f x1 x2. When we write f x1 x2, it simply means that probability that x1 will be taking the value of x1 and x2 will be taking the value of x2. And CDF returns the total probability that each component is less than or equal to a given value. So everything, the key ideas are same. They have just been extended to include one more component. So one of the examples is trinomial distribution. For a bivariate random variable, the example is trinomial. Remember, for a univariate random variable, the example was binomial. And for a bivariate, it is trinomial. So you might be wondering, it was uni and the distribution was bi. Over here, it is bi and the distribution is tri. So basically, one is being added, right? When you're talking about distribution, you'll understand why. You'll just understand why. So let's take an example. So there are 2 components, in fact, of a trinomial. There are n independent trials. And we talk about 3 outcomes. Since it's a trinomial distribution, we will discuss 3 outcomes, of course. In case of binomial, we were discussing 2 outcomes. So we can model these 3 outcomes using actually 2 components only. That is why it is a bivariate random variable, but a trinomial distribution. Trinomial distribution for 3 outcomes, but it can be modeled using 2 components. That's why it is bivariate. Earlier also, in case of binomial also, see, it was modeled only using the success parameter, right? Because the failure parameter was implied as 1 minus p. So over here, if suppose there are 2 components, x1 is the number of realization of outcome 1, x2 is the number of realization of outcome 2, and you know that there are total n independent trials. So using n, x1 and x2, can we say that simply n minus x1 minus x2 is the number of realizations for outcome 3? Yes or no? Or n minus x1 plus x2. So do we need a third variable x3, or we can directly deduce it? Do we need a third component x3 over here, or we can directly reduce it? We don't need. Absolutely correct. We can reduce it. So that's why bivariate trinomial. Okay, so that is the idea over here. So it has three parameters: n, the number of experiments; p1 will be the probability of observing outcome 1; p2 will be the probability of observing outcome 2; and probability of outcome 3 can simply be calculated as 1 minus p2 minus p1, which is nothing but 1 minus p1 plus p2. And this is the PMF of a trinomial: n factorial divided by x1 factorial, x2 factorial, x3 factorial times p1 to the power x1, p2 to the power x2, p3 to the power x3. Now we have written x3 and p3 separately because it makes the memorization of the PMF easier. Because if you have, let's say, 1 minus p2 minus p1 over here, and you have n minus x1 minus x2, it will make your job a bit difficult in terms of memorization. So that's why just write x3, but it should be implied what is x3? X3 is nothing but n minus x1 minus x2, because x1 plus x2 plus x3 is n. Okay, and simply p3 is also 1 minus p2 minus p1. Okay, so I have reproduced this definition over here, and let's solve an example. So if n is 8, p1 is 0.25, p2 is 0.6. I have to find out the probability that what is the probability that x1 will take a value of 1 and x2 will take a value of 5. If this is what I have to find out. Technically, I am telling you, technically, they should be capital N. Again, see these things, although people tend to ignore, but see, because 1 is the real, this is actually small x1. You know, this should be capital X and this should be capital X2. Anyways, don't worry about all these things from an exam point of view, but technically, capital X1 is the random variable and the small x1, this is the realization. Okay. Anyways, let's continue. So tell me what will be x3 over here? What will be x3? What will be x3? Quickly.
2.
2. Very good. So we can use this to find out x3. Absolutely. So x3 is 2. What is p3? What is p3? Perfect.
0.15.
Yes, yes, 0.15. So we can use this to find out p3, which means my f1, 5. So this can be simplified to, if you want to write it in a condensed manner, you can write f1, 5 simply is equal to, we use the PMF of the trinomial and we get the result as 7.35%. So the interpretation is that under these conditions, the probability of x1 taking a value of 1 and x2 taking a value of 5 is equal to 7.35%. Now let's come to joint probabilities. So let's take an example over here. Now, discrete distributions, if they are defined over a finite set of values, they can be described using this kind of a probability matrix. It simply relates the realizations that we were talking about, these three realizations, to these probabilities. And these are joint probabilities. So basically a tabular representation of the PMF, you can say. Okay. So what is the meaning of the numbers in this table? These are giving you the joint probabilities. So for example, the probability, say this one, of x1 taking a value of negative 5% and x2 taking a value of negative 1 is 20%. So this 20% is the joint probability that the stock return will be negative 5% and the analyst rating will be negative. Remember, this is not the conditional probability. Conditional will be calculated later. This is the joint probability. So all these numbers in these cells are the joint probabilities. Okay, is it clear? These are joint probabilities. Is it clear? Okay. Now, what if I want to deduce the marginal PMF from these joint probabilities? So now the same table I've just extended to include one more extra column, one more row, where we are actually summing the entries of these cells. So basically, if I want to find out the unconditional, see, marginal also implies unconditional. So unconditional in this case, not always, in this case, for probabilities. So when I want to find out the unconditional or marginal probability that the stock return is negative 5%, what is the probability that the stock return is negative 5%? Simply, So we will just add all the entries over here. So for negative 5%, we have 3 entries, 20%, 10%, 5%. What is the summation? 35%. Okay. Similarly, can you tell me what is the probability that analyst rating is neutral? What is the probability that analyst rating is neutral? Everyone. Not only one or two answers. What is the probability that analyst rating is neutral? Correct, absolutely. So you will sum across the second row, right? This is your neutral. So this is your probability over here, okay? To make it more precise, I can also include either this part or I can remove this. But anyways, that's just a diagrammatic representation, but the idea is clear. Now, one more important aspect you're observing is either you sum across these cells or you sum across these cells. The total will always be equal to 100%. So this is how you derive marginal probabilities from joint probabilities using this joint probability matrix. Now, the marginal CDF measures the total probability in the marginal PMF less than or equal to x1. So similarly, in a very similar fashion that we defined the CDF, over here also it's the same thing. So let's say if I want to find out the marginal CDF corresponding to x1 at 0%, it means that if I want to find out that the stock return will be less than or equal to 0%. So less than or equal to 0 means what? Either this or this. So I'll find out the marginal probability of this and I'll find out the marginal probability of this and I'll just add them both. So can you tell me what will be the CDF defined in a way such that I want to find out the probability that the stock return will be less than or equal to 0%? Tell me. Correct. Absolutely correct. Okay, so basically we are going to add this and this. For 0%, you have 30. For negative 5%, you have 35. So this is your CDF. That's why capital F is written over. CDF. So this gives you the probability that stock return is less than or equal to 0%. Okay. Now conditional probability. Again, in the same way that we calculated conditional probability earlier, only the notations have changed a little bit. Okay. So if you remember, this was the formula for conditional probability earlier, right? So in the numerator, you have joint probability. Over here also you have joint probability. Okay, in the numerator, you have the marginal probability. Over here also you have the marginal probability. So let's take an example. Using the same table, if I want to find out the conditional probability, this question can be asked in the exam. Because they'll give you a table, let's say, and joint though they'll definitely not ask because it will be way too simple. Marginal also is way too simple. So what they can ask is, I think, this kind of question where you are assuming that x2 has already occurred. If you are assuming that x2 has already happened, okay, so given that x2 equal to 0 has already happened, it means that it is given that analyst has already given a neutral rating. So given that analyst has given a neutral rating, what is the probability that the stock return will be negative 5%? If this is what I have to find out. So what is in the denominator? Marginal probability. Now earlier, in the case of the theorem of total probability, when we studied this for the first time, I said that the denominator generally should be calculated using the theorem of total probability. You add all the probabilities for the denominator, right? The corresponding. Over here also you are doing the same thing. You are adding across the rows. So only the representation is different. You are adding across the rows and the columns. Okay. So tell me one thing. First, I want to find out the marginal probability of x2 equal to 0. So what is the marginal probability of x2 equal to 0? We have already calculated. What is the marginal probability that x2 will be equal to 0? Absolutely. 40%. Okay. This blue oval, add all the probabilities. 10, 15, 15, 40%. 40%. We have already calculated it. So the denominator will be how much? What will be the denominator for this? 0.4 only based on our definition. Okay. So this is our definition of conditional probability. This one, fx1 comma x2 divided by fx2. So joint divided by marginal. Joint divided by marginal. So look at the table and tell me what is the joint for these two. What is the joint for x1 equal to -5 and x2 equal to 0? Let's go back to the table. See the question carefully and I'm going back to the table. Find the joint of these two outcomes. Okay, x1 equal to -5, x2 equal to 0. Fast. x1 equal to -5 and x2 equal to 0. What is the joint? Correct, 0.1. So this is the joint, this one. This cell we are talking about. This cell. Okay, so over here, x1 equal to -5% and x2 equal to 0. So analyst neutral rating and so joint probability is 10. So joint is 10, marginal was 0.4. So what will be your answer? 0.25. As simple as that. So is it clear how to calculate conditional probability from the table to everyone? Great. Everyone. Okay. So I think the animations were not in correct order. Actually, this should have been before. Okay, so this is the joint probability, this is the marginal probability, and this is the final probability. This animation was missed, I think. Okay, fine, no problem. Now, anyways, so the two components of bivariate random variable, they are independent if fx1 comma x2 is equal to fx1 times fn. This is similar to the joint probability being the multiplication of the individual probability. That was the independence condition. Remember this from probabilities? It's exactly the same thing which is written just in a slightly different notation. The same thing is written in a slightly different notation, and we know that this was the condition for independence. Okay. So tell me one thing. This is the example over here. Okay. And the numbers have been changed. Okay. Just for this example. So first, let's find out the marginal probabilities. Let's add across these three rows. If we add across these three rows, just check the calculations. Will you get 35, 30, and 35? Yes or no? Is it correct? Okay. Now, across the columns, you get 35, 30, and 35. Across the rows, you will get 30, 40, and 30. Correct? If you add these three entries, 30, 40, 30. Correct? Now, if I have to check the joint probability that x1 equal to 0% and x2 equal to -1. If I have to check this, is it 9%? This one? Agreed? Is this correct? The joint probability? Okay. So what is the product of marginals over here? The joint probability of x1 being equal to 0% and the analyst rating being negative, that is x2 being equal to -1, is 9%. But the product of marginals, let's calculate that also. So for 0, x1 equal to 0, the marginal is 30, right? And for x2 equal to -1, the marginal is 30 again. So over here, PA times PB is also 0.3 into 0.3, which is nothing but 0.09 or 9%. Are these equal? Is the joint equal to the product of marginals? Is the Sushant 0.09, right? Do not miss it because these silly mistakes will be very costly. You know, even if you say miss one or two questions because of these silly mistakes, it will be. So as of now, you just have to compare. But maybe in a calculative question, instead of 0.09, if you mention 0.9, it will be a disaster, right? So please do the calculations very, very carefully in the exam. So is the joint equal to the product of the marginals? Yes. Is it true for all cells? Can you check randomly for any one cell? Because since all of you will be checking, and there are around 50 candidates right now, 47 candidates. So if all of you are checking, I'm assuming everyone will check, say, any random cell on their own. So all the cells will be checked. Just check any one random cell and check if the product of marginals is equal to joint or not for any other cell. Yes, every cell. Correct. Absolutely. So even if it is not applicable for a single cell, the independence condition will be violated. So that's why these numbers have been chosen very carefully by Garth. Okay, so that this example is clear to you. Got it? Fine. So expectations. Now, instead of writing the formula for expectations, I thought that it would be better to explain expectations directly using an example over here. Because we know what is expectation. Expectation was nothing but summation pi xi. Even in case of bivariate, it works in a very similar way. So let's see an example. So let's say you have x1. Okay. It's not visible. I'll use a different ink over here. This is x1. Okay. And this is x2. So x1 is taking the value 1 and 2, and x2 is taking the values 3 and 4. Now consider this function, x1 to the power x2. So there are 4 possible outcomes for this function, because there are 2 values for x1, 2 values for x2. So that's why there are 4 possible outcomes, 2 times 2. What are those 4 outcomes? These are the 4 outcomes. Do you agree? Do you agree? These are the 4 outcomes. 1 to the power 3, 2 to the power 3, 1 to the power 4, 2 to the power 4. Because x1 is only having 1 and 2, x2 is only having 3 and 4 values. So if I want to find out the expectation of g x1 comma x2, and these are the probabilities which are given, the joint probabilities. And of course, I have to use joint probabilities because see, when will x1 to the power x2 take a value of 1 to the power 3? It will only take a value of 1 to the power 3 when x1 is 1 and x2 is 3. Correct? So if I want to find out the expected value of x1 to the power x2, these type of questions can be asked in the exam. If I want to find out the value of x1 to the power x2, what will I do? I'll multiply these individual probabilities by these value of the function, the realized value of the functions. Agreed? So 15% will be multiplied with 1 to the power 3. Can you tell me 2 to the power 3 will be multiplied with which probability? 2 to the power 3 will be multiplied with which probability? Correct. 10%. 2 to the power 4 will be multiplied with which probability? Very good, 15%. And finally, 1 to the power 4 will be multiplied by 60%. So if we do this, we are able to find out the expected value of x1 to the power x2 like this, which is 3.95. Is it clear? Will you be able to calculate the expected value of a function in case of bivariate variable now? Will you be able to calculate it in the exam? Okay, very straightforward. Just multiply the probabilities by the realized outcomes. That's it. Okay. See, one thing I just want to point out over here. Since this is a crash course, I said we are taking very limited examples, but initially also I said that doubt solving will be very difficult and query discussion will be very difficult. But in case of examples that we are discussing, if you are not able to understand the solution or any of the steps, you can ask directly and I'll explain that time. Okay, like some of you have asked earlier also. Don't hesitate to ask in between examples. Now moments, just like in the case of univariate, the first moment is similarly defined. The only difference is now you have the mean of both the components, mu1 and mu2. Second moment, in case of a bivariate random variable, anyone who can remember what is the second moment? In case of univariate, second moment was variance. In case of bivariate, what is the second moment? Do you remember?
Covariance.
Very good. It is covariant. So these are the two formulae. One is this one, the other is this one. Again, this is sometimes more convenient to use. Completely your choice during the exam. Okay, now there's a problem with covariance. We all know that although covariance tells you how the two variables are moving together, it does not measure the strength of the relationship. So comparability is a problem with covariance. The values cannot be compared. Okay, so that is why to compare them, we have to scale the values, and when we scale the value by dividing the covariance by the product of standard deviations, we get correlation, which can be easily compared across data points. Okay, so correlation between x1 and x2 or rho 1 2 is defined as this is the covariance divided by the product of the standard deviations. Okay, and of course the same result can also be written like this. Covariance is equal to correlation multiplied by product of standard deviation. Now, correlation measures the strength of the linear relationship between two variables, and this scaling effect ensures that it is always between -1 and +1. Okay. Now, if you remember, we did scaling effects and shifting effects earlier on some moments. What about covariance? What can shifting and scaling do to covariance? So this is the effect. If you have covariance of a plus, so both the variables x1 and x2 have been linearly transformed. Earlier there was only one variable. Remember, x, it was transformed to y is equal to a plus bx, and we discussed about 4 moments, the effects that were there, the 4 moments. In this case, you can see that the location parameter has no effect whatsoever on the final covariance. Okay, because the covariance between x1 and x2 is simply multiplied by the scale parameters b and d. So this has no effect. What about correlation? What about correlation? For correlation, these scale parameters, in fact, the location parameters again will have no effect. Again, I'm telling you, that's why I have not even included the location parameters. Although if it was included, it would be more general, but there was no point of including. They will have no effect. Okay. Even the
It's B and D, right?
sorry,
Is sign of B, sign of D.
sign of no, actually it's a. That's I've written a and b. Okay, the scale parameters actually have. Where are you saying?
From previous
Which
one,
part?
A plus BX1, C plus BX2. If we calculate correlation,
This one,
it will be
sign of.
yeah, sign of B into sign of B.
This will be sign of b times sign of d.
No. If you take same expression as previous
Yes,
one
absolutely,
and
absolutely,
calculate
absolutely. Yes,
correlation,
absolutely, absolutely. So that's why I would have. It would have been better if a more general case simply this would have been replaced by correlation, covariance, and absolutely it would be sign of b, sign of d. So that is what I've written. The scale parameters are now a and b. So the point is that finally it is the sign of the scale parameters which actually affect the correlation. Okay. So as you mentioned, in fact, I'll write that also in a plus bx1 c plus dx2 is equal to sine of b sine of t multiplied by correlation times correlation of x1 comma x2. Okay, so this is the general case, and this is where I have altogether omitted the location parameters because they are not making any difference. So the sign of the scale parameters make a difference. So let's see some examples. One example, in fact, please. Let's say the correlation is negative 0.78. Okay, and if I want to find out the correlation between 8 plus 3x1 and 2 minus 4x2. So this 8 and 2 will have no effect. Fine. Sine of 3, sine of -4, and finally correlation between x1 and x2. So what will be the final answer? What will be the final answer? Everyone, even if it's very straightforward and simple, please send the answer. What is the correct answer? Sine of 3 is positive. Sine of -4 is negative. And then you have correlation as negative 0.7. So negative times positive times negative 0.78, which is 0.78. Okay. So this question also can be asked as one of the easier questions in the exam. Now, what are the properties of covariance? So covariance between x1 and x2 is equal to 0 if they are independent random variables. What will be covariance of a variable with respect to itself, guys? What will be the covariance of a variable? Very good. It is variance. Correct. So covariance of any variable with respect to itself is nothing but the variance of that variable. Absolutely. Now this we have already seen. Then variance of x1 plus x2 is equal to variance of x1 plus variance of x2 plus 2 times covariance of x1, x2. This is a general formula that I think you should remember from the exam perspective. Quite easy to remember. Very analogous to a plus b whole square. And variance of x1 minus x2 is equal to variance of x1 plus x2, variance of x2 minus 2 covariance x1, x2. Now, if x1 and x2 are independent, then of course this term will become 0. And in that case, whether you are talking about variance of x1 plus x2 or whether you are talking about variance of x1 minus x2, both will be vx1 plus vx2 because this term is gone. Okay, the variance terms were in any case additive in nature, so they will get preserved on the right hand side in the same way, and the covariance term will disappear away because it is actually 0 since they are independent variable. And this is the most general formula, the most general, the last one, variance of ax1 plus bx2, which will be a square bx1 plus b square bx2 plus 2ab times covariance of x1 comma x2. Okay. Now let's come to covariance matrix. So just a representation of writing the different variances and the covariances between the two variables. So let's say we have, for a bivariate only, let's say there are two components, x1 and x2. So this diagonal row, I will not call it, I'll just call it the diagonal entries. So this diagonal represents covariance of the variables with respect to themselves. Okay, you can see that this is x1 over here also and x1 over here also. So the first diagonal, the principal diagonal, represents the variances always. In a covariance matrix, the principal diagonal always represents the variances, and these are the covariances. And of course, these values will be same or different. These values will be same or different. Same, absolutely. Absolutely. Okay, now how do we interpret correlation? And after this, I'll come to a very interesting discussion where we'll compare correlation and slope. So this part of the discussion, I mean, till now, the chapter that we have started, it is a bit theoretical, a bit boring, but be patient, I'll say, because there are a lot of interesting discussions coming up, not only in this chapter, but also in linear regression, especially. So how do we interpret correlation? See, this indicates a very strong positive correlation, a very strong positive relationship. So both the variables are moving together very strongly. They are very close to the straight line, right? And if the correlation is say 0.23, it indicates a very weak positive correlation. Very weak positive correlation. Okay, rho is equal to 0.23. Similarly, for negative side also, you can have a very strong negative correlation or a very weak negative correlation. What about perfect correlation? When perfect correlation will happen, all the points will lie on correct, this straight line only. So this is a perfect positive relationship. This is a perfect negative relationship. Now, what is the difference between correlation and slope? Are they same? Because we know there's something called as slope also. We have learned this in our school days also. And slope measures not but the steepness of the straight line. That's it. So what is the relationship? See these two diagrams. In the first case and the second case, whose slope is higher? The second one or the first one? Second one. So the first slope is, let's say, 0.3 and the second slope is 0.75. Whose correlation is higher? Can you tell me? Very good answer. Correlation is same in both the cases, even though slopes are different, because as long as they are lying on the straight line, because correlation measures the strength of the co-movement of the variables with respect to each other. So steepness does not matter. They are still moving together in a straight line. Okay, so in both cases, correlation is equal to 1. So please remember this distinction. Correlation is not the same as slope. Although they might, in fact, we have a separate slide, separate section also in our videos where we have discussed the differences, 4 or 5 differences between slope and this correlation. But from the exam point of view, only this understanding is enough, I'll say. Now, covariance, correlation, and independence, of course, when random variables are independent, they must have zero correlation for sure. But is vice versa true? What do you think is vice versa true? Is it guaranteed that if they have zero correlation, they will be independent? No, vice versa is not true. Because the correlation that we are talking about till now is a measure of linear dependence. It is linear correlation. Although we'll discuss other measures of correlation later also, even those will be based on linear relationships. Spearman's rank correlation, Kendall's tau, that is discussed in today's 12th chapter. And we'll discuss some examples also how to calculate Kendall's tau and Spearman's rank correlation. So correlation is a measure of linear dependence. But there can be some other type of dependencies, non-linear dependencies. So for example, if there are two variables, one is x1, which is normally distributed, standard normally distributed, and the other variable is x2, which is equal to x1 square. So there is a direct dependency. But if you calculate the covariance between them, you will find that the covariance is equal to 0. So there is a possibility that even with some kind of dependence, the covariance can be equal to 0. That will happen when the variables are non-linearly dependent. They might not be linearly dependent. Okay. Now, what are IID variables? IID variables are a very important class of variables. You'll hear this a lot of times, in part 1, part 2, numerous times. IID, independent and identically distributed. So IID variables are those variables if each random variable has the same probability distribution and all are mutually independent. So basically, you are generating all the variables from the same underlying distribution. You are generating all the variables from the same underlying distribution. Is it clear? Is it clear? You are generating them from the same distribution. That is very, very important. So let's say you take a normal distribution. So if you are taking out continuously variables, okay, then they are from the same distribution. But they also have to be independent of each other. It means one trial should not influence the other. So if you are taking, say, one outcome out randomly from a almost normally distributed, say, data set, you keep it back and then you take another out independently. So they will be IID variables. So is the idea behind IID clear? Same underlying distribution and mutually independent of each other. Shall we proceed to their features? Basic idea, I just wanted to ask you, is the basic idea clear? Okay. To everyone? Is the basic idea clear? Okay. So remember that they have the same moments. Since they are independent of all each other, they have the same moments. And one very important property which will be discussed again and again. The expected value of a sum of IID variables is n times the expected value of each variable. Again, I'm repeating, the expected value of a sum of n independent IID variables is equal to n times expected value of each variable. Now you can ask me a counter question over here. You should ask me, why will expected value of each variable be same? What should be the answer? Tell me. Why I have simply written
Because they
as
are
mu over here?
independent.
Exactly. The underlying distribution is same, right? So that underlying distribution is having some mean, and that is the expected value of each variable. So since the underlying distribution is same, that distribution is having this mean of mu. Also, another property is that variance is also scaled n times. Variance is also scaled n times. Mean is also scaled n times. Variance is also scaled n times. And later on, we'll see in QTA 12 today that since variance is scaled n times, standard deviation is scaled root n times. And that is a very important property when we discuss VAR, value at risk. Okay, fine. That's it for this particular lecture. So we'll take a very short break for 5 minutes. Let's be back at 2:57. Is that okay? And do not, that is my recommendation, unless and until it's very urgent, try to attend till the end, because it will help you a lot, not only from a revision perspective, but also for building your exam temperament. So please stay till the end. There will be some phases where the content will be a bit boring. That is how the curriculum is. But there will be a lot of interesting discussions in between. Hypothesis testing in regression. In fact, in time series chapters, where I think candidates have a lot of difficulty in absorbing time series chapters. So we'll discuss some very key points, in time series chapters today. Not in detail, but at least from a conceptual point of view, so that it is clear to you guys. So 2:57. Okay. Okay, so let's resume. Let's resume with sample moments, the 5th chapter. Now the mean estimator. Mean estimator is defined like this: 1 over n summation of xi. Again, see, if you remember, I mentioned that if suppose there are cases where equally weighted is not given, you need to make sure that you are taking the probability weighted average. Over here, it's the simple weighted average because we are assuming that the probabilities for all outcomes are the same. So this is the mean estimator, and this is the expected value of the mean estimator. The expected value of the mean estimator is same as the population mean. The expected value of the mean estimator is same as the population mean when mean is constant. Ritman, sure. I mean, as I said, doubt solving might not be possible if it's not related to current examples, but definitely you can do one thing. You can message us on Telegram, okay, or WhatsApp, and we'll try to get your doubts. So don't worry. And this is for everyone who's attending this session. If you have any doubts also after the session or any pending doubts that you're having, please feel free to post your doubts. Okay, there's a actually separate section, a discussion section which you'll have in this LMS. So against this lecture only, open the discussion section and post your doubts. We'll get it solved. Don't worry. Okay, on the forum. So the expected value of mean estimator is same as the population mean. Variance of the mean estimator is the population variance divided by n. These are points which you have to remember, okay, from the point of view of the exam. Expected value is same as the population mean. Now, bias of any variable is equal to expected value of that variable minus the true value of that variable. So for mean estimator, the bias is actually 0. So that is why it is called as an unbiased estimator. Since its bias is 0, it is known as an unbiased estimator. Also see one more thing you can observe over here, that as n tends to infinity, the denominator over here, as n tends to infinity, the variance of the mean estimator tends to 0. Now, one word of caution I want to throw over here is that variance of the mean estimator is something which is different from the population or sample variance. That is completely different. This is the mean estimator that we are talking about. We have estimated the mean. We have got an estimator of the mean. Now, for that estimator, we are trying to find out these parameters, the expected value, variance, and all those things. Okay. Right now, we cannot go into details. We've discussed this in the class and the videos. But right now, just remember that there's a difference. Then comes the variance estimator. Now, this is how the variance estimator is computed. But the problem is that the variance estimator is biased. It is having a bias of negative sigma square by n. In fact, in the previous version of GARP book, I think in 2020 or 2021, the bias was incorrectly written as sigma square by n, and we mailed them that time in 2020 that it is incorrectly written, and they have corrected it to negative sigma square by n. So to correct this bias, instead of n, what do we divide it by? What do we divide it by?
n minus 1.
N minus 1. This becomes your unbiased estimator of the variance, and this is your sample. This is how we calculate the sample variance basically, and this is how we calculate the sample standard deviation. Now next comes a very important parameter, which is standard error. Now I discussed earlier that the variance of the mean estimator was equal to sigma square by n. Now the standard deviation of this mean estimator is nothing but the standard, whatever the term that you have heard many times, standard error, standard error, standard. So what is that standard error? Standard error is nothing but the standard deviation of this mean estimator, which is sigma by root n. Okay, so I'll just give you a short explanation right now. We have given a very detailed explanation. I'll give you a short one right now. See, what is exactly happening here? Estimator, variance of estimator, then variance of sample, variance of population. What are we talking about right now? No, not the variance estimator. The standard deviation of the mean estimator. See, variance estimator is different. So, Shujant, okay, this is the variance estimator. Got it? This is the variance estimator. So what is meant by estimator? We actually, since we are not able to find out the actual variance of the population because maybe the data set is huge. So we take out, or maybe it's because of some other logistic reasons, we actually try to find out or project or estimate the variance using a small sample size. So that is known as the variance estimator. But this is the variance of the mean estimator. So when I say variance of the mean estimator, yeah, you got it, I understood. So the variance of the mean estimator means what? You will have a distribution of different means. And for that distribution, you will also have a standard deviation and a mean. Understood? So the standard deviation of that distribution of the means, which we call as sampling distribution of the sample means. So basically what is happening, try and understand. Let's say you have a population of size, say 1 billion. You are not able to perform your calculations on that sample. So you take a small sample every time and you find out a mean every time. Okay? So let's say you do this sampling 50 times. The sample size is say of 200. You take out 200 samples each time. 200 observations, sorry, each time, not samples. 200 observations each time. And you do this 50 times. Can you tell me how many means you will get in total? How many means you will get in total? Very good. 50 means, not 200, 50 means, because this is the population, let's say, okay. 1 billion observations are there in the population. So what you do, you take out small samples. Sample size is equal to 200. And you do this sampling 50 times. You do this sampling 50 times. So obviously you will get 50 different means of each sample. So those means will also have a distribution, agreed or not? If you have 50 different means, then those means will also have a distribution, right? You can put them into any distribution, correct or not? Because it's not a single observation. Any data set which is having say 50 observations, you can have a distribution for that, right? So the distribution of those means is known as sampling distribution of the sample means. And the distribution, let's say it is something like this. Say there are 50 observations. So 1, 2, 3, 4, something like this distribution you build. Okay. Maybe middle values are higher, something like this. So this is the distribution which will have a mean and variance, correct? So we are talking about the variance of the mean estimator. It means we are talking about the variance of these 50 means. Is it clear now? Is it clear now? Okay, to everyone? Okay, fine. So standard deviation of the mean estimator or any other estimator is known as the standard error. So this is what standard error is. Standard error is nothing but standard deviation of the sampling distribution of sample means, or simply the standard deviation of the mean estimator. Okay. Now, if the returns are IID, then we have already seen earlier in the last lecture that the return scales with n. If one period return is mu, n period return will be n mu. Variance also scales with n, correct? So standard deviation will scale with root n. And this relationship is true even if returns are not IID but uncorrelated. So the above relationship, is true, approximately true, even if returns are not IID, but even if it is given to you, returns are uncorrelated. Still, you can apply these two scaling effects where the n period mean return will be scaled by n. So it will become n mu, and the n period variance will also be scaled by n. It will become n sigma square. N period standard deviation will be scaled by square root of n. Now, what is the blue mean estimator? If the mean estimator is the best linear unbiased estimator, blue, of the population mean when data are IID. So blue is actually a very desirable property for an estimator because it will establish that the estimator is the best estimator. Best means it is having the smallest variance. It is having the smallest variance. So best means smallest variance. I'll write it over here. Best means smallest variance. Wait, let me do one thing since the handwriting, because of the incorrect mapping of the pen. This handwriting is not coming out correctly today. Yeah, me now. So best means smallest variance. Then you have linear. L means, of course, linear. Yeah, this is much better. So L means linear, and unbiased, we have already seen what is unbiased. Okay, so mean was unbiased because the expected value was equal to the actual value. There was no bias. So linear means what? Linear means this can be expressed like this. Summation Wi xi. So basically linear simply means linear transformation. That's it. Means there should be no power of 2 or 3 or 4. The power should always be 1. For all the xi's, the power should be 1 and it should simply be a weighted average, a linear weighted average. That is the meaning of linear over here. Unbiased we already know. Okay. Then large sample behavior of the mean. If suppose the data are IID normally distributed, see, even though these portions might seem a bit boring, but since theoretical questions are asked a lot, so be very attentive and try to listen as much as possible. The mean estimator is also normally distributed if the sample size is large enough. So we are talking about law of large numbers over here. So when law of large numbers, this law of large numbers, it establishes the large sample behavior of this mean estimator. And it provides some conditions where the average converges to its expected value. So when this LLN applies to an estimator, the estimator is said to be consistent. What is the meaning of consistent? Consistent means that when n tends to a very large number n, very large number, the bias of the estimator tends to 0. Makes sense, right? It makes sense. Because see, if n is very, very large, now there are two aspects. N can be interpreted as sample size, or it can be interpreted as number of times you're doing the sampling. Over here, it should be number of times where you're doing the sampling. Okay. So bias tends to 0. Because finally, the number of times you are doing the sampling will automatically become the sample size of that sampling distribution of the sample means. Because there will be 50 means in that case. So then there will be 50 such means. So then n will become 50. So that is why n is nothing but the number of times you are doing the sampling. Also, when n tends to infinity, the variance tends to 0. Bias also and variance also. So a very practical example we always discuss with our candidates is the example where we consider two cricket players. Okay. So law of large numbers applies everywhere in most of the situations wherever we have statistically relevant information, which can be, of course, numerically encoded. Now, let's say we have two cricketers. Sachin Tendulkar, okay, is playing his 200th test match. And Sachin's average just before the test match is, let's say, 55.41, let's say, hypothetically. So, irrespective of the number of runs he scores in his last innings, will his average change too much? Will his average change too much? Right, so there is very little chance, right? Almost negligible chance that his average will change to a large extent. Okay, maybe by 0.2, 0.3 max. I'm even that is theoretical, because even to change the average from 55.41 to 55.61, even for a 0.2 change, he'll have to make a lot of. So theoretically, although it will be possible, but practically even those many runs are not possible. So his average will not change that much. But if it's a player who's, say, playing only their, say, third match. Say Karun Nair was playing his third match. Okay, Karun Nair was the one, right, who scored triple century. His name was Karun Nair, right? 3 years back. Yeah. So let's say if Karun Nair was playing his second or third match, his average before the match, I mean, he has just scored a triple century and his average has become quite high, let's say, okay, after 2 matches, his average has become 100, okay. So what is the chance that his average will fluctuate much more as compared to Sachin's average, right? Sachin's average will fluctuate very, very minutely, but Karun Nair's average will fluctuate heavily depending upon the runs he scores. Until he scores exactly the same runs as his average, whose probability is very low. So the point is that this same analogy which we are applying, the theoretical foundation of this analogy lies in the law of large numbers. When the number of times you are doing the sampling is very high, then your bias as well as variance, they are automatically reducing, they are tending to 0. Okay, and in that case, the estimator, and if this happens, then the estimator is said to be consistent. If this does not happen, even if suppose n is increasing and still your bias is not tending towards 0, your variance of the mean estimator is not tending towards 0, it means that the estimator is not consistent. Okay, now let's come to the central limit theorem. So for the central limit theorem, first I'll draw a diagram of a normal distribution. Let's say this is a normal distribution with a mean of mu and a variance of say sigma square by n. Okay. Now, in case of the central limit theorem, but I think the diagram will be drawn over here again. I'll just check. It states that given a sufficiently large sample size, we define sufficiently large sample size as a sample size of n greater than or equal to 30. From a population with mean mu and variance sigma square, then the sampling distribution of the sample means, the same distribution that I was talking about, it will obey 3 properties. It will follow a normal distribution pattern. It will have a mean approximately equal to the population mean, and it will have a variance approximately equal to the population variance, sigma square by n. So, irrespective of the underlying distribution, if you have a sufficiently large sample size from a population with mean mu and variance sigma square, then the sampling distribution of the sample means will follow an approximate normal distribution pattern, with the mean being approximately equal to the mean of the population and the variance being approximately equal to sigma square by n. Now, earlier, remember I mentioned that n can be either the sample size or it can be the number of times you are doing the sampling, right? Remember, in both cases, the variance as well as bias will reduce. Even if you are having a large sample size, let's say you have a population of 1 billion and you choose a sample size of only 100, then there is a very good chance that the results will be very poor, okay? And then you do the sampling only 50 times. It will not give you good result. Either the sample size that you have to choose is very large, at least 1 million if you're doing the sampling only 50 times, or if you are choosing a small sample size, say 200, 300, then the number of the number of times you do the sampling should be so large that finally your results actually are close to accurate. Okay, so either of these conditions should be true. It is actually an ideal condition when sample size is also sufficiently large and the number of times you do the sampling is also sufficiently large in statistics. So yeah, this will be the resulting distribution. So remember, what are the premises of the central limit theorem? Given a sufficiently large sample size with a population mean mu and variance sigma square, I'm repeating it for the 3rd time because it is extremely important from the point of view of the exam. The underlying distribution will follow a normal distribution pattern with mean equal to mu and variance equal to sigma square by n. Okay, and we have actually proved this using some examples, verified this using some examples. But the premises are very important. Now, median, we all know what is median, 50% quantile. We have already discussed it, so we'll not discuss it again. Interquartile range is also been discussed. Okay. Now, 2 features make the quantiles very attractive. First, they have the same units as the underlying data, so they are easy to interpret. Percentage is expressed in percentage or dollars or whatever units. The quantiles will also have the same units. Second, they are robust to outliers. Now, this is a point which we can easily verify. Let's say if you have, say 5, a very simple example I take. So 1, 2, 3, 4, 5. What is the mean of this distribution, guys? What is the mean? What is the mean of this distribution? Equally weighted. Assume equally weighted, okay? Assume equally weighted. I'm asking about the mean. 1, 2, 3, 4, 5. Correct. 1 plus 2 plus 3 plus 4 plus 5 by 5, which is 3. What is the median? Median is also 3. Okay. So let's say now what I do is I add an outlier to this distribution. Say 200. What is the mean of this distribution? What is the mean of this distribution now? Equally weighted again. What is the mean of this distribution? 35 point something, right? Okay. What is the median of this distribution? The average of these two, correct? Okay, now tell me, is the new mean of 35.83 in any way a good representation of the sample? Is it even close to any of the points? Not even 1, 2, 3, 4, 5, not even 200. Are you seeing what has happened to the mean now?
I didn't catch that.
Oh, what happened to Siri? I was asking you guys. Anyways, so is it a good representation? Is it a good representation, guys? 35.83 of the sample points? No. But is median still a good representation? Is it still close to these 5 points at least? Right? Even, yeah, median is still, even though it's not close to the outlier, it will not be. So which one is more robust to outliers? Mean or median? Which one is more robust to outliers? Obviously, median is more robust to outliers. Okay, so that is the very attractive property of median. Now, this is the formula for sample covariance estimator. Again, the crux is that you have 1 minus n by, 1 over n minus 1. So, n minus 1 is in the denominator, which gives you an unbiased estimate instead of n. Then, in case of multivariate moments, what you can do is you can actually extend the same principle that we had in case of univariate, where we had skewness and kurtosis. Over here, we can have cross moments. So we'll have, for pth moment, we'll have p minus 1 different measures. So when we are talking about pth cross moments or cross pth moments, there'll be p minus 1 different measures. So what I mean to say is that there will be no cross means. Why no cross means? Because it is the first moment. So p is 1. So p minus 1 is 0. So 0 cross means. There is one cross variance, which we call as covariance. There's only one covariance, right? Between two observations, two components, if you have two components of a bivariate random variable, x1, x2, there's only one covariance, correct? There's not more than one covariance. So since we are talking about the second degree, the second moment, so p minus 1 is 1, there is only one covariance. So this can be verified over here also. What about skewness? How many co-skewness will be there? 2 co-skewness will be there. Why? Based on this principle, skewness is the third moment, correct? Third standardized central moment, if you remember. So if it is the third moment, it means p is 3. So p minus 1 is 2. So there are 2 co-skewnesses. And how many co-kurtosis measures will be there based on this rule of thumb, I should say, or convention? How many co-kurtosis measures should be there according to you? Very good. It should be 3. So there is one covariance, 2 co-skewnesses, and 3 co-kurtoses. Okay. Now in the there is an example in the video. We have done that. If you want, we can add that in the PDF also, where we have interpreted the co-skewness and co-kurtoses with respect to gold prices and stock prices and bond prices and crude oil prices. So 4 instruments were taken and the interpretation was done properly. Okay, you can refer to the GAR book also for that. The same example was taken. Okay, or if you want, we can add it in this revision PDF only. Fine. Okay, so let's take a short 5-minute break. Can resume at 3:27. Hypothesis testing is a very important topic. So we'll discuss from 3:27. It might take a little more time than the previous topic. So, but we'll try to cover within 40 minutes hypothesis testing also. So we'll be back at 3:27. Okay, let's start hypothesis testing. Oh, this also I think we'll cover quickly. Let's discuss some examples because the standard normal distribution and everything has already been covered. Okay, now confidence intervals. Again, we are not discussing this in detail, so we are relating specifically to direct questions or concepts which can be asked in the exam. So what are confidence intervals? Confidence intervals, they take on the following form, because confidence intervals we already introduced in when we discussed normal distribution, right? 95% confidence interval, 68, the 99 and 90. So they take this form: point estimate plus minus reliability factor times standard error. Okay, now let's say if you are having normal distribution with a known variance, then a confidence interval for the population mean can be calculated like this. In this case, the reliability factor becomes the critical value of the Z statistic. And since we are talking about confidence interval, are we interested in one-tailed critical value or two-tailed critical value? What do you think? Generally, we are interested in two-tailed critical value for a confidence interval, but you would be surprised to know that even confidence intervals can be created from negative infinity up to a particular value. So in fact, we can also have one-tailed critical value usage as well. Okay, although those kind of questions are not asked in the FRM curriculum, but even that is possible because the interval means, I mean, you can also start from negative infinity up to a certain point. That is also an interval. So this is what a confidence interval for a normal distribution will look like. Now, which critical value to use, Z or T? There's always a choice between the Z statistic and the T statistic. Now, this is a table which summarizes what kind of statistics should be used, which is preferable, which is permissible. Now, if distribution type is normal and population variance is known, then in that case, irrespective of the sample size, because you already know that the distribution is normal, so there is no problem with the sample size. You can directly use the Z statistic. Population variance is also known. So you can also use the Z statistic. If the distribution type is non-normal and the population variance is known, now in that case, you have to check what is the sample size. If sample size is greater than or equal to 30, then based on the central limit theorem, you can approximate that it will behave like a normal distribution. Okay, so in that case also Z statistic can be applied. But what if n is less than 30? In that case, you cannot apply any of the statistics because the distribution type is non-normal and n is less than 30. So it is not possible for you to apply any statistic. If the distribution type is normal but the population variance is unknown, in that case, this is preferable. T statistic is preferable. But Z is also permissible. Okay. And in this case, if n is less than 30, then you have to use the T statistic. If the population is non-normal, population variance is unknown, sample size is greater than or equal to 30, again the same thing. T statistic is preferable, Z is permissible, and if n is less than 30, then you cannot apply any of the statistic. Now remember one thing, that in this particular chapter, we are only dealing with Z stats. T statistic hypothesis testing is going to be discussed and is applied in case of hypothesis testing of linear regression parameters, slope and intercept. So when we test for slope and intercept in case of linear regression, then we use the t-test most of the time and we use the critical value of the t statistic. Okay. Now, although it is not necessary, but the null hypothesis H naught is generally constructed which the researcher wants to reject. So for example, if I'm a researcher and I believe that the mean return of any stock is greater than 10% or say 5%, then how will I construct the null hypothesis? If I believe that the return is greater than 5%, that is my belief. So I will construct the null just opposite to that. So this will be my null hypothesis. HA less than equal to 5 or 10, whatever you, if you believe 10%, it will be 10%. Got it? So less than equal to 10% or 5%. Okay. Now, based on the results of the test, if there is a very high probability of the return being greater than 5%, then you can reject this null. And you will say that, okay, you were reasonably confident that your return, your belief is not incorrect. Your belief is correct. Okay. Now, one thing is very, very important. The null hypothesis is never accepted. Never. We never say we accept the null hypothesis. It is either rejected or fail to reject. You never say, if you could not reject it, you will never say you accepted it. You will say you failed to reject it. I always use a courtroom example for this, and it's the best example, I think, to start with, because when any accused is not convicted, if the accused is coming to the court and the accused is not convicted, then what does the court pronounce? Does the court pronounce that the accused is not guilty, the accused is innocent? The court, in fact, you've seen many movies, Hindi, English, or any other language, the court never pronounces that the accused is innocent. We are letting go of the accused because we believe that the accused is innocent. Never. The court says that yes, due to lack of reasonable evidence. Okay, because the accused has to be established as guilty beyond a reasonable degree of doubt. So the court will never say that the accused is innocent, that's why the court is releasing the accused. No, the accused, there is a lack of evidence. The prosecution may be failed to prove that or give sufficient evidence. So due to lack of evidence, the guilt of the accused cannot be proved beyond a reasonable degree of confidence. Okay. The alternative hypothesis is written in exactly opposite terms as the null hypothesis and is concluded if there is enough evidence to reject the null hypothesis. So in this case, alternative will be greater than 5%. Okay, now two-tailed test or a one-tailed test. So let's talk about two-tailed test. Let's talk about a 95% confidence or a 5% significance two-tailed test. Now, earlier, the confidence level was if 95%, then this 5% was termed as significance level. In the new curriculum, they have termed this as the test size. So remember, whether it is significance level or the test size, the implication is the same. And I don't think there was any reason to change the usually adopted convention of significance, because mostly in most of the cases it's mentioned significance level only in most of the other books. So I think it would have been better if they continued to use significance level, but probably they will use test size in the exam. Now, what are the keywords in the question which you can use to identify that this is a two-tailed test? These are the keywords. If the question says test if it is different from something, test if it is not equal to something, test if something had an effect or not. So had an effect can be both positive effect or negative. Not equal to can be on both sides, greater than or less than. Different from also can be on both sides. So are you getting the points? These are the keywords which will help you identify which kind of test we are talking about. Okay, and this region will be your fail to reject region. This region will be your reject region. And of course, we'll discuss one example to make things more clear. So this is the idea behind the two-tailed test. Now let us discuss the idea behind the one-tailed test, specifically the right-tailed test. The same idea can be extended to a left-tailed test also. What are the keywords? The keywords will be for a right-tailed test greater than, and for a left-tailed test less than, or at least, or at most. All these keywords will be there. Even for a right-tailed test, the keywords can be less than. You have to be very smart and choose. You'll be able to understand when you look at the question carefully. You'll be able to understand. So this is your fail to reject region. This is your reject region. Now these are the steps. Steps I'm not going to go in detail. In fact, I have curated the steps. I mean, these are not the standard steps which are given in the curriculum or any other book. So I've actually modified the steps a little bit so that steps are included properly, so that you can understand when to go back to which step. Okay, select the appropriate test statistic, specify the critical value of the test statistic based on the significance level stated in step 2. Okay. Then, and also based on the notion of the test. So whether it is two-tailed test or one test. So these things are important. Then state the decision rule regarding the hypotheses based on the critical values specified in step 3. Again, you go to step 3. Then sample test statistic. Then make a decision based on which two steps also are given. Then draw a conclusion based on which two steps. So this is a modification. Go through this once you get the PDF. Okay. We'll directly go to the example. So let's discuss only one example. And in the PDF, I'll be sharing 2 more examples. Okay. A left-tail test also and a two-tail test also. So read the question. An electric bulb manufacturer claims that the average lifetime of bulbs produced by it is more than 36 months, with a standard deviation of 3 months. A random sample of 50 bulbs was taken and the average lifetime of those bulbs was found to be 37 months. Test the manufacturer's claim at 5% level of significance. So tell me one thing. If suppose you take a random sample, the claim is that the average lifetime is more than 36 months. If you take a random sample and if you find that the average lifetime is 33 months, will you even perform the test? Tell me. Will you even care to perform the test in that case? Because see, we always do hypothesis test and all, but do you need to perform it every time? No. In any case, it's the claim has been violated in the sample only. You only perform a hypothesis test. I'm repeating, Rohit. See, you see, this is the claim. More than 36 months. Okay, Rohit, this is what manufacturer is claiming. You are the person who's testing the claim. Okay. You go there and you take a random sample of 50 bulbs. You test the average lifetime of those bulbs and you find it to be 37 months. But if I ask you that instead of 37 months, if the average lifetime was 33 months, would you even perform the test? Do you even need to perform the test? No. Because the claim is 36. You will. Yes, I will repeat the keywords. Absolutely, I will name it. So why this is a one-tail test, we'll discuss that. So the average lifetime, if it is found to be 37 months, it means that you believe that, yes, okay, there is some merit in the manufacturer's claim. The manufacturer is claiming more than 36. I've got 37. So there is some merit. Let's test this claim. Okay. Now, what are the keywords which will tell you that it is a one-tail test? What are the keywords? What did we discuss, Niharika? These were the keywords over here. Greater than, less than, or more than, less than, at least, at most. Okay. So can you see some related keywords in this example? Can you see some related keywords in the first line itself? Very good. See, Niharika, got it? Got it, Niharika? Can you see this? More than? So the claim is that it is more than something. It means you have to test in the right tail. Got it? Okay. So you will perform a right tail test. Now you will test and you start by using the first step. So let's go back now. That's why I did not discuss. So we'll discuss it using the example I said. So first step is state the hypothesis. State the hypothesis. What is your null? What is your belief? Tell me. If as a researcher you have found some merit in the manufacturer's claim, your belief is maybe the manufacturer is correct. Let's test it out. So you also start to believe that, yeah, the average lifetime is more than 36 months. So what will be your null and what will be your alternate? I said that generally the null should be something that you want to reject. Generally. So let's go with the general convention.
Null is less than 36 months.
Yes, mu is less than equal to, this is what you want to reject. And this is what you want to believe, right? So again, just like I mentioned my way for writing conditional probability, I mentioned that I write given first when I write conditional probability today, earlier in the conditional probability discussion. So in this case also, I tend to write the alternative hypothesis first. When as a student, I am saying, when I started studying FRM for the first time, in 2011, I actually wrote the alternative hypothesis first because it made me more comfortable. I don't know why. So if it works well for you, then it's great, because whatever you believe, that you have to write in the alternative, and the opposite you write in the null. So we know that it is a right tail test. So we'll draw this diagram accordingly. Okay. Next step. Next step is to specify the level of significance test size. Is it given in the question? What is the test size? Even if it's obvious, please say.
50 bulbs.
Correct. No, test size. Significance level.
5%.
5%. See, that is why I said they should not have changed it to test size. They should have written significance level only. So test size is 0.05 or significance level is 0.05. Third step, select the appropriate test statistic and specify the critical value of the test statistic based on the significance level stated in step 2. So we will specify the critical value based on 5% significance level and also based on the notion of the test, whether it is a two-tail test. So we'll give a two-tail critical value. If it's a one-tail test, we'll give a one-tail critical value. Now tell me one thing before we proceed. I mean, how to decide which test we will use? This table, refer to this table for the test. This table. So distribution type, population variance, and sample size. Now let's go to the sample size. Is sample size more than 30? Is sample size more than 30? Yes, it is 50. And also, is the population variance known? Also, yes, because it is given that this is for the population only. It is not for the sample. See, for the sample, standard deviation is not given. It is given for the population only. The manufacturer is claiming that all the bulbs are having the average lifetime of all the bulbs are having a standard deviation of 3 months. So you know the population variance, you know the population standard deviation, and you also know that the sample size is greater than or equal to 30. You are free to use the Z test. Okay. Even if that is not the case in the exam, if they don't give you the T table, perform the Z test only. So you have the Z test. And can you tell me what is the critical value of the Z statistic at 5% level of significance, one-tailed critical value? We will use the one-tailed critical value. One-tailed critical value. What is the one-tailed critical value?
1.625.
Very good. 1.645. So 1.645. So this is 1.645 over here. So graphical illustrations also we are giving to make you understand properly. Now, what is the decision rule? Next step is the decision rule. The decision rule regarding the decision rule is that this is the reject region, correct? So reject H0 if my sample test statistic is greater than 1.64. How do I find out the sample test statistic? It's a Z test. So this will be my sample test statistic, X minus mu naught divided by standard error of X. How do you find out the standard error of X? How do you find out the standard error of X? First, let's find out the denominator. Denominator is Sx, standard error of X. What was the formula for standard error?
Standard deviation by square root of n.
Sigma by square root of n. Absolutely correct. Okay. Since sigma is known, you will use sigma directly. If sigma was not known, you could have used the sample standard deviation. But the first choice is always sigma. So sigma by root n, which is 3 over root of 50. So 0.4242 is your Sx, the standard error. Okay, so let's find out the sample test statistic. Now tell me what will be X. See, mu naught is the hypothesized value. Remember, mu naught is the hypothesized value. So mu naught is something against which you are testing. And it is given in the first step only. Remember, if you have to find out mu naught, so there's always a confusion sometimes I see in the minds of the candidates, which is X and which is mu naught. Remember, mu naught you will pick from the first step, from the hypothesis. So against the hypothesized value. So mu naught is 36. And X you will check from the claim. So what is the claim? Sorry, X you will check from the sample. Mu naught is from the claim or the hypothesized value. X is from the sample. So what is X? Absolutely correct, Tanuj. It is 37. So I'm repeating once again. X you will check from the sample, the data that you have got from your sample. Mu naught will be your from the claim or the hypothesized value, whatever you want to call it. So this will be your STS. 37 minus 36 divided by 0.4242, which is 2.357. So this is your 2.357. Is it in the reject zone or fail to reject zone?
Reject zone.
Reject zone. So since 2.357 is greater than 1.645, so we will reject the null. Is our question complete or is still one step remaining? This is only step 6, guys. Reject or fail to reject is step 6. The last step I mentioned, draw a conclusion. So what will be your conclusion? Very good. Yes. So the conclusion will be that you have sufficient evidence to claim. You never see. You should never, I mean, being a statistician, you should never give a layman kind of claim that, yeah, manufacturer's claim is correct. Questions might be asked like this in the exam. Even options might be like that. So that is okay for you. But you should always claim like this, that you have sufficient evidence to validate the manufacturer's claim at 95% confidence. So this is how you should frame the answer. Now, a few points I want to discuss regarding standard error and sample test statistic over here. See, if suppose the sample size was decreased to say 35, let's say. If I decrease the sample size to 35, would you be more confident in your results or less confident? What do you think? Your degree of confidence will reduce, correct? Do you agree or not? Because the larger sample size you have, the better it is for you. And mathematically also it is justified. You see, with standard error, what will happen if n's value is decreased? What will happen to standard error if n is decreased? Can you tell me?
It will increase.
It will increase because it is in the denominator. So if this increases, it means the denominator increases. And if the denominator increases, what will happen to sample test statistic?
Decrease.
It will decrease, absolutely. So because of the sample size decreasing, your sample test statistic also might decrease, and there is a chance it might fall into the fail to reject zone. Do you agree or not? Because the more number of bulbs you have, the standard error is lesser and lesser, given that sigma is constant. Okay, so your 2.357 over here, maybe your next value will become 2.5 if the sample size is 60 bulbs. But what if the sample size is 35 bulbs? It will come close to 1.645. It may even go to the left of 1.645. So in that case, you will fail to reject the null if that happens. Okay. So tell me one thing, if you fail to reject the null, hypothetically, what will be your conclusion in that case? That is what I want to ask. Give me a technical conclusion. Anyone who can say. Give me a technical, proper conclusion.
There is sufficient evidence to reject the null.
We have?
Not able to reject the null. So
Exactly. You will never say that manufacturer's claim is not correct. Okay. You will say that you don't have sufficient evidence to support the manufacturer's claim at 95% confidence. That is the best way to conclude. So that is why we never accept the null. We will never say that we have proved this. No. We don't have sufficient evidence to prove this. We have not proved this. Got it? So that is the whole point. Now, one more question I asked you in the beginning, that if suppose the average lifetime of the sample is 33, will you even test? You said you will not test, and you were absolutely right. Mathematically also it makes sense, because if instead of 37, if it is 33, what will happen to the numerator? It will become negative. And if it will become negative, it will always be in the fail to reject zone. So there is no point of testing the hypothesis. You will never be able to support the claim, right? So mathematically also everything is justified. Okay, so that is the whole idea behind hypothesis testing. Fine. Now, this is another question. I'm not going to discuss this right now. Okay. So I'm going to quickly go through it. It's a two-tailed test. You can go through it from the PDF. It's better, right? Because I think if we have discussed one question, let's proceed to the next part, right? So this is the same way. It's a two-tailed test. The only thing that I want to ask in this question, which keywords? Now, Niharika, you tell me which keyword is telling you that it is a two-tailed test. Come on. Which keywords are telling you, keyword or keywords? Niharika, please answer. If you are able to find. If not, then question is open to everyone. Because you had asked about keywords. Do you want me to go back to the keywords slide? I can, no problem.
Mostly.
Effect, very good. Okay, fine. Someone has already answered. Okay, fine. No problem. So it had an effect, right? So clear? Yeah. No, it had an, because see, negative effect means it is only on one side. It is given both positive as well as negative. Understood? So over here, you see, it can have a negative effect or a positive effect. But finally, the main keyword I'll say is this. Although over here also in the question it has been given, but if suppose even these things were not given to you, had an effect is a keyword because it can have a positive as well as negative effect. And if you go back to the keywords, you will clearly see that one of the keywords was had an effect. Got it? Okay. So let's move on to type 1 and type 2 errors. A type 1 error is rejecting the null hypothesis when it is actually true. And type 2 error is failure to reject the null hypothesis when it is actually false. Okay. And again, in the context of a courtroom example, if suppose an accused, anyways, I'll have to state the null and alternative, and I'll have to explain that completely once again. So I'll not go into that example. Just remember that rejecting the null when it is actually true is type 1 error, and failure to reject the null when it is actually false is actually type 2 error. Is it clear to everyone? Is anyone having any doubt in type 1, type 2 error? Do you guys need me to explain? Anyone who's having any doubt? Then only I'll deal with that example. Otherwise, I'll skip it. Shall we proceed to the next part? Oh, I mean, use of type 1 and type 2 error. Absolutely very useful. Because see, if you are performing a hypothesis, it is still a test, right? You are just being 95% confident. Right, Rohit? So yes, with Redman, I'm proceeding and I'm just explaining this point that why it is useful. So you are just performing a test. You are not giving 100% guarantee, right? Even you can be wrong. So maybe you actually, so let's take this example. I think it's a very relevant question. That's why we should discuss this. So let's say this example, okay. So you actually have rejected the null in this case. Okay. But then some other researcher comes and takes out another sample. In that case, the average lifetime is less than 36. Another researcher comes, the average lifetime is more than 36, but the Z statistic is, sorry, the sample test statistic is less than 1.645. Again, the researcher fails to reject. Another researcher again fails to reject. So it means your results were wrong. Understood? So it is possible that even in a hypothesis test, you might be wrong. So these errors are actually telling you, okay, that if suppose you are rejecting the null when you should not have rejected. So if the court is pronouncing an accused guilty when the accused was innocent, let's say, in reality. I mean, again, it depends on what is your null and what is your alternative. Because in a courtroom example, we always presume, see, you might have heard this term that innocent until proven guilty. Any accused, if brought to court, that accused is always assumed to be innocent until proven guilty. So based on the prosecution and based on the defense, the null and alternative might be different, but there is always a standardization to it. we actually, when we construct the null, that is why I said when I have to go into that example, it will take some time. But just remember this, at least the last part of the example. I'll not go into the example in detail, but at least remember the last part of the example. So if suppose someone is innocent and the court has pronounced them guilty, they are making an error, right? And if someone is actually has committed a crime, which even the public knows, maybe there are some celebrities for whom we probably are aware, but the court did not have reasonable evidence, right, to prove that they are guilty. So that is another type of error. And again, depending upon what is your null and alternative, it will depend if it's a type 1 error or type 2 error. Got it? So just understand that if you are rejecting a true null hypothesis, it is a type 1 error. Again, I did not say accepting hypothesis. I said rejecting a true null. It means when the null is actually true. It does not mean I'm accepting the null. So don't get confused with the terminology. And the second one, if suppose the null is false, but you are not able to reject it, then it's a type 2 error. So that is the use. Okay, then the significance level is the probability of making a type 1 error. Remember that. So if the significance level is 5%, there's always a 5% chance of making an error. And probability of type 1 error is significance level. And power of a test is 1 minus probability of making a type 2 error. Okay. Now what is the p-value? The p-value is the minimum level of significance at which the null hypothesis can be rejected. And I'll tell you the usage of p-value also from the exam point of view. P-value is the minimum level of significance at which the null hypothesis can be rejected. So let's discuss these two cases, one tail and two tail. So in this case, you are having 5% on the right hand side, 1.645 is your critical value. Now let's assume that this is your sample test statistic over here. Say this is 1.8, just hypothetically I'm assuming. Okay. So if this is 1.8, then for any critical value, listen to this very carefully. For any critical value which is to the left of 1.8, you can reject the null or not? Tell me. For any critical value. Say this critical value is 1.645 in this case. Critical value can be, say, 1.6 also, 1.7 or 1 depending upon the confidence level. Okay. So any critical value to the left of 1.8, you can reject. So let's take a practical example. 1.645 is the one-tailed critical value for which significance level? 5% significance level. Right? Can you tell me what was the critical value, if anyone remembers, the one-tailed critical value for 2.5% significance level? Anyone who remembers? Even if you don't remember, you should be easily able to decipher, easily able to derive it right now. It's very good. Because see, for two-tailed, what happens? For two-tailed, this is 1.96 and this is minus 1.96, correct? So 2.5% area is over here and 2.5% area is over here, correct? So obviously, if I have 1.96 over here, then it means to the right of 1.96, you have 2.5% of the area, correct? Okay, so everyone is okay with that, great. Now tell me one thing. Can you reject the null at 5% level of significance? Yes or no in this case, if this is your STS? Can you reject the null? Can you reject the null at 5% confidence, significance, sorry. 1.8, the sample test statistic is greater than 1.645. Can you reject the null at 95% confidence? Why not? Obviously, yes, this is the reject zone, right, Sushant? The right side is the reject zone. Na? 1.8 is greater than 1.645. Correct, Sushant? Clear? Got it. But can you reject the null at 2.5% significance? 1.8 is less than 1.96. Can you reject the null at 2.5% significance? No. So reject at 5%, fail to reject at 2.5%. right? So it means that there is a value between 2.5 and 5, which is the minimum value at which you can reject, and that is known as the p-value. Okay, so basically any significance value to the left of 1.8, any critical value corresponding to a significance level to the left of 1.8, you can always reject them. Okay, and it is very easy to calculate. You calculate it based on the STS only, based on this STS only, or which we can also call as T sometimes. What is the formula? You simply find out the area to the right of this. This is your p-value. The area to the right of the black line is your p-value. Understood? Because as long as the area is to the right of this rejection region is to the right of and it includes 1.8, you can always reject the null hypothesis. But as soon as this area, I'm drawing another diagram. As soon as this area, let's say this is 1.8, as soon as the rejection region shifts to the right a little bit, now this 1.8 falls in the fails to reject region. So in that case, you will not be able to reject the null. Now, this p-value slide only, if you remember, those who have attended the classes, I think we devoted around 40 to 45 minutes only to explain each and every aspect of p-value. So it takes a lot of time, but I'm trying to explain the crux over here. Is it clear? Yes, you reject in black zone. Absolutely. So my point is, if the rejection zone shifts towards the right, you are not able to reject. Agreed or not? Right? If the rejection zone shifts towards the right of 1.8, you are not able to reject. Correct? So it means that the rejection zone has to come close to 1.8 first. And it has to exactly coincide with 1.8. It has to, this end point of the rejection zone, the left side, has to coincide with 1.8. And as soon as this happens, this is the minimum level of significance at which you can reject the null hypothesis. Understood? This area is the minimum level of significance at which you can reject the null hypothesis. So that is why, if you see, again, I'll explain this diagram once more. That is why if you see this example which we had, this was 1.8 and this was 1.96. So corresponding to 1.96, guys, this is the rejection zone, correct? So that is why you are not able to reject at 2.5%. Agreed or not? The rejection zone is to the right of 1.8. This is clear now? To everyone. To everyone, not only to one or two people, to everyone. Is it clear? In this case, since the rejection zone is to the right of 1.8, you are not able to reject because this is the diagram, guys. Let's go back. Let's revisit. Yeah. See, reject zone is this to the right hand side. And this is the fail to reject zone. Okay. So if the reject zone is to the right side of 1.8 in this example, will you be able to reject? That is my question. Will you be able to reject at 2.5%? I am emphasizing this point again and again because it is important. Will you be able to reject at 2.5%?
No.
No. But are you able to reject at 5%? Yes. Because 1.8 is in the rejection zone as far as 5% is concerned. Understood? So p-value is the minimum level of significance at which the null hypothesis can be rejected, and it is nothing but this area. Okay, so this is the formula. P-values, just look at the Z table. This is the formula. And for two-tailed, of course, you have to consider both the regions. Now, last part, testing the equality of two means. I'll not explain the theory. I'll not explain why how the hypothesis is transformed. I'll show you how to solve the question in the exam. Okay, directly. So see which test statistic has to be used. If suppose this kind of question is asked, you just remember that you have to use this test statistic, this one. What happened? I think there is a problem with respect to animation again. Let me just see. Yeah. Anyways, there's a problem with respect to animation. You see this part first. So this is the test statistic that you have to remember. Mu x minus mu y divided by sigma x square plus sigma y square minus 2 sigma xy divided by. Just a quick question. Why cap is there in all these values? Why a cap you can see? Can you tell me? Why there's a cap? Fast.
Those are
Yes,
claims.
yes, these are estimators from the sample. Very good. These are all estimators. These are all estimators. Okay. So if this kind of question is asked, consider two distributions that measure the average rainfall in city X and city Y. Means, variances, sample size, correlation, this will be given to you in the exam. Using this formula, you calculate the test statistic and then you compare it against the critical value and you directly say that the null hypothesis can be rejected. So when null can be rejected, it means the population means are not equal. Because if you see the hypothesis mu x equal to mu y can also be stated as mu x minus mu y is equal to 0. And this is your null. And the alternative is that mu x is not equal to mu y. Okay, so this is how you will perform this question in the exam. No, this will also be Z test. This will also be Z test. Unless and until they mention. Because see, I'll tell you why. The sample size and everything, if they because the data that has been collected, it is the average rainfall. This has been collected probably based on a data of 200 days. So 200 is a large enough sample to use a Z test. Okay, so just look at the null and alternative hypothesis and take a correct decision. Remember that if you are able to reject the null, the population means they are not equal. It means the average rainfall in city X and Y are not equal in this case. That is how the construction of this test is done. Very smartly, a equality test has been transformed into a equal to 0 test. Equality between two means has been transformed because see, again, I'm repeating. Mu x minus mu y. You are writing. Actually, the main test was mu x equal to mu y. So this was the null hypothesis. So either you test this or can you write the same thing as mu x minus mu y equal to 0? Yes or no? Tell me. Are these two statements identical or not? Are these two statements identical or not? Yes. Because if mu x equal to mu y, then mu x minus mu y equal to 0. Now, if you have rejected the null, it means you have rejected this. It means you have rejected this. Okay, so rainfall is not equal in both. Got it? So that is the whole idea. Now, one more thing which I want to add, that generally you will find that wherever we have written the null hypothesis, we have always included this equal to sign with it. Equal to sign, whether it is less than equal to or anything. So null sign, null hypothesis always contains equal to sign. Alternative hypothesis does not contain equal to sign. Either it will be greater than, or it will be less than, or it will be not equal to. So this is one of the keys in you can use to frame the null and alternative hypothesis. Okay. Fine. Okay. So we'll take a break for 20 minutes. We can be back at 4:30. Is that okay? Or a shorter break, as you say. I'm completely okay with both. 4:30 is okay. Shorter 15 minutes, fine. 4:25. Okay. At least revisit the concepts. Okay, Caroline is asking for 20. Caroline, actually, see, the content is very, very long, and I agree that, even if you are able to say 5 minutes, it will be better. It's already 4:11. So at least do one thing. We are going to do very important chapters, regression related chapters. So before you resume, at least have a quick brush up of the regression concepts and the formulas quickly, and we can resume at 4:25. 10 minutes. Is that okay, Caroline? Does it work? Does it work for you? 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. 4:25. Okay, fine. DMs are also being given. So anyways, let's start at 4:30, no problem. So 20 minutes. Fine, let's start at 4:30. Thank you. So we'll start with now QTA regression, QTA 7, sorry, linear regression. Okay, now linear regression, it assumes a linear relationship between any explanatory variable and a dependent variable y. Okay, so this is the relationship where beta is the slope or regression coefficient. It measures the sensitivity of y to changes in x. So how we interpret the slope coefficient in a linear regression? Basically, it is the change in y for 1 unit of change in x. So that is why sensitivity of y to changes in x. So remember that. And we'll modify the same interpretation in case of multiple regressors. Okay. Then you have alpha, which is the intercept, which is constant. And again, the interpretation of alpha is that the value of y, the value of the dependent variable, when x is 0. So obviously the expected value of error term is assumed to be 0. So if both these terms are 0, if x is also 0, then y will become alpha, right? So alpha is interpreted as the value of the dependent variable when the independent variable is 0. Okay, so just remember this. The interpretation of slope is nothing but the change in y for 1 unit change in x, and alpha is nothing but the value of y when x is 0. Remember this, okay? So just like straight lines, which we did in class 11. Now, E or epsilon is the shock, the innovation, or the error term. It represents a component in y that cannot be explained by x, and the expected value of the error term is always assumed to be 0. So let's take some example. Let's say we take an example of phone sales versus discount, where phone sales is my dependent variable, discount is a dependent variable. We can also have an example of H1 returns versus lock-in period, so Y versus X. And we can have an example of student average marks versus student-teacher ratio. So 1 and 2, what do you think, a positive relationship or a negative relationship between Y and X? In case 1 and 2, a positive relationship or a negative relationship? As discount percentage increases, in general, what would you expect for sales? Increase, right? Similarly, as locking period increases, hedge funds returns tend to increase. The first two relationships are having positive relationships. First two are having positive relationships, first two pairs. And the last one, the third one, is actually a case of negative. Absolutely. Because if the student teacher ratio is high, if there are more number of students per teacher, okay, if there are 60 students per teacher, and compare it with a situation where there are only 10 students per teacher. So if everything else stays constant, then the marks will of course improve for a lower student teacher ratio. So it's a negative relationship. Okay. Now these parameters, what are the naming conventions? Y is known as the explained variable, or the left hand side variable, or the dependent variable, or sometimes the regressand or regressand. And X is explanatory variable, right hand side variable, independent variable, or regressor. Epsilon or E is the shock or innovation or noise or error or disturbance. Okay. Then you have dummy variables. Dummy variables are a special class of variables which we use in linear regression. They are binary and they only take values of 0 or 1. So dummies are used to encode qualitative information. For example, a firm's sector or a bond's country of origin. So let's say you might have a case where you are denoting IT sector with a dummy variable of 1, and anything other than IT sector is having a value of a dummy variable value of 0. Now let's come to OLS. Consider a basic regression model which includes a single explanatory variable, the basic example that we have been taking. Now these alpha and beta can be estimated using OLS estimators. Okay, so this is the beta estimator. Okay, this by mistake it's a double equal to. Okay, and this is equal to covariance between x and y divided by the variance of the independent variable. Remember that in the denominator, I have seen candidates making silly mistakes in the exam where in the denominator they'll write variance of y. Don't make that mistake, okay? And of course, if you want to frame the same relationship in the form of correlation, this is the relationship over here. Okay, this also can be derived by minimizing a problem using maxima minima in differentiation. Okay, you take the function and you minimize it, set the dy dx equal to 0, and basically we are trying to minimize the sum of squared errors. Okay, so we get beta hat equal to this, and alpha hat is estimated using a property of the OLS regression line, that it passes through the mean x bar y bar of the values of x and y. Okay, so these are the properties. Again, derivations we are not going to do, only formulas are important from the point of view of the exam. Derivations we have done in the class. Now, let's take an example. Let's say this is an example. This is how you will be asked in the exam, this kind of question. So the covariance matrix will be given to you. X bar is given, Y bar is given. Covariance matrix is given to you. So the first job is to find out beta or beta hat. Okay. So this was the formula. Beta hat equal to this, which gives you 1.5188. So you can see that these parameters are directly taken from the covariance matrix. 512.3 is the covariance, and 337.3 is the variance of x. Okay, so what is the interpretation? The interpretation of beta hat is that the return, because we are talking about the mining sector, okay, and this has been assumed over a period of 20 years, and these are annual returns. Okay, remember that the period is 20 because this will be important later on. So n will be equal to 20. Okay, 20 years data. So beta hat equal to 1.5188. The interpretation is that the return on the mining sector portfolio, which is my dependent variable, it increases by an average of 1.5188% when the market return or the independent variable, it increases by 1%. So for every 1% increase in return in the market, the mining sector portfolio increases by 1.5188%. Okay. So for alpha hat also we'll use the formula and we'll get 3.5989%. What is the interpretation? What did I say for alpha? For alpha, the interpretation should be the value when x is 0, right? So this indicates that the portfolio returns are having an average return value of 3.5989%. Okay, if there is any calculation mistake, please let us know now or later also. Okay, or any typo, as I said earlier as well. It returns an average, the portfolio, mining sector portfolio, it returns an average of 3.5989% when the market return is 0. That is the even based on interpretation, the questions can be asked. Okay. Next, there are 3 important definitions. Explained sum of squares. So it is the sum of squared deviations of the predicted values from the average value. See the difference, predicted minus average. Sum of squared residuals. Sum of squared residuals. So sum of squared residual is very, very important. Or you can say residual sum of squares, or RSS. RSS, SSR, whatever you want to call it. So this is the sum of square deviations of the actual values from the predicted value. So these are basically the error terms over here, the sum of the error terms. Okay, the SSR or RSS. And ordinary least square tries to minimize these error terms. Okay. Next, one thing I just want to highlight over here with respect to ordinary least square before we proceed. Remember, ordinary least square, we are talking about the error term. So we are not minimizing the perpendicular distance. We are minimizing the vertical distance. What I mean to say is, suppose these are your points, okay? Okay, and you have to find out the best fit line. So there are many ways. Of course, it is not only OLS method is not there. There are many multiple ways. OLS specifically minimizes the sum of the squared distances of the actual values from the predicted values. So predicted values are the one which you are predicting on the line. And these are the differences between the actual and the predicted. You can see that these are vertical distances. These are not perpendicular distance. Okay. So there is a confusion sometimes. And in fact, this concept itself is not clear. The visualization is not clear what is happening to many candidates. So first make the visualization clear that what are we minimizing? we are minimizing the sum of these squared errors. These are all the errors, actual minus predicted. Okay, and these are vertical distances. Remember, vertical distances. Okay, not perpendicular distances. And once you minimize it, you get the value of beta. And once you have the value of beta, you get the value of alpha. So this is the second parameter, and this is the third parameter, total sum of square. So total sum of square is basically the actual minus average. So this is an average value. What is the difference between the actual value and the average value? Now it can be very easily shown, although we'll not show it, that TSS is equal to ESS plus RSS, and it is a very important result. Okay. In the class, we have used Excel sheets and some examples, also manual calculations to illustrate these ideas and the calculation of related terms like R square now. So let's come to R square now. R square is the proportion of the variance in the dependent variable that is explained by the variation in the independent variable. Again, this is the part which is very technical, I believe. This is also a part where, I mean, if you ask someone what is R square, so R square, they'll say percentage of dependent variable explained by the independent variable. Wrong. That's not correct. Percentage of the variation in the dependent variable explained by the variation in the independent. That is, this distinction is very important. Okay. So R square is not, I mean, in layman terms, you can definitely say it, but this is technically incorrect. The technical definition of R square is, it is the proportion of the variation in the dependent variable that is explained by the variation in the independent variable. Now remember a very important point, since we are dealing with linear regression with single regressor, in that case, correlation is the square root of R square. This is only applicable for linear regression with a single regressor, because for multiple regressors, there is a different story altogether and there's a different relationship. So it's also a straightforward relationship, but not this one. Okay, now what are the assumptions? The expected values of error terms are 0. Data realizations from independent and identically distributed random variable. Variance of x is greater than 0. There is no correlation between error terms. So error terms for each data point, I mean, if you take each data pair, if you calculate the error term, then the error term should be independent of each other. The variance of the error term should be constant, and this fifth assumption is a very important assumption. We'll see later on why. And the data contains no outliers. Now, as I said, that this fifth assumption is very, very important, because this is the figure over here. You can see that in this case, the variance of the error terms, you see the spread is not changing as you are moving from left to right. The spread is almost, I mean, to illustrate this, even dummy distributions have been drawn. These are dummy distributions just to illustrate. Okay, that, okay, this is the spread. I mean, almost all the normal distributions you can see are having the same dispersion. Okay, so the level of the error terms is not changing with the level of x, and in fact it is constant. But in the second case, the dispersion or the variance is increasing with the level of x, and this is a problem. This is known as heteroscedasticity. In fact, there are two types of heteroscedasticity: conditional and unconditional. This is actually a specific case. This is actually conditional heteroscedasticity, because the dispersion is increasing conditionally with x. I mean, if suppose it was sometimes increasing, sometimes it was decreasing, sometimes it was becoming random, even if it was not constant, even if it was changing, but it was not systematically changing with the level of x, then it would be unconditional heteroscedasticity. Even that can be dealt with. Homoscedasticity is not a problem. Of course, this is the ideal condition. That is the assumption also of OLS. Even if you have heteroscedasticity, unconditional is still acceptable. Still you can manage. Conditional, it is very difficult to work with conditional heteroscedasticity. Okay, so there are some tests and there are some methods to remove it. Now, what are the properties of OLS system? This is also one part which I think many candidates tend to ignore, because the hypothesis testing of beta will require, and this is something which has been given in such a complicated way in the book. We have tried to simplify it as much as possible. So you remember what we teach today only from the point of view of this learning objective, as far as regression coefficients hypothesis testing is concerned. Okay, so this properties of OLS slope estimator is being taught in the context of hypothesis testing of slope coefficients. Okay, So in practice, what you do is, the first thing you do is you treat beta hat as a normal random variable, which is centered around the true value beta. It means the mean you assume to be beta. See, when you have to test the hypothesis for beta, what do you need? Do you remember how do we test the hypothesis? We need a hypothesized value. We need standard errors, correct? We need estimated values of beta. So estimated value of beta you have. You also have the mean now with the assumption of a normal variable. What else you need? The denominator is standard error. So estimated standard error is given by this form. Standard error of beta is S divided by root n sigma x hat. And what is S? This is S. The square root of this is S. Okay, so S is the square root of S square. So these two formulae are important if you want to test the hypothesis for the statistical significance of beta. Okay, so let's continue with the previous example. These are the results we already got. So alpha and beta were already estimated earlier for the same example. Okay. Now, if you want to perform the test of statistical significance, now before I proceed, I want to just ask any candidate who can reply on this. When we perform test of statistical significance, against which value we are testing? It means what is the hypothesized value over here? If we are testing statistical, it is
0.
Very good. It is 0. Because you want a test of statistical significance. So statistical significance means whether it is statistically different from 0 or not. If it's not significant, it means it is 0. So test of statistical significance always imply a hypothesized value of 0. So this is how you will perform a test of statistical significance. Your null will be that beta equal to 0, alternate will be beta not equal to 0. Got it? Then your sample test statistic, how you will calculate it. This is the formula for sample test statistic. The same formula that we have been using, beta hat minus beta naught divided by SE beta hat. Now, as I told you earlier that we were performing Z test in hypothesis testing. What did I mention about which test we'll do in hypothesis testing for linear regression? Which test I mentioned? T-test. So over here in the exam, if T-table is not provided, which I don't think they will directly give you the two-tailed critical values or the T-critical value, most probably. Okay, if they don't give you, you should at least have an idea how to look at the T-table. That is also very straightforward. So it is given to you that 95% two-tailed critical value is 2.09. And why two-tailed, guys? Can you tell me why we are using two-tailed? Why not one-tailed? Again, anyone can answer. Because here there are no keywords.
Equality.
Sorry?
We are checking for equality.
Equality, very good. Because see, we don't have a problem statement over here, but the hypothesis itself, if you have equal to and not equal to, it means you are already testing two tails. Because equal to, not equal. Not equal to can be on both sides, na? Left hand side also, right hand side also. Is it clear to everyone? Is this clear to everyone? Okay, so make sure, Shreyas, are you asking this? Beta estimation is as close to mean. Can you just repeat, Shreyas? Is it a question that you're asking? Or something that you want to convey? Okay, not a question. Okay. So you are mentioning that beta estimation is as close to mean of, may I know? Mean of the true value beta only, right? That is what you're saying. Okay, for two-tailed test, you're saying. For two-tailed test, you're saying beta estimation is as close to mean. It's not very clear. Can just try and reframe your sentence, okay? Beta estimation is as, yeah, please.
Yeah, I meant to say that for the we are conducting a two-tailed test because we want to test whether beta which we have estimated is falling within those.
Okay, got it.
Yeah.
Got it. That's what you're saying. But in this case, actually, see, in this case, we don't have the idea about the mean. Okay, we are actually testing the statistical say. So we are testing whether beta is close to 0 or not the mean. So instead of the mean, you should say 0. Got it? Okay, so that is the idea. Fine. Okay. So what was the formula for standard error of beta? Okay, this you know what is the hypothesized value. This is very clear. This is 0. You're testing against 0. Okay. This is already estimated 1.5188. What else you need? You only need the denominator, standard error of beta. This is the formula for standard error of beta. S by square root of n times sigma x cap. So again, let's reproduce the covariance matrix for reference so that you don't miss out on the numbers. So one thing I can assure, I mean, I'll not say assure you, I think I can say with a reasonable degree of confidence, I mean, just like we have been using the hypothesis testing terms, that they might not give you the full long calculation. It is possible that they'll directly give you the standard error of beta like this. They'll give you, and you just have to test. Okay. But what if you have to calculate? So if you remember, this was the formula. S divided by root n sigma x cap. But how do we get this S? So that is why I told, remember the formula of S square also. Okay. And S square was nothing but this much. So this is how you will calculate S square first. Then you will calculate standard error of beta. Is it clear? Okay. Also tell me, I mean, we are going backwards actually. Also tell me, for calculating S square, we need one more parameter, rho. Do we have rho? Is it given? Okay, so why I'm going backwards? Because they will give you directly this, most probably. If not, maybe they will give you directly this. So you can perform this. If not, then you have to do this. But for this also, you need the correlation. How you'll calculate the correlation? Quite easy from the covariance matrix. Directly you'll calculate it as 0.6330. Yeah. So just see all the calculations. Are the calculations clear? Check the calculations. Just check the steps. You don't need to tally the numbers and all. Just check the steps. Are the steps clear or not? You can do the revision later, okay? Clear to everyone? Are the steps clear to everyone? Okay. And more can, okay, great. At least few of you should reply. Now, standard of beta we have got as 0.4042. Let's find out what is the sample test statistic. It is 3.76. So we know that 95% total critical value was 2.093. So this is 3.76 is greater than 2.093. It means we reject the null. So what is our conclusion? Do we have reasonable evidence to claim that beta is statistically significant? Because we are rejecting the null. It means that we are rejecting this. So do we have sufficient evidence now to claim that this is correct? Okay, yeah. So beta is yes. So we will conclude that beta is statistically significant at 95% level of confidence. Okay, so this is what hypothesis testing of slope coefficients will involve. You may also be asked to construct 95% confidence interval for beta. So you know the same thing. I mean, you will be given the critical value standard error. Either you will be given or you have to calculate. Process is same. Okay, so I'll not go into this right now. Then p-value, again, the same process as we have been doing in the hypothesis testing chapter. So there's no difference at all. Okay, fine. So that's it for this chapter. Are you guys okay if we don't take a 5-minute break now? Can we continue? Okay, great. So let's continue with multiple explanatory variables as well. Okay. So regression with multiple explanatory variables. Now, multiple regression is a regression analysis with more than one independent variable, which is yi is equal to alpha plus beta 1 x1i plus beta 2 x2i plus up to beta k xki plus ai. So there are more than one independent variables, and these are the corresponding slopes. So assumptions are same. All assumptions of linear regression apply with some minor modifications, of course, since there are multiple regressors. So they will just be the assumptions will just be extensions of the previous assumptions. there is one additional assumption. This one. It assumes that explanatory variables are not perfectly linearly dependent. And this is very important. Again, there is a concept called multicollinearity in which this will be discussed once again. So what this tries to say is these variables, x2i, x1i, xki, these can be somewhat correlated. That is okay. See, the ideal scenario will be if they are independent, but that is not possible. Suppose if you are carrying out a regression on the price of a stock, okay, and you have explanatory independent variables like say GDP, say inflation, say unemployment numbers. Can these be independent 100% practically? Is it possible? Can these be independent practically? Not possible, right? So some correlation is okay, but they should not be perfectly correlated. Got it? So if there is a possibility that maybe one of the parameters is perfectly correlated with say GDP numbers, it's possible. Maybe one of the GDP is an input in the calculation of some parameter, and even that parameter is being used. So then there is no point of including any extra variable that is perfectly included related with any other independent variable, because all the information is already captured, and this will lead to more problems. This will lead to problems of multicollinearity. Okay. Now, what are the assumptions of multiple regression? We discussed. Now, what is the interpretation? Okay. So earlier in the last case with single regressor, the interpretation of slope coefficient was that it was the change in dependent variable from a unit change in the corresponding independent variable, keeping all other independent variables constant. Okay. So basically you are controlling the effect of all other independent variables. Over there was a single variable, single independent variable. So there was no need to control any other variable. Over here, the interpretation is same, but you have to control the effects of other independent variables. You don't have to make them fluctuating. They have to be constant. So for example, beta 1 is the effect of a small increase in x1, holding all the other variables constant. Okay. Now, when the value of independent variable changes by 1 unit, the change in the dependent variable is not equal to the slope coefficient, but also depends on correlation among the independent variables as well. Because see, if suppose GDP changes by 1 unit, let's say in percentage terms by 1%, and you're carrying out a regression, and GDP affects unemployment also. So obviously, the change in the dependent variable will not be same as the slope coefficient corresponding to GDP, because at the same time, unemployment will also change. At the same time, inflation will also change. So that is why these slope coefficients, since we are controlling the effects of other variables to try and keep this definition alive over here, and it is actually the second point also states that practically it is not possible, right? So that is why these are known as partial slope coefficients. They are not known as proper slope coefficient, they are known as partial slope coefficient. The interpretation of intercept is straightforward. It is simply the expected value of y when all xi's are equal to 0. Okay. Now, you all are very aware of the OLS regression for linear regression with a single regressor, but most of the candidates, they actually overlook the OLS estimators for multiple regression parameters because it is actually difficult. It is the steps are very much detailed, but again, I'm saying the good news is that they do not ask you to perform the entire regression. Only the steps are important. That is what we have seen in the sample papers also and the feedback also. So let's say this is a model with 2 independent variables. So what are the steps if you want to calculate? See, earlier it was very clear. The formula for beta was covariance between x and y divided by the variance of x. But over here you have 2 x's. So now for beta 1, you have to first perform 3 single variable regressions. So the first regression will be for x1 on x2. So x1 will be regressed on x2 only. And the residuals from this regression will be retained. Then the second regression will do the same thing on y. So basically, y is also regressed on x2 and the residuals are retained. And finally, the residual of y is regressed on the residual of x. In fact, sorry, I think just there was slight error in what I said. The first regression will regress x1 on x2, and it will retain the residuals from this regression. The second regression will regress y on x2, and it will also retain the residuals of that regression. Then the residuals of the two regression will be regressed. Okay, so these are the three regressions which are carried out. Okay, and for beta 2, the same thing will be done. The only thing is that the roles of x1 and x2 will be interchanged. So the first regression will be done by doing regression x2 on x1. So x2 will be your dependent variable, x1 will be independent variable. Then y will be dependent variable, okay, and x1 will be independent variable. And then residual of y on the residual of x2 will be done. Okay, so residual on the first two regressions will be done. That's it. So these steps are important, guys. Don't worry about the detailed process. Of course, you should. I mean, if you've gone through the curriculum for the earlier, then you might have gone through the steps and as well as the calculation. So keep that in mind also. But I think from the exam perspective, steps are more important. Okay. So focus on the steps as well properly. Now, standard error of regression. This is the formula, and it conveys the fit of the regression line, and the fit is better if standard error of regression is smaller. Now, if you remember, R square was the proportion of variation in the dependent variable explained by the variation in independent variables. And I told you that earlier, the correlation was equal to square root of R square. But I said for multiple regressors, that is not the case. For multiple regressors, this is the case. For multiple regressors, R square is the correlation between, in fact, squared correlation. Squared is missing. So that correlation was between x and y. Remember, earlier for single regressor, this has to be clarified. R square was equal to rho square between x and y. But this correlation is different. This is a correlation between yi and the fitted value of y. So between the actual and predicted values. You take the correlation, you calculate the correlation, you square it, that will be your R square. So this distinction is very important, asked multiple times in the exam. Now there are problems with R square. Now if you add a new variable, even if the new variable is insignificant, you will find that your R square is always increasing, which means you will be under the impression that you are creating a better and better model. That will not be the case. Okay, so that is one problem. Another problem is R square is not comparable. And there is no general value for which can be considered as a good value for R square. So again, depending upon the problem being studied, maybe even R square value of 85 might not be great, 85% or 90%. But for some other problem, maybe 70% R square will be very good. So it totally depends on your stream, the kind of success that other people have got based on that experiment. Okay, depending upon the domain, as I said. Okay, and it is not comparable also. So what other measure you use to address some of these limitations? Not all, but some of these limitations. The first limitation can be addressed. How? By adjusting this R square. So this is the formula for adjusted R square. Okay. It includes the number of independent variables also. And the same formula can also be expressed in the terms of RSS and TSS like this. 1 minus epsilon RSS by TSS, where this is epsilon, n minus 1 by n minus k minus 1. So one thing you have to remember that this should be greater than 1. This has to be greater than 1 because denominator is less than the numerator. Now, if k increases, if the number of explanatory variables increases, then epsilon actually increases, but RSS decreases. Okay, so the net effect adjusted R square might increase or might decrease. So that is why adjusted R square has this property that like R square, in fact, I should say unlike R square, it does not always increase with the increase in independent. It might also decrease. In fact, the example that we have given in our PDF, we have actually adjusted R score has actually decreased, right? So if K increases, then there is no guarantee that adjusted R square will increase. It may increase, it may decrease. That is why it is a better measure as compared to R square, which always increases. Now, if you want to perform tests of null hypotheses, for individual tests, you can do the same process which we have discussed earlier in the last lecture. Linear regression with single regressors. Very straightforward. But if you want to do joint test, that is for single test. Now, there are different kinds of joint test. One joint test is the joint test where restricted and unrestricted models are tested. Another joint test is there, which was a part of the pre-2020 curriculum, which has been removed, which again, I think was actually an important test. I don't know why they have removed it. So I will not discuss it today, but we have discussed it in our videos and the PDF. But from the exam point of view, since it's not there in the GARP book, so it might not be asked. But I'll tell you the crux of that test. So basically, it was the joint test of all the coefficients together, that all the slope coefficients will be equal to 0, and the F statistic was the interpretation of that test is there, but that how the test is performed, that is not there in the curriculum. So the joint test, I mean, this question can be asked in the exam before I proceed to the next joint test, that let's say if you are given that you perform a joint test. So remember that joint test will always be performed using a F test. So joint test means you are testing that beta 1 equal to beta 2. Let's say there are only two coefficients equal to 0. So both your coefficients are 0 versus at least one of them is not equal to 0. So HA is at least one of them is not equal to 0. So this is what you do. This is F test. So a question can be asked in the exam that from the F test, you conclude that these are jointly statistically significant, let's say. It means that you reject this null. It means you conclude that they are jointly statistically significant. Either they can ask this in the form of a direct F stat value, or they can give you the R square value, or they can give you the P value. The most common question that we have seen is in the terms of P values. So I discussed that what is P value? P value is the minimum level of significance at which the null hypothesis can be rejected. Correct? So if I say that hypothetically, I'm saying, let's say the minimum level of significance at which the null can be rejected is 4%. Let's say hypothetically. So if you want to frame it in the opposite manner, can I say I can be maximum 96% confident? Minimum level of significance, does it translates to maximum level of confidence or not? Because significance level is 1 minus confidence level. Yes or no? Think about it. If this is minimum, this is maximum. Do you agree? Mathematically, it makes sense, na? Everyone. Right? So minimum level of significance corresponds to maximum level of confidence. Statistically, any P value which is less than 0.05 is acceptable. Any P value which is greater than 0.05 is not acceptable. Okay? Again, I'm repeating. Statistically, any P value which is less than 0.05 is acceptable. Greater than 0.05 is not acceptable. So it is possible that for individual t tests, let's say for the individual test of beta 1, I'm giving an example. Let's say they give you a p value of 0.12. What will you conclude about the statistical significance of beta 1? Tell me. What will you conclude about the statistical significance of beta 1? Statistically significant or not? Because normally, yes, very good. If P is less than 0.05, then only conclude that it is significant. If P is greater than 0.05, it means you cannot be maximum 95% confident. You can only be maximum 88% confident, which is not statistically a good result. You should be at least 95% confident. Okay. So for any test, if P value is less than 0.05, it is okay. It means statistically significant. But if P value is greater than 0.05, it is not statistically significant. So it can happen. I mean, when we discuss multicollinearity later, we'll discuss this P value part once again. Okay, and heteroscedasticity also. So let's continue. We understood P value. Let's continue. Now, there are two models which they will give you. One is the restricted model, the other is the unrestricted model. So again, since I'm assuming P value should be less than 0.05, not greater than. Okay. P value should be less than 0.05. Got it? So I'm assuming that you are already aware of the capital asset pricing model since you have done the course at least once, correct? So can I take that example of capital asset pricing model? Also, can I take the example of FRM French model? Okay. How many variables, independent variables, are there in the FRM French model? Perfect. 3. Right? One is the market factor, one is the size factor, the other is the value factor, correct? 3 factors are there. And how many factors or variables are there in the CAPM? In the capital asset factor? Only one, market factor, correct? So can I say that CAPM is a restricted version, theoretically, CAPM is a restricted version of FRM French, correct?
Yes.
Yes?
Yes.
What is the number of restrictions we have to apply to FRM French to give CAPM?
2.
2. Perfect. So this is what I was expecting. If you are already aware of this, then I can continue with this example. Okay. So this part was the earlier, the previous old curriculum F statistic, which I was talking about, which will not be discussed right now. Okay, this is the distribution anyways. So consider the FRM French model. So to imply restrictions, we will imply restrictions on which 2 factors? Tell me. Size and value, correct? So if we imply restrictions on size and value, it means that statistically we want that these two should be equal to how much? If I am applying restriction, 0. So if I make these two equal to 0, can I say that FRM French will convert to CAPM? Correct?
Yes.
Okay. So this is the null, this is the alternative hypothesis. So let's impose the null on the unrestricted model, which will give me CAPM. That is what I said. So CAPM gives you alpha plus only the market factor plus this EI. Okay, let's continue. Now let's assume these are the parameters which are given to you. 4200, 50, Q equal to 2, KU equal to 3. So remember, this is the formula that you have to remember. This is the formula you have to remember. Okay, N, KU is important. And then RSSR, RSSU, Q. What is Q? Q is the number of restrictions. Okay, Q is the number of restrictions. KU is the number of variables in the unrestricted model. So can you tell me in the FRM French model, which is unrestricted, what is KU? How many number of variables are there in the FRM French model? 3, correct. What is the number of restrictions? Q. Total number of restrictions we applied to create CAPM? 2. So please be clear on these things. You might be a little confused even now after studying. I mean, if some of you might have studied this, but I'm pretty sure many of you would be here today to which these concepts would not be clear. So remember that this is the number of restrictions and KU is the number of variables in the unrestricted model, which in this case is the Fama-French model. Okay. So using the values that we have, if we calculate the F stat, we get 4.38, and it will be given to you, or the table will be given to you, that the critical value is 3.2. So 4.8 is greater than 3.2. It means you reject the null. So what is the interpretation? See, if the test statistic, which we got over here, 4.38 we got, if suppose we got 2.1, then we would not be able to reject the null, and we would conclude that CAPM appears to be an adequate solution or an adequate model in explaining the returns to the portfolio. Why? Because if we are not rejecting the null, then what are we concluding? Kind of. We are not accepting it, but we are failing to reject it. So it means that we don't have sufficient evidence to claim that these are statistically significant. It means we will have to assume that they are statistically insignificant. So it means if they are insignificant, then only this was sufficient to explain. Understood? So the interpretation part they can ask you properly. Please let me know if interpretation is clear to you or not. Okay, because I'll repeat it once more for this part, or the part which we have got as 4.38 greater than 3.2. Now, since we have got 4.8 greater than 3.2, it means that the null hypothesis is rejected, which means that the size factor and the value factor coefficients are also statistically significant. So we will conclude that CAPM does not appear to be properly explaining the returns to the portfolio. We need the Fama-French model. Tell me if it's clear or not. Is it clear or not? And anyone who wants me to repeat any point, please do not hesitate to ask. Because this is a test where I think many of the candidates, again, I'm saying, get confused. They might make mistakes. So please ask if it's not clear. Otherwise, I'll proceed. Clear to everyone? Okay, great. So when you reject the null, I just write it over here. That it means if you're rejecting the null, then CAPM is not adequate. Fama-French is better. Okay, fine. Okay, so that's it for this chapter. We will continue with regression diagnostics. Again, are you okay if we don't take a break? We will try to conclude it in half an hour. Okay, and then we will take a 10-minute break and we can start the last 3 chapters. Fine. So let's quickly go through omitted variable versus extraneous variable. So omitted variable is that variable which has non-zero coefficient, but it is not included in a model. So basically it's a relevant variable. It should have been included. It is not included. What will happen because of this? If it is not included, it will have 2 effects. The remaining parameters can become biased. Okay, there will be some common variation which will be left. That will be the remaining parameters will be biased, and the estimated residuals will be larger than the true shocks. Because if you include this, then it is possible, it is highly possible that your shocks, your error terms will reduce. Okay. The opposite of omitted variable is extraneous variable. It is not required in the model, but it is unnecessarily included. Okay. So that's the difference. Now, bias variance trade-off is a concept which will also be discussed in machine learning, which we are not going to cover today, of course. Now, the choice between omitting a relevant variable and including an irrelevant variable is ultimately a trade-off between bias and variance. So if you have larger models, they will have a lower bias, but they will have less precise estimated parameters. So bias is lower, but variance is higher. Less precise estimation means variance is higher. Okay, so I just write it down. What is the meaning? But high variance. So there is always that. But smaller models will have bias, high bias, but low variance. Okay, smaller models, high bias, low variance, whereas larger models, opposite, low bias, high variance. Okay, this will be discussed in machine learning. Let's come to heteroscedasticity. I've already introduced heteroscedasticity, right, earlier. So you can see over here also, there is a pattern. First, it is decreasing the residuals, and again, they are increasing with the levels of it. So this is also conditional heteroscedasticity. There is no random pattern. See, if it increases, then decreases, then random, then again. So it's not like that. Even if it's decreasing, then increasing, still there is a pattern. Okay. So this is conditional heteroscedasticity. It is systematically related to the level of independent variables. So what are the effects of heteroscedasticity? The regression coefficients are not affected in terms of consistency and unbiasedness. The asymptotic distribution of the estimated parameters takes a different form. Standard errors are usually unreliable estimates, and hypothesis testing of regression or coefficient produces unreliable result. Okay. So what are the tests for heteroscedasticity? In the beginning only I mentioned that instead of the whole test, they actually focus more on the steps, just like we did for OLS for multiple regression. So over here also steps are important. In fact, this question, if you see, is one of the direct questions even in this year's gap sample paper question, last year's gap sample paper question. So you basically, what you do, it's a test proposed by White. You estimate the model and compute the residuals first. Now the question was based on only step 2. They asked the question that the second step of the White test regresses the residuals on the following. This was the question. So on a constant, all explanatory variables, cross product of all explanatory variables, and one more option was given, which was the incorrect option. Okay, so which of these is incorrect? Something like that is there. Okay, so you can see that the square of the residual term is regressed on a constant. This is a constant. All explanatory variables, x1, x2. And cross product of all explanatory variables, including the product with itself. It means x1, x2, x1 square, or x1, x1, x1 square, x2 square. So x1 square, x2 square, x1, x2. That's it. And of course, this is the error term of this regression. Got it? The null hypothesis will be gamma 1 equal to up to gamma n equal to 0. And the test statistic is computed as nr square. The distribution is also important. The degrees of freedom is k times k plus 3 by 2, chi-square distribution. These things you have to remember from the point of view of the exam. This can be asked. Okay. Now, if suppose you fail to reject the null, then the data is homoscedastic. It means there is no heteroscedasticity if you fail to reject the null. But if you are not able to reject the null, then there is heteroscedasticity. Can you tell me why it is it might seem very complicated, but it is actually quite simple. If you see the regression, see, if you cannot reject the null, it means at least one of them is not equal to 0. Agreed or not? Yes or no?
Yes.
Yes. Okay. So let's say if gamma 1 is or gamma 2 is, say, statistically significant. Okay. Because if at least one of them is not equal to 0, let's assume it's gamma 2 or any other. Okay. So if this is statistically significant, this means that error term is directly dependent on the level of x finished. That was the definition of heteroscedasticity. That's it. So it's not very difficult. In any way, if error term is related to any of these, it means that there is heteroscedasticity, conditional heteroscedasticity. Okay. So there are some approaches to model data with heteroscedastic shocks. The first is to ignore and then use robust covariance estimator, the heteroscedasticity robot, which is the wide covariance estimator. The second approach is to transform the data, or you can use this weighted least square method. Then you have multicollinearity. Multicollinearity occurs when one or more explanatory variables can be substantially explained by the others. I shared in the beginning that there is an additional assumption of multiple regression. What was that assumption? The assumption was that the variables should not be perfectly related to each other. Otherwise, there will be perfect multicollinearity. Even if there is not perfect, let's say if there is one of the variables which is heavily influenced by the other variable, it means that the effects of one of the variables which is already captured unnecessarily, another variable is also capturing the same effects. Maybe it has some other exclusive, very small exclusive effects, but mostly it is having the same effect as any other variable. So that is multicollinearity. So again, over here also, you either ignore the issue or you identify multicollinear variable using variance inflation factor and consider removing them from the model. So what is the variance inflation factor? This is the formula for variance inflation factor. 1 minus Rj square, where Rj square, I think they will give this to you in the exam. And it comes, see, of course, they'll not give it directly. You'll have to be smart about it. They'll give you a regression. You have to remember that, okay, Rj square was coming from this. So they'll give you, okay, Rj square as a regression of xj on other variables, maybe. And then they'll, in fact, this also we have shown on Excel in our class, how to perform the this test or calculate VIF. See, basically, it's very simple. Xj is being regressed on other variables. See, if one of the variables is dependent on the other, what is the best way to deal with it? How to find it out? Just the same way like you did for the error term. If error term was dependent on, say, x1, x2, or x1 square or x2 square, we regressed it to find if there any relationship is there. Similarly, if let's say if you feel that, okay, x1 is related to any of the variables, you regress x1 against other variables. Finished. Then you regress x2 against other variables. You will find that if there is any relationship between them or not. Okay. So you exclude the dependent variable and you regress the xi's or xj's on other variables in the model, and you find out the variance inflation factor. Now, residual plots, they are standard methods. This you can just go through the PDF directly. Okay. Okay. Now, outliers. What are outliers? Outliers are values which, if removed from the sample, sorry, I think there's a question. Pooja, again, I'm saying we have already discussed actually this in the class. This part has been discussed in the class, but the problem is that no, it was covered. It was, in fact, an Excel sheet also is there where variance inflation factor has been calculated. Okay, so don't worry if it was there. Okay, so VIF has been calculated using an Excel sheet. No problem. If, let's say, I mean, you just double check once, and if you cannot find it, just let us know. We'll share the Excel sheet also if required. Okay. And right now it won't be possible, as I'm saying to other, this is for other candidates, it won't be possible to show the calculations. So just remember VIF and the logic, the idea behind everything. Okay, so these are residual plots. This I said you can go through yourself. Outliers. Outliers are values. If they are removed from the sample, they will produce large changes in the estimated coefficients. Just a quick recap. When we studied quantiles, what was the main benefit of quantiles? One of the benefits?
They are not impacted by outliers.
Correct. They were not susceptible to outliers. Okay. So, but outliers are a problem, right? So, even in linear regression, outliers are a problem. So, how to check for outliers? This is one of the methods, because the outliers can be measured by some distance specific method, right? How far they are or how close they are. So this is one of the methods, the Cook's distance. It measures the sensitivity of the fitted values in the regression when you drop a single observation. So what happens when you drop a single observation? What happens to the fitted values? So this is how Cook's distance is calculated. Okay, where these are the variables, the yi minus j, it means it is the fitted value of yi when observation j is dropped. So you have to be very careful about it. You have to compute the fitted value again after dropping one of the observations. So that is your yi minus j. Yi, I should not say to the power. So this is yi, what do we call it? Postscript, or what do we call it? It's not a subscript, right? Fine. Now the rule is, if finally, if dj, the Cook's distance, is greater than 1, then it is an outlier. Otherwise, that observation is not an outlier. Okay, so that's it. Okay, so that's it for this part of the lecture. So we can take a break for 15 minutes or 10 minutes. We can take a break and then we can resume. Okay. So let's resume in 10 minutes only. Right? That will be the last part of today's lecture. Okay, 15 minutes, fine. So let's resume in 15 minutes. 5:15, 5:45. Let's resume at 5:45. Okay. So we'll start with QTA 10, stationary time series. Now, time series can be decomposed into 3 distinct components. So in this chapter, we are not going to deal with the detailed time series equations and all. So I'll try to, even though it's chapter in quantitative method, but you all are aware, you have studied time series chapters. There are a lot of theoretical concepts behind the time series analysis chapters, both of them, non-stationary as well as stationary. So we will try to focus on both. We'll try to keep a balance. And from the exam point of view, I have prepared the slides so that memorization of some of the important stuff is easy, because the problem is in time series, you will find that as far as exam is concerned, there is a lot of irrelevant information also, right? So you don't need to learn each and everything. Okay, so there are slides where I will ask you to memorize some of the formulas later on using the PDF. So it can be composed into 3 distinct components. You can have trend, you can have seasonal component, and you can have cyclical component or cyclical component. The first 2 components are deterministic, whereas the cyclical component is basically non-deterministic. It can be shock, and as well as it can be having a memory. Now, a time series is covariant stationary if the mean is constant and it does not change with time. So in this chapter, we are dealing with covariant stationary or stationary time series. So mean is constant and does not change with time. Okay, that is one assumption. Variance is finite and does not change over time. Okay, then autocovariance is finite, does not change over time, and only depends on the distance between the observation. Now, autocovariance, why we are calling it as autocovariance? Autocovariance, we are calling it because it is the covariance of a variable with its lagged value, with its own lagged value. So if you're talking about, say, y3, then what was the lagged value, say 5 periods before or 6 periods before? So y7 or y8 or y9. So there is no other variable, right? All the variables are lagged values of themselves. So it depends only on the distance h between the observations. So what is the message over here is, for example, if you have covariance between y8 and y2, it will be same as the covariance between y15 and y9. Because the distance between 8 and 2 is 6, the distance between 15 and 9 is also 6. Okay, the idea is very important. Also, autocovariance, you define it like this. Okay, so autocovariance is basically the covariance between the process values at different points in time. So this is the hth autocovariance, you can say this one. Also, if the covariance structure is stable over time, as we discussed, as required by covariance stationarity, it does not depend on time, only h. Autocovariance only depends on h. And another point is that since it depends on distance only, that is why the autocovariance function is symmetric. So it means whether you go forward or you go backwards, if the distance is same, the autocovariance will also be same. Now, when h equal to 0, then gamma is equal to EYT minus EYT square. This is the variance. So basically, the autocovariance at 0 lagged value. So it means the covariance with respect to itself. This is nothing but the variance of that particular. Now, if YT is covariance stationary, then the autocorrelation is defined as this ratio. This is autocorrelation. Gamma H, which was autocovariance, remember? Autocovariance, and this was the variance. Gamma 0 was the variance because it was with respect to itself. Now, this point, many of the candidates, they get confused. What is gamma H? What is gamma naught? But it is very simple. You just understand gamma H is the autocovariance. Got it? Gamma H is the autocovariance. Okay. And gamma naught, when we are talking about this part, gamma naught. Okay. This is nothing but the variance of YT. Okay, gamma naught is the variance of yt, and it is mentioned over here also, and it makes sense also because at zero lag, the covariance will be nothing but the variance with respect to itself. And we have partial autocorrelation function. It measures the strength of the correlation between yt and yt minus h after controlling for the values between them. So you control for the values between yt and yt minus h, and then you get you observe the correlation. That is your partial autocorrelation. Now, this is the part where I want to have a slightly detailed discussion, because the distinction between autocorrelation and correlation, partial autocorrelation and autocorrelation, should be very clear in your mind. How many of you are very clear with the distinction between partial autocorrelation and autocorrelation? Have you ever wondered that why partial autocorrelation, why autocorrelation, what is the difference? Not clear, right? How many others who feel that it is not clear? And B, you can straight away say not clear. Okay. Okay, fine. Fine. So let us take an example. We can take an example for, say, stock prediction. We can say take an example for prediction of sales in a retail store. We can take example of weather also. Okay. So let's try and take any example. Let's say, imagine you are trying to predict tomorrow's weather based on past data. So this autocorrelation function, it might show that generally, again, if suppose, because we are all in the summer season, so mostly it's sunny, right, nowadays. So if suppose it was sunny today, it will be sunny after 3 days as well. This is the summer season, right? So autocorrelation function will show that if it was sunny today, it will be sunny after 3 days, or it was sunny 3 days before also. So let's try and assume that, okay, I am trying to relate how much sunny the weather will be after 3 days based on how much the weather is sunny is, how much sunny the weather is today. So the weather after 3 days, let's say it is my current value, and the weather today is my past values, because it is 3 days before Wednesday. Okay. Now the problem is that autocorrelation function does not only include the direct effects. I should not have said the problem. The observation over here is, or the fact with the autocorrelation function is, the definition of autocorrelation is that it includes all the effects that might be there, which are indirect effects. So for example, if it is sunny today, will it affect the weather tomorrow also? Yes or no? Will it affect the weather tomorrow also? Yes. And the weather tomorrow, will it affect the weather day after tomorrow also? Yes. And then finally we have after 3 days Wednesday. So that will be also an effect. So basically, autocorrelation function includes the direct effect of today's weather on the weather after 3 days, but it also includes the indirect effects, all the indirect effects, every indirect effect that you can capture. Say like this and then like this. Okay. Every indirect effect that you can capture is also incorporated in autocorrelation. But what does partial autocorrelation do? Partial autocorrelation simply tells you what is the unique effect of the weather today on the weather 3 days later. And none of this has to be explained by what happens in the next 2 days. Got it? So autocorrelation function is giving you kind of a broader picture of all the time dependencies, which are considering all the intermediate effects. Whereas partial autocorrelation function is getting rid of all these intermediate effects, and it is simply focusing on specific relationships between y3 and y0, between, say, two particular values. Understood? Only direct effects are considered in partial autocorrelation. Direct, absolutely one-to-one effect. So is the idea clear? Distinction clear? Similarly, we can have it for stock price. Let's say if the stock price on Monday tomorrow is say $100 for some particular stock. That will have an effect on the stock price on Tuesday. It will have an effect on the stock price on Wednesday, similarly on Thursday. Okay, so these indirect effects, if we calculate, then the price of the stock tomorrow will influence the price of the stock on Thursday using direct and indirect relationships. But what is the unique effect of Monday's stock price on Thursday's stock price? That is captured by the partial autocorrelation function. Whereas what are the direct as well as indirect effects of the Monday stock price on the Thursday stock price? That is captured by the autocorrelation function. Is it clear now, the difference? To everyone? Okay, fine. This was actually something which is an important concept and probably could have been explained, but there is a lot of lack of literature based on the basic ideas behind PACF and ACF. Only the application part is given, the graphs are given. Okay, now white noise. White noise is a fundamental building block of any time series model. So this is a white noise process. This is how it is denoted. This sigma square is the variance of the shock. So you can see it's a very random process. A very, very random process. Okay. It has three properties. One is mean is 0. Again, constant and finite variance, and no autocorrelation or autocovariance. So is a white noise process covariance stationary? What do you think? Is a white noise process covariance stationary? Because there were three properties, right, of covariance stationary. You can see all the three properties are being followed or not. Go back to covariance stationary and you see these three properties: mean constant, variance finite, autocovariance finite, does not change over time. Is it being followed? Yeah. If autocovariance is 0, it means it is finite and it is not changing over time. So all the properties are being followed. Okay. So this is also a covariance stationary process. Now Gaussian white noise is a special case of this IID noise. It is represented like this. E is IID N. The difference in white noise and Gaussian white noise is that white noise is a general process and Gaussian white noise is a special case of IID white noise. It's a special case of IID noise where they are normally distributed with a mean of 0 and variance of sigma square. So you have a normal distribution. Okay, so basically what is happening, randomly the values are being picked from identically distributed normal distribution, and then you are taking those as error terms. So that is basically your white noise, Gaussian white noise. Okay, I think there is, yeah. So autocovariance function for a white noise process is this, and autocorrelation function for a white noise process is this. Autocovariance sigma square when h equal to 0, and it will be 0 when h is greater than or equal to 1. Makes sense, right? Because there is no covariance with respect to any future terms. Finished. It is completely random. Similarly, autocorrelation. Okay, and similarly for partial autocorrelation. Now let us come to AR models. So this is how AR models are represented. YT is a function of an AR1 process. Okay, so only one lagged value we will consider. And again, I'm saying I'm not discussing all the things in great detail. I'm just giving you the basic model, the idea, that's it. And a presentation in such a way so that you can remember a lot of stuff which are important from this chapter. So YT is being regressed, you can say, a kind of, this is also a kind of a regression. I mean, carrying forward from our previous discussion on regression, where YT is being regressed against YT minus 1. Yeah, absolutely. This is lagged value. This YT minus 1, Rohit, is a lagged value of YT. Understood? So if suppose, let's take an example of Monday and Tuesday. Tomorrow the stock price is $100. Tuesday the stock price becomes $105. So let's say we reach Tuesday. We are at, we have arrived, Tuesday has arrived, and we are trying to find out what is the lagged value of the stock price, 1 period lagged value. So if on Tuesday the stock price is 105 and if on Monday the stock price is 100, So the 1 period lagged value of the stock price is 100. Got it? So basically, what is lagged value? Lagged value is nothing but the 1 period or 2 periods or 3 periods before what happened with that variable. That is the lagged value for that variable. So this is the 1 period lag value, a previous value. 2 period lag value will be yt minus 2. 3 period lag value will be yt minus 3 lag. Got it? It's a very simple, clean idea. Okay, very straightforward idea. Now, if suppose phi is less than 1, then this process will be covariance stationary. Remember this. Again, the presentation of these topics is very complicated in the books. So remember this. This will give you a very good picture. For this process to be covariance stationary, this has to be less than 1. The mod of phi has to be less than 1. And if mod of phi becomes equal to 1, then it will not be stationary. Okay, and we can explain it quite easily. Okay, although we don't have time, it is quite easily explainable. Remember that the expected value of yt is delta by 1 minus phi. Now, I have seen multiple times they tend to confuse the candidates in the exam. What they'll do is that instead of this AR1 process, they will actually make this term as 0. So they'll give you this yt is equal to phi yt minus 1 plus et. And they will ask what is the mean of this process. And they will give you this option also, delta by 1 minus phi. Delta is 0, boss. There is no delta. Okay. So the answer will be expected value of yt in that case will be 0. Remember that. So don't get confused. Sometimes they will actually make delta equal to 0. So you have to be very careful about this. Now variance of yt is equal to sigma square by 1 minus pi square. Okay. Then this is the correlation function. This is phi to the power h gamma naught. Again, we have derived this also in the class, but you just remember this. Phi to the power mod h gamma naught. So it is a recursive function. It is very simple. You just have the value of phi. Yes, Akshay is asking, where do we consider other factors in time series models like geographic risk, financial statement announcement, uncertain event due to nature? See, actually, Akshay, when you are considering yt against yt minus 1 and yt minus 2 and yt minus 3, the regression is exclusively against lagged values only. Other factors are not incorporated explicitly, but if you see the effects of geographic risk, financial statement announcement, and uncertain event are already implied in yt minus 1. Because let's say if something like that happens, some kind of announcement is happening 2 days before some announcement happened. So don't you think the stock price 2 days before will automatically reflect the effect of that financial statement announcement, right? So even though we are not including those terms explicitly, Akshay, but those values, the effects actually of those announcements and those values, those uncertainties are already included in yt minus 2, yt minus 3, whenever those events happen. Got it? Is it clear? Okay, fine. So this is very simple. You just take phi and raise to the power of h. That's it. So if you are having 2 lagged values, so it will become phi square. That's it, finished. Very simple. And this will be for rho h, the function, which is phi raised to the power h, and you have alpha h as phi raised to the power h for h 0, plus minus 1, and 0 for h greater than or equal to 2. Now, all these things which you are seeing over here, it is better, especially the last 2 points. It is always better. See, this is autocovariance and this is autocorrelation. And this is partial autocorrelation. So remember that partial autocorrelation is represented by alpha. Autocorrelation is represented by rho. Okay. And this is autocovariance. Okay. Now it's better that for understanding these 2 points, rather than looking at the formula, first you look at the graph. So what happens in AR models? What happens in AR models? In AR models, the partial autocorrelations, they actually, just a minute, there is a mistake. Just give me 1 minute. Okay, I had changed the diagram, but I think it has not been. Let me just check. Next one, please. Yeah, this diagram actually had changed. is not being reflected. It's a mistake actually. Yeah, there is a slight error over here, okay, in the diagram. Slight error. Just give me 30 seconds. I'll just paste the correct diagram. Just 30 seconds, please. In the correct diagram, so I'll just modify this only. Sorry. So this is partial for this particular diagram because generally what we have done is we have used, is the PPT visible or not? Because it's stuck. It's not changing over here. What happened? Is it visible, the PPT?
Hello.
Hello, is the PPT visible?
Previously it was visible.
Okay, okay, just a minute. So the pen is also not working. Okay, it is stuck actually. Stuck. Wait. PPTs are stuck. I'll just restart the PPT. No, not working. Can't find the correct diagram, so I'll just modify it. I wanted to add the correct diagram because we have used this very clear color code convention that brown is for autocorrelations and light green is for partial. But anyways, just for this particular side, assume that this is partial and this is autocorrelation. Okay, so the feature of AR1 process that we are seeing is that the autocorrelation function, the green one, it is decaying gradually. You can see that, right? Gradually it is decaying to 0. Okay, whereas partial autocorrelation function is non-zero only for one lag, and that is what this message is. This is only at 0 or at the first lag, because at 0, of course, it will be with respect to itself only, so it will be 1. Whereas, and anything to the power 0 is 1 only. So 5 to the power 0 will be 1. So obviously autocorrelation with respect to itself is 1. But at lag 1, it is having some non-zero value. It is abruptly cutting off at lag 2. Abruptly. So there is no partial autocorrelation value after lag 1. Now, one important point which I want to discuss is practical point, because see, theoretically this diagram is correct. This is how it should be explained. But those who have done R or Python coding and they have actually implemented these models, they might be aware that it does not abruptly go to 0, right? There are still some segments left, correct? Have you seen this like this? Anyone who has seen this? Right. So that is also the assumption that it has actually become statistically insignificant, because actually there are some confidence interval bands. Okay, so anyways, that is a different aspect which FRM curriculum has not covered. So but why I'm saying this, because in the exam, let's say hypothetically, if they give you, instead of abrupt cutting to 0, if they give you say small values also, you need to assume that it is abrupt cutting to 0, almost 0. Okay, so that is why I want to highlight this point. So partial autocorrelation function is abruptly cutting off to very close to 0 or 0, and autocorrelation function is gradually decaying. That is one of the features. Next, okay, this diagram is correct, thankfully. Now in this case, if suppose phi is negative, then you can clearly see that autocorrelation is actually dwindling and fluctuating between negative and positive values, but the magnitude is still decreasing. If you see the magnitude overall, it is still decreasing, right? In magnitude, it is still going to 0. But again, the partial autocorrelation function abruptly drops off. And if you see, it makes sense also, because the first number, if you raise it to a power of an even number, odd number, you will get a negative number. That's why you have negative 0.9 over here. But if you raise it to the power of an even number, first you raise it to the power of an odd number, you get a negative number. You raise it to the power of an even number, you get a positive number. And of course, the magnitude is decreasing. That's why negative, positive, negative, positive, negative, positive, like that. Okay. So just make sure that you are through with two things. It is a AR1 model or a AR2 model, because if it's a AR2 model, then the abrupt cutoff of the partial correlation will happen after 2 lags. Remember this. Okay. Now ARP process. This is the general ARP process. This is the expected value of the ARP process. This is the variance of the ARP process. Now there is an operator which we call as the lag operator. It expresses and manipulates more complex time series models. It shifts the time index. So you just need to remember that LYT is equal to YT minus 1. That's it. Okay, and one more thing I want to inform you right now, which we have discussed in fact in class, we have discussed factorization also, the revisit the concepts from class 6 and 7 of algebra. But I just want to tell you, when you study unit roots, we cannot do detailed derivations today. But if you find anything like 1 minus L or L minus 1, just remember this. It means it is a case of unit roots. So lag operator also helps to simplify the expression so that you can identify unit roots quite easily. That will come later on, but I'm just telling you that this is one of the ways, and the detailed derivation is not discussed later. That's why I'm telling you right now. Now let's come to moving average model. Now AR model was regressing YT against a lagged value of itself. Whereas MA model, if you see, it is regressing YT on a lagged value of a shock, an error term. So today's error term, of course, will be there, but yesterday's error term has been included as an independent variable. If you call it a regression, although it's a time series, if you call it a regression, then yesterday's error term has been included as an independent variable in this regression. And this is the new error term which will be generated in today's regression. Okay, so it regresses YT against the lagged values of the shocks. Remember one thing, there was a condition. What was the condition for AR1 to be covariance stationary, guys? What was the condition for AR1 to be covariance stationary?
Mod of phi less than 1.
Yes, phi should be less than 1, and if phi was equal to 1, it was non-stationary. But MA1 process is always covariance stationary, always. So there is no problem at all. But over here, instead of covariance stationarity, we need to focus on persistence. So theta, if it is greater than 0, then the model is persistent. If theta is less than 0, then the MA1 process is mean reverting. Okay. Expected value of this is mu. This is the formula for variance. This is for autocorrelation. Okay. The complex formulas, which I think there is a very low probability of being asked, I have completely omitted those formulas. So while revising, these will be enough. Don't worry. Okay. Now, this is the distinguishing feature of the MA1 process from the AR process. What is the feature? That in case of AR process, the partial autocorrelation was getting abruptly cut off. Whereas in case of MA process, it is the autocorrelation which is getting abruptly cut off. Right? So autocorrelation is getting abruptly cut off, whereas partial autocorrelations are gradually decaying. But there is a very important distinction over here also. Even though theta is positive, the partial autocorrelation is fluctuating between negative and positive values. So remember this. And when theta is negative, the values are completely below the x-axis. So this is something which you need to remember from the graph. Okay, don't forget this part. Then, of course, MAQ process, there will be Q lagged error terms. Expected value will be same. This will be the variance. And remember that in general, the ACF is always 0 for lags larger than Q, and PACF is non-zero. Same idea. So basically, if it's a MA2 process, it means autocorrelation will cut off after 2 lags. If it's a MA3 process, so same thing has been explained in general over here. If it's a MAQ process, then autocorrelation will be 0 for lags larger than Q. Okay, because as soon as you hit the lag Q, autocorrelation function will become 0. And PACF is non-zero at all lags. So for all lags larger, as soon as you cross, not hit, as soon as you cross lag Q, ACF will become 0. Now, one thing which is important to discuss, although you may not find it very significant, you will say that, okay, this was the same thing which was taught as the mean, the expected value of YT. But this is a separate derivation which you can do for the mean reverting level also. And it can be shown that this mean reverting level is same as the expected value. So the mean reverting level of these processes are same as their expected values as well. Okay. And remember, mean reverting level is not same as the mean. So this is a different derivation, mean reverting level. And the good part is that the mean reverting level also comes out to be same as E of yt, which if you remember in this case, it was delta by 1 minus phi. And for MA process, it was mu simply. So the same thing is the case for mean reverting level also. The mean reverting level for AR1 process is delta by 1 minus q, and for MA process it is mu. Okay, so this can be asked in the exam. Is the mean reverting level same as the expected value? Yes, for both processes. And of course, I mentioned that if there is no intercept, if delta is 0, then remember that the mean reverting level is 0. So just remember these things. Now, AR, MA 1, 1. This is the combination of AR and MA processes. So this is a simple process where you can see a lagged value of yt also and a lagged error term also. Then you have the expected value of yt, which is delta by 1 minus phi. Okay, so in this case, the expected value of yt is given by delta by 1 minus phi. I think it would be better. Why I am saying this? I think it would be better if you omit this term while remembering it. Because see, mu, you might get confused that this was the mean of the MA1 process. So just remember that even for AR-MA process, the mean is same as the AR1 process. The variance is different, of course. I don't think it's important, so this will not be asked, most probably. Now, if you remember, in one of the processes, partial autocorrelation function was abruptly cutting and other was gradually decaying. In another process, the opposite was happening. Whereas since it is a combination, ARMA, so in this case, both will gradually decay. None of them will abruptly cut off in ARMA process. So this is the idea. Both of them, although it is not visible, but it is gradually decaying, the partial autocorrelation functions. And of course, there are P and Q terms. So P lagged YT and Q lagged shocks. So AR, MA, PQ is covariance stationary. Now, if you remember, MA is always covariance stationary, moving average process. So it means for AR-MA process to be covariance stationary, MA part is not a problem. This is not a problem. This is the problem. So if this is sorted out, if this is covariance stationary, it means AR-MA is also covariance stationary, no problem. And AR-MA PQ models have ACF and PACF that decay slowly while possibly oscillating. Fine. Now, this is the part which is being asked a lot in the last few years, the joint tests of correlations. You have the Box-Pierce test statistic and you have the Jung-Box test statistic. So the null hypothesis is all the correlations are jointly equal to 0. All the correlations are jointly equal to 0. And when I'm talking about correlations, I'm talking about sample autocorrelations. Okay, so in the class PPT class lecture, we have discussed that part also. But since the test is more important, I have omitted this slide today. So just remember, we are talking about the sample autocorrelations right now. So this is the null. So obviously this will be the alternative hypothesis. And both the tests will have chi-square distributions with a degree of freedom of each. So we can take an example. First, let's see the formulae. So this is the formulae for Box-Pierce. This is the formula for Jung-Box. Remember that if samples are large, then there is not much difference between the result of the test. When sample is small, then Jung-Box statistic is actually preferred to test multiple autocorrelation. Okay. Now let's take an example. So let's say T is 500. These are the 3 lags which are given. These are the coefficient values which are given. How do we perform the 2 tests? First, you calculate the Box-Pierce test statistic. So it's very simple. T times summation of rho square. So T is 500. These are the values of rho. 0.7, 0.3, negative 0.2. So 500 times 0.7 square plus 0.3 square plus negative 0.2 square. How much you're getting? Calculate quickly and tell me. It's been a long time since you guys are sitting. You have been patient, and that is very good actually. And if you're able to, even these are very minor calculations, but if you're able to solve, perform the calculations right now, also it means your efficiency level is going up. So tell me what will be the answer for BP, QBP, how much you're getting? Okay, 310. Is everyone getting 310? QBP? Is everyone getting 310? Two answers. Okay, third one also. What about others? Okay. So it is 310. What about LB Jungbox? Jungbox is a bit complicated. It's t times t plus 2 summation of 1 by t minus h times rho square. So t is 500 and h is the lag, remember. So first how many lags are there? 3 lags. So one lag first, then second lag, then third lag. So this is the calculation you have to do. Okay, I don't think examples are there in the book. I'm not very sure. I don't think they're there. So these, just having the formula might not help. So the calculations are important. So perform the calculations, how much you're getting. How much you're getting. You'll be getting 312, close to 300. So they're quite similar. Okay. Let's say the critical value is say 90. Then you can reject using both. What is the problem? Okay. Yeah. Yes, you have 312. Okay. Now, what if the sample size is small? If you have these three coefficients and you perform the calculations, you'll find that this is 89 and this becomes 92. So now if the critical value is 90, the problem will be that you will not be able to reject the null using box peers, but you'll be able to reject the null using Jungbox. Okay, so you have to be careful. What is the sample size? If the sample size is small, then it is clearly given that the Jungbox statistic should be actually used. There are some particular reasons. It is actually closer to some chi-square asymptotic distribution, but you just remember that that should be the preferred method in that case. Now, what about model selection? The first step in model building is to inspect the sample autocorrelations and the PACFs to get some idea about the correlation structure. Okay, and then you measure their fit. This is one of the parameters to measure their fit, mean squared error. So this is how it is defined. Then you use some information criteria. One is Ekaik and the other is Bayesian or Schwarz information criteria. So these are the definitions. This is something which you need to remember. Okay, and they both are actually penalizing. They both are penalizing for the degrees of freedom, you can say, and this 2k over here and this KLNT. See, the first term is same. The difference is in the penalty factor only, 2k and KLNT. Okay, so they both are actually penalizing for the extra number of degrees of freedom, you can say. Now, difference in penalty has two implications. The BIC, it is analogous to, I'll tell you what is happening. It is analogous to adjusted R square, how it was penalizing for the extra number of independent variables. Okay, so how it was penalizing for the extra number of independent variable, AIC and BIC are something like that. There is some bias variance trade-off actually. They try to balance the cost and benefit of different specifications. Okay, and if you see the first term over here, it is actually adding a penalty of 2k. So for every parameter, 2 times the number of parameters will be added. So if the k is 1, so penalty will be 2. If k is 2, penalty will be 4. Whereas for BIC, it is having a cost which is initially a bit low. But as you increase the value of t, it is actually increasing with not exponentially, logarithmically increasing with the value of t. So the penalty term is different. So this difference in penalty has two implications. The BIC always selects a model that is no larger than the model selected by the AIC. And BIC is a consistent model selection criterion. Now, this part, I believe it would have been better if, these are portions where we believe that it would be better if GARP also introduces, RStudio or Python, at least with these topics, so that you can understand these things in a better way. Because there is a limit to theoretical understanding to these topics, because nothing more you can understand. Either it will be high level mathematics, or the best idea is use the coding part, use Python, and try and visualize what is happening over here so that you get a better idea. Okay. Now, there is one methodology which is known as Box-Jenkins methodology. See, there can be, it is possible that maybe there will be models which have different parameter values, but they will have the same ACF value, same PACF value, etc. So if these models are equivalent, how to choose the best model, how to choose a better model? This methodology is used to choose a better model, the Box-Jenkins methodology. So there are two principles. One is parsimony. If the models are equivalent, of course, you will go with the model with the fewer parameters. And the other is invertibility. So it should be selected such that MA coefficients are invertible. Again, the math part is not there, so you'll not be able to understand it. There is a proper criterion of invertibility, which actually, in fact, we deal in class 11, 12 also. Invertible functions, if you remember. The idea is same actually. But since there is a lot of restriction on the mathematical part, so we will just remember this. Yes, the theory part can be asked. See, they can ask, what are the two principles of Box-Jenkins? Got it? Because there is no mathematical touch over here. They will just ask, what is the meaning of parsimony? Fewer parameters, more parameters. Got it? So they will ask, based on the idea, or based on the principle of parsimony, which model should be chosen? That's it. Theoretical questions can be asked. And forecasting is very simple. You just try to predict the forecasts, try to predict the future based on the current information, conditional on the current information. And this part you can just go through the PDF directly. So there are 3 rules. We have discussed this part extensively in the class, that why these rules should be applicable, and then we have derived a forecasting model also. Now, series with deterministic seasonality are non-stationary, whereas those with stochastic seasonality can be stationary. Okay, and seasonality can be introduced into the AR component, the MA component, or both. Seasonality will be discussed in non-stationary. So let's continue with non-stationary without a break. So any time series that is not covariance stationary is non-stationary. So the 3 conditions that we were talking about, if any of the condition is violated, so can you just quickly recollect what were those 3 conditions? Quickly. What were those 3 conditions?
Constant mean and non-variance less than infinity.
Correct. So mean, constant, stable over time, autocovariance structure. Very correct, absolutely. You can directly send, instead of DM, you can also send it to everyone, no problem. Yes. Variance finite, absolutely correct. Yes. And covariance structure, stable over time, right? So what is the meaning of that? What is the implication of the third point?
Covariance stationary.
Yes, no, the third point, in terms of autocovariance, what is the implication? The first point is mean is constant. Second is about variance. What about the third point? I'm asking. What was the third point? I mentioned also, I gave a hint just now. Stable autocovariance structure, something like that. I think. Yes, correct. It only depends on the distance, not on time. Very good. Yes. So that is the implication. Okay. So if any of these conditions is violated, then you will have a non-stationary time series, and there are two main sources. One is time trends, and then you have seasonality. In fact, three main sources, sorry. And then you have unit root, which is a random walk process. Now, with respect to unit roots, personally, I think that again, the mathematical part is actually quite extensive, and a very limited information has been given on unit roots and its derivation, how to find out unit roots. But there is one test, the ADF test, which we have discussed in the class, the full implication. Today it will not be possible in the crash course, but go through that ADF test also properly. Okay. The details, we'll discuss the steps, but you go through the details. At least one example you should go through before the exam. And the time trends part is quite clear. Seasonality is not very difficult at all. A time trend is simply, it is shifting the mean of the series. So, you know, if suppose there is a trend, like in non-stationary, the mean was not shifting. Over here, there is a trend. Maybe it can be an upward shift or a downward shift. So you can have linear trend models like this. Maybe it is an upward shifting model, downward shifting model. So the trend is going upwards. And this is very clear when we do stock trading. You know, there are always trends, right? So the same trend, this is the same trend that we are talking about. Then you can also have quadratic trend models like this. So in quadratic trend, you clearly see that the power of t is 2 over here. Okay. And this is the general form. If you extend, if you go for higher order trends, in case of, say, if you include more number of powers of x, so you can say polynomial time trend model, you can include higher powers of x, and this is generalized like this. Then you can have logarithmic trend models. So you can have log linear trend models like this, where yt will be equal to delta naught e delta 1t. If you take log on both sides, you will get this. Again, properties of logarithms and these derivations have been discussed in the class, but derivations will not be asked in the exam. The conceptual part is that this is what will happen. This is an exponentially increasing model. You can see that. This one, the first one, is an exponentially increasing model. As soon as you take the log of this on both sides, you actually get a linear model. So it is quite close to a linear model. The trend is linear, right? So this is the log linear trend model. You can also have log quadratic trend model, but that is not going to be asked in the exam. Then seasonality, seasonal pattern, as the name suggests, it repeats itself, and it can be exact, which means deterministic seasonality, or approximate stochastic seasonality. It appears a lot in financial and economic time series. You can have example as the January effect, where the equity market returns, they are more in January as compared to other months of the year. You can have other calendar effects as well, like, you know, Monday effects are there, and Friday effects are there. It has been observed that in the US, statistically, Monday returns have been statistically lower than Friday returns in the US equity market. But different these kind of seasonality patterns can be determined and identified. Then deterministic seasonality. Now, deterministic seasonality produces differences in the mean of a time series, which are quite easy to model using dummy variables. Okay, so this is how it should be modeled. One important part, in fact, we'll go through an example for this. Just see what is happening. If suppose you have S periods, then you don't need S dummy variables. You need S minus 1 dummy variables, and I'll show you why. There is a reason. So let's take an example. Let's say this is your model over here. Okay. Now what we do is we are trying to estimate the parameters using OLS regression. We are regressing YT on this constant and 3 dummy variables. So we are assuming that there are 4 quarters in 1 year. Okay. And the repetition is after every quarter. So it means there are S periods. There are 4 quarters. To model those 4 quarters, we only need 3 dummy variables. This is just analogous to, you know, the trinomial distribution. We said that there are 3 possible outcomes, but only 2 components are sufficient because the third is already implied. So the same case is over here. See how. Suppose this is the I1 dummy variable. I1 takes a value of 1 in the first quarter and 0 in the other quarters. Okay. So you can see it repeats itself after every 4 periods. Agreed? Is it clear, I1? Is I1 clear? Similarly, I2 is a variable which takes a value of 0 in the first quarter, 1 in the second quarter, and again 0 third, 0 fourth. This also repeats itself after every 4 quarters. Similarly, I3. Tell me, do we even need a I4? Or I4 is implied from I1, I2, and I3? Can I say when all three variables, I1, I2, I3, when all of them are 0, it is I4. It is the fourth quarter, correct? Do you agree with this or not? Implied, exactly. So there is no need to have a separate dummy variable. So that's why S periods means you need S minus 1 dummy variables. So if you want to find out the predicted value of Y in the fourth quarter, so in the fourth quarter, what will be the value of I1, I2, and I3?
0.
What will you substitute? Exactly. You will substitute all of them as 0, 0, and 0, and you will get simply 2.5. Similarly, if you want to find out predicted value of Y in the first quarter, then only I1 will be 1, remaining will be 0. Similarly for second quarter. So is the idea of dummy variables clear? Is the idea of dummy variables clear? Okay. Now, this is a very general model. It includes everything. It includes a time trend, the first part, delta 1t. It's a linear time trend, of course. With S minus 1 dummies or S minus 1 dummy variables, it includes seasonalities. Okay? And this part also includes the cyclicality because it's an AR term. If you remember, phi yt minus 1 was an AR term. So if phi yt minus 1 is also included, it captures the cyclical component, how yt depends on itself. Okay, this is a very general term which captures everything. Now let's come to random walks and unit root. Now this definition, again, you might have seen these things many times in the books and you have tried to understand these things. Things might have gone above your head, but sometimes things are not very difficult. See, this says that a simple random walk process evolves according to this. So it's simply that a random error term has been added to the previous value to give the current value. That's why it's a simple random walk process. That's it. Okay, similarly, if you try and extend this recursively, can you write for yt minus 1, can you write this? Can you write this for yt minus 1 for a random walk process? So any random term has been added. There is no phi. You can see that there is no phi. The coefficient of yt minus 1 is not there. Do you agree that you can do this for yt minus 1? Okay, fine. So you can see that doing this recursively, you will get y0 plus a lot of error terms. Finally, you will reach up to y0. Okay, you did not get it. Let's come back. This first part is clear, Pooja. This is a random walk process. Okay, because there is no phi. I mean, a random error term has been added to yt minus 1. So same thing, if you substitute t minus 1 instead of t in this equation, if you substitute t minus 1 instead of t, what will you get? Will you get yt minus 2 is equal to, sorry, yt minus 1 on the left hand side, and this will become t minus 2, this will become t minus 1, correct? You will get this. Correct? Okay, so this thing you actually substitute in this equation for yt minus 1. Got it? So that is what you are doing. And of course, so continuing like this, there will be a point when you will reach up to y0 and there will be a lot of error terms added. So you can see this is what is happening. So random walks, they are placing equal weights on all shocks as well as the initial value. So this is a very strange process, right? Whatever happened today is having equal weight as all the random terms that happened, after today, then day after tomorrow tomorrow, day after tomorrow, day after that, like that. Okay, so it permanently, a shock in any period will permanently affect all the future values. They should not happen. Even this was not happening in MA process, this was not happening in AR process also. Okay, so that is why we said that when phi, if you remember in AR process, we discussed if phi equal to 1, it will become non-stationary. So that is what has happened. Phi is equal to 1 over here. The coefficient of yt minus 1 is actually 1. So that is the problem. It has become a random walk process now. Okay. No, et will not be a constant. It will be a random term again. It is a random term. Got it? It is a random shock. Fine. So this is something which you need to just remember from the point of view of the exam, that they place equal weights on the shocks as well as the initial value. Now unit roots generalize these processes. Unit roots, they generalize these processes, and these are the challenges in modeling a time series that has unit roots. So these three challenges are there: DF distributions, spurious relationships, and it will not mean revert. So the problem has some solutions. One of the solutions is to take the difference of time series. Again, we have discussed this in detail, the differencing process and all. But I think in the exam point of view, they will just ask about the solution. What is the solution? Which of one of the following is a solution to the unit root process? To the problems faced by the unit root process. Differencing a time series is a very good solution. Okay. So if yt has a unit root, then the difference will not have a unit root. We have proved this actually, okay, in the class. So ADF unit root test. This is the ADF unit root test. Again, just like one of the previous examples, it might be asked, not the process, it might be asked that the ADF test regresses delta yt on the following. Which of the following is not one of them? So it regresses delta yt on lagged level, on deterministic terms, and on lagged differences. So this question can be asked in this format. Remember that this is a constant over here in the deterministic term, and this is of course the trend part. So in the deterministic term also, there are two components, delta naught and delta 1. One is the constant, one is the trend part. Then you have the ADF test statistic, and there are two choices, which deterministic terms you have to include and how many lags you have to use, the number of lags of difference data to use. Now again, remember, this is going to be very, very theoretical in the exam. So these steps are very important. These choices are very, very important. Then seasonal differencing, you can just read this. This is also something you can just read directly. Yeah, okay, this we can do. Spurious regression. Now, spurious regression is a common problem when you are modeling the relationship between two or more non-stationary time series. So that is the common problem. It occurs quite frequently when both the dependent and one or more independent variables, they are non-stationary. Okay, it is not an issue in stationary time series. Remember that. This is not an issue in stationary time series. So if we are able to ensure somehow that these variables xt and yt are stationary, maybe by differencing, then this issue can be addressed. Okay, so the cause is misleading statistical relationships between dependent and independent variables, especially when they are non-stationary. If we are able to ensure that they are stationary, then there will be no problem at all. Okay, now this is the forecasting of time trends. Same idea, forecasting, I'll not go, just replace t with t plus h. And this is the expectation. Confidence interval, again, same idea. In practice, remember, this sigma is not known, but it can be estimated as the square root of the residual variance from the estimated regression. So confidence intervals can also be constructed like this. Fine. So we just end this chapter. We can just complete the last chapter for today. That is measuring returns, volatility, and correlation quickly. So returns, they can be simple returns. They can be logarithmic returns. Simple returns are calculated like this. Logarithmic returns are calculated return over period, and they are denoted as RT. It is ln pt minus ln pt minus 1. So good part about this return of the simple returns is that if you want to find out return over multiple periods, this equation will hold good. 1 plus RT will be equal to product of 1 plus R1, 1 plus R2, 1 plus R3, like this. So it is kind of a geometric mean result. And the good part about logarithmic returns is that it is even more simple. If you want to find out the return over multiple periods using logarithmic returns, you simply add the returns. Directly you add the returns, you will get the return over multiple periods. So if logarithmic returns are given in the exam and you have to find out the return over multiple periods, you just add the returns. Okay, and this is the formula, the relationship between simple returns and logarithmic returns. So can you tell me which one will be greater, RT or capital RT or small rt? If this is the relationship, can you tell me which one will be greater? Any idea?
Capital RT.
Capital RT will be greater mathematically, yes. Now, simple returns can never be less than negative 100%. That is a total loss, but log returns can be less than negative 100% whenever simple return is less than negative 63. So this simple additive structure of log returns, it makes them more attractive in cases where the error is small. But there is a problem. You can see that the log returns can be less than negative 100%. So this situation has to be avoided. Now, this thing we have already done earlier, that if suppose the volatility is sigma square in variance, then the square root of variance is the volatility in terms of standard deviation. And for daily returns, daily volatility will be calculated. This we have also done, that mean and variance scale linearly. Remember, they get multiplied by n, both mu as well as variance, whereas volatility scales with the square root. So this gets scaled with the square root. So for example, if you have to convert daily volatility into annual volatility, you will multiply it with square root of 252 because there are 252 trading days in a working year. Okay. And if you have to convert monthly to annual, you'll multiply it with square root of 12. This result can be directly asked in any question in the exam, not only for this chapter, but also for VAR. Okay. Then one of the very common questions being asked from this chapter is the Jark-Bera test. I remember, in fact, in our class, this chapter was, I think, skipped. So one of the candidates, they asked about the Jark-Bera test only. If I'm not wrong. It was Akshay or Sushant. So many return series are both skewed and fat-tailed. So Jark-Bera test statistic is used to formally test whether the returns are normally distributed or not. So tell me, if the returns are normally distributed, what will be the skewness and kurtosis of normal distribution? 3 and 3 will be the kurtosis. Skewness will be 0. So this is your null and this is the alternative. 0 skew and k equal to 3 is the null. But this is something which you want to reject. Why? Because you believe that there are return series which are skewed also and fat-tailed. This is your belief. So at least one of these properties will not hold. That is what you think. So either this or this will not be true. So it means either S will not be equal to 0 or K will not be equal to 3. Yes, I should have said either this or this will not be true. So it means either S will not be equal to 0 or K will not be equal to 3. S is the skewness, K is the kurtosis. The Jark-Bera test statistic is this. So you do this calculation. In fact, we did one example also in the class, I think 2-3 classes back only. Okay, and you remember these two critical values from the point of view of the exam. I think they will give you also these values, but if they don't give you on the safer side, try and remember these values. Okay, so when the test statistic is above these values, remember that the null can be rejected. So if you reject the null, it means the data is not normally distributed. And you can clearly see if skewness is high and if kurtosis is high, it means the test statistic will become higher and higher. Then there will be more chances of rejection. So it will be easy to conclude that they are not normally distributed, which makes sense. Now we are just coming to the end of the chapter almost. So this part you already know, I will not discuss. This is the simple correlation which we have already covered till now. Next, I will discuss the Spearman coefficient. Now, Spearman's correlation coefficient is sometimes referred to as the Pearson correlation for ranked variables. So these are the steps to get rank correlation. The first step is actually optional, but I think this is easier. This makes your job easy, the first step. It is not given in the book, actually. I have added it separately because I think it makes your job easy. If you actually rank them, at least one of the sets, then it becomes quite easy to compare. But anyways, this is optional. Even if you don't rank according to X, you rank them individually, then it is okay. Sorry, even if you don't order first with respect to X and you just rank them directly, even that would suffice. Then the ranks are derived, and difference is rank is termed as DI, and then this is how the rank coefficient is, rank correlation coefficient is calculated. So this DI can also be directly, either you can write it as DI or simply you can write it as Rx minus RY, whatever you want to call it. So let's take an example, a short example from the GAR group. So this is the data set you have. How to calculate the rank correlation coefficient. These are the steps. Again, the ordering has not been done. The optional step has not been followed by GAR, as I mentioned. What I meant to say is that what you do is, I first prefer to order it with respect to X. So it means that I arrange it in ascending order with respect to X, so that my Rxi becomes 1, 2, 3, 4, 5, 6 quite easily. That is how I do it. So like this, say X, Y, I'll rearrange this set and I'll write X, Y. So which is the lowest value on X? Can you tell me? Which is the lowest value for X? Quickly. Lowest value. Right, it's given also.
3.08 minus
Correct,
3.08.
negative 3.08. So I'll write negative 3.08 first over here. And then corresponding to negative 3.0, you have negative 0.9 and negative 0.9. So I'll completely rearrange this data and I'll order this based on the values of X only. Then I'll write the second highest value, which is negative 0.75. Now corresponding to this negative 0.75, you have negative 5.14. Okay. And then why it makes my job easy is because Rx is quite easy. Rx is simply 1, 2, 3 like that, 4. Got it? And then you just have to calculate R1. But again, this is an optional step, and it's not at all difficult to calculate the ranks also directly. There is no problem at all. So first you calculate the ranks of all the X's. Okay, so this is the first rank. You can do it directly over here, 1, 2, and obviously it is written over here. So these are the differences in ranks. These are the DIs. Okay, and this is summation of DI square. So once you calculate summation of DI square using our previous formula of 1 minus, what was the formula? 1 minus 6 divided by n times n square minus 1 multiplied by summation of DI square. Right? This was the formula, correct? So use the formula and you'll get this. 1 minus 6 times 32, which is 0.81. Is the calculation clear? Is the calculation clear? Okay. Now, Kendall's tau is also ordinal and non-parametric. Okay. What is the difference between cardinal and ordinal? What is the difference between cardinal and ordinal?
Ordinal, both X and Y go in same direction. Ordinal, they go opposite direction. X increases, Y
that is not the difference. That is not the difference actually, because over here you will find both cases. Yeah, it is with respect to ordering. Correct. So see, actually, ordinal is actually giving you order. You can say categories with some kind of an order. Okay, but it is not necessary that there will be equal intervals between categories. So it is simply basically order or ranking. Right. So if I say that, all of us are having different levels of experience, right, in this batch today. Some of you are having, say, 3 years of experience. Let's less than 3. Let's call all the people who are having less than equal to 1 year of experience as freshers. Then let's call the people who are having anywhere between 2 and 6 years of experience as intermediates. Then more than 6 years of experience as experience. So we can have 3 categories. So this is ordering. Okay. Whereas in case of cardinal, the differences will be very, very important. The differences between the measurements will be very, very important. They are actually, that is why they are also known as intervals. That's what, because differences are important, or ratio data. So whenever differences between the values are meaningful, because there is no difference between, say, intermediate and fresher. I mean, in general, if you don't know what is the exact category, you don't know what is the difference. Similarly, for a survey, if I give a survey after this class, let's say, how happy were you with today's class? Some of you say happy, some of you say extremely happy, some of you say just satisfied. So what is the difference? The exact difference, the magnitude between the two, we don't know, right? So when the difference is also very important, order is important, of course, in cardinal also, but the difference is also important. Got it? Is it clear? Ordinal only ranks, cardinal both ranks as well as the magnitude difference. Okay. So Kendall's tau, it measures the relative frequency of concordant and discordant pairs. It is defined like this: NC minus ND divided by N times N minus 1 by 2, where NC is the number of concordant data pairs and ND is the number of discordant data pairs. Now, what you answered just now when I asked about ordinal and cardinal, you actually answered about concordant and discordant. See, the pair is concordant if suppose xi is greater than xj and also yi is greater than y. If you are comparing two pairs, okay, then in fact two pairs, I should say, what has happened is the pairs will be concordant. They should have used plural, I think. Anyways, the pairs will be concordant if xi is greater than xj and yi will be greater than yj, or opposite, of course. But it will be discordant if xi is greater than xj and yi is less than yj. And it will be neither concordant or discordant if they are equal. So I'll just tell you what is happening over here. So let's say this is the data set. Okay. So the first step that you have to do is that you have to rank the two series separately. So these are the ranks: 5, 5, 2, 4, 4, 1, 3, 2, 1, 3. So we have identified the ranks. Then we have to see which pairs are concordant and which pairs are discordant, which pairs are neither concordant nor discordant. So basically, I have to do the comparison of each pair with the other pair. Okay, and remember one thing, that we don't have to do it twice. So it means that if you have already compared 1, 2, it means 2, 1 is same as 1. We already compared it with 2, 1. I'll explain in the next diagram when it comes up. So this is how we are doing it. So let's compare pair 2 with pair 1. So this is pair 2. Compare it with pair 1. See, is 3.12 greater than negative 1.26? Yes or no? Correct? And 2.58 is also greater than negative 0.05. Do you agree this is correct or not?
Yes.
Yes. So they are concordant pairs. Understood? So that's why a C is written over here. And of course, as I said, I don't need to perform the calculation once again over here. So that's why this section has been blocked, because this and this, they are the same. They will give the same result. So we are comparing pair 2 with pair 1. So why I'll do it twice. Now, if you see, since the rank of the first pair is actually highest on both x and y, you will actually find that all the pairs are concordant with pair 1 with I equal to 1. It is guaranteed. You can check it for all of them. Let's verify the case for a discordant pair. So let's compare 3 and 2. Let's compare 3 and 2. Let's compare 3 and 2. Is 2.08 greater than negative 1.26? Yes. And Is negative 0.72 greater than negative 0.05? No. Negative 0.72 is actually less than negative 0.05. So these pairs are what? These pairs are
Discordant.
discordant. So this is how we do for all of them. And then you find out the number of concordant pairs, number of discordant pairs. How many number of concordant pairs are there?
5.
5. And discordant pairs also 5. Right? So basically, we did so much of hard work. Finally, we got nothing. No candle star. This is in Hindi we call na Khuda pahad and nikli chuhiya wala thing has happened actually. So basically, everything is same. There is no correlation we were able to find out. Okay. So, but of course, in the exam, even this is important. The candle star of 0 is also possible. So, is the method clear? How to find out number of concordant and number of discordant pairs, and how to find out candle star? Okay. Fine. Okay, fine. So that's it for today's lecture. It's been 8 hours almost since we started, and I think we took some breaks also in between. But still, you guys it sat for I think more than 6.5 hours at least, 6.5 to 7 hours. Okay, so how effective was the session? Did you feel that the session was a bit helpful for you? Okay, fine. So shall we continue like this for other modules as well? Fine. So we'll definitely have the sessions for FMP. Now, one thing I have an idea, and one thing what we can do is, let's say that, like for example, today in quants we are still left with 3 chapters, right? So because of lack of time, see, let's do one thing rather than having it again as a live class. Anything which is left, because in any case we are trying to condense the lectures as much as possible. If you see the videos for these 12 chapters, these 12 chapters themselves are having more than 35 hours of videos, which we have covered in 6.5 hours, right? So if suppose, yes, the recordings will be shared with everyone. The recordings will be shared with everyone. It will definitely be shared by today only in the LMS. Okay, and on YouTube, if at all it is shared on YouTube, then of course you all can watch. I'm not very sure about YouTube right now. It might be, it may not be. So yes, I'll answer the questions also now. So I said that first I'll just discuss this part. Let's say we have 3 topics to cover in quants. Now, instead of taking those 3 topics in the live class, it's better that I record the crash course for those 3 topics, and then I will upload it in the LMS. That will be better, right? Because see, we cannot have, then things will get postponed a lot. So today was quants. Let's do away with quants for today, right? And then another lecture will be recorded. Right. Absolutely. Fine. So yeah, it will be on the LMS only. We'll not be able to share it via mail, but you'll get a notification when it is uploaded on the LMS. You'll get an automatic notification on your mail. Fine. So there was a question regarding mocks. Who was asking? I think chat has disappeared. Yes, question was how long must we spend on a mock revision? See, I will say first you have to take 5 mocks at least, right? 5 mocks you should take. And to revise based on your results of that mock, I think you should devote at least 1 day. That's what I will say. And that is how we plan our, we give 5 mocks. I mean, just 1 month before the exam, we start the mocks. Mocks have started, by the way, MF candidates. You can just message on Telegram and get yourself registered for mocks also, the CBT based mocks. So once you complete the mocks, at least take 1 day to get a proper assessment of how you perform and work on your weak areas, tie up some loose ends, whatever you have. So that is the idea. Okay. Yes, absolutely. Again, see this kind of question when it is asked, Rohit, if we saw 15 years past papers given in our LMS, will it be enough for clearing? I always say that if you have done everything properly, then it is more than enough for clearing. But again, have you also done the PDFs? Have you also solved our question bank? Have you also watched the videos? Then yes. then it is enough for clearing. So conditional on the fact if you have done all the resources properly, if you have covered all the resources properly, then it is enough for clearing. No problem. For the remaining courses, see actually, Oleami, we actually have a notification. If you see, there are reminders being sent. You check your mail. All the candidates who were added to the LMS, you will get reminders on your mail. That is how the LMS is structured. We send a reminder at least 1 day in advance and 2 days in advance also. On Saturday only, many candidates who enrolled before Saturday, they might have got received these mail reminders. And even on the app, if you install the MidhaFin app, you're going to get notifications on the app also that live class is about to start in 24 hours, live class is about to start in 36 hours, like that. Okay. So you just install the app or you can check your mail. Okay. Thank you, Niharika. So this was the first crash course session. Yes, Pooja, this was the first crash course session. Sushant is asking, there will be a separate course for mock series. We will try, Sushant. Definitely we'll try. At least 1 or 2 sessions we'll give, because we give it every time. So for mocks, once you complete all the mocks, we will have a separate doubt session for mocks as well. Okay, but that will not be taken by me and the other instructor. Yes, we'll have a separate doubt session. Yes. Yes, that's why I mentioned that you message on Telegram, Sushant, and you'll get access to it, because the mocks are hosted as a separate course. That's why. Okay. So all the candidates who have enrolled, they automatically get added to that course also as soon as they message on Telegram. So that is the idea over here. Understood? Okay. Next. Anything else? Okay, fine. So thank you very much, everyone. Enjoy your evening. I mean, you have 1 or 2 hours at least to enjoy. And let's meet in the next session. We'll have FMP. At least be prepared as much as possible with FMP. Have a quick overview of the concepts. Learn the formulas. If possible, solve questions in the class with me. Because see, when I am solving questions, when I am illustrating the formulas and all, you should also try, and only for questions. See, for notes, you don't need to take any notes. As I mentioned, the PDFs will be shared with everyone. But you can always try to solve questions when I'm solving them. Okay, even if you're not able to do it as quickly as they are being shown through the animations in the slide, but still at least you are trying, you're getting a hold of that. So always keep a notebook with you, at least for solving questions. Fine. Anything else which you guys want to discuss? Okay. Thank you, Pooja. Thank you so much. Thank you. So I just end the session then. Good night, everyone. Good evening. Good night.